So as you start getting better simulators, we're noticing that you can start doing sim to real, and this is working without any real world adaptation. Okay, so towards this, we released about a year ago, we released Obgiverse. And Obgiverse 1 and Obgiverse XL together represent 10 million high quality 3D objects, right, in simulation. And if you look at scale and if you look at quality, the Obgiverse family of models completely surpasses, previous data sets that we've had before. And many of you and many others in the field have already started using Obgiverse in your work. And we've seen some wonderful adoption in building all kinds of 3D powered systems. And so today I'm going to take a little bit of time in telling you about, just a sample of diverse applications that have been powered by Obgiverse and which are now, in a sense, more 3D aware. First, I'm going to talk about learning to interact in the 3D world and how Obgiverse has powered the diversity of interactions and the generalizability of robots. Then I'll tell you how 3D assets can actually improve 2D image generation. And then, of course, the obvious set of applications in the 3D world itself. So about 18 months ago, we were thinking about how do we scale up data for robots? And so the obvious answer that we've been working on for several decades has been simulation. But ironically, simulation has also remained in the small data regime. That's because simulators are built by hand. And so what we decided to try was to see if we can build simulators procedurally, right? So this was a work from a while ago, which said, let's write down the specification of an environment, and then let's write down a set of procedures in order to start sampling a layout. Given a layout, you can sample what objects you want to place, how you want your lighting, how you want your materials, etc. And what this gave us was hundreds of thousands of houses in which to train our robots to perform tasks. And the learning that we got from this exercise was that as you scale up the number of environments in simulation, downstream tasks keep improving, not just in simulation, but also in the real world. So how can we expand upon this to give the user more flexibility in creating more rich environments, particularly now that we have Obgiverse? And second, how can we extend this to domains beyond houses? And towards this, at this CVPR, we'll be presenting a new framework called Holodeck. Holodeck is a system that leverages natural language to produce rich 3D environments. So gone are the days when we have to create this ugly tree structure with just a few constraints about connectivity between rooms. Now you can simply specify in natural language what kind of environment you want. And you can specify how many you want, and it can generate a countless number of environments for you to train robots. And we do this with the power of large language models. So I'm going to skip over the details here, but at a very high level, large language models can convert natural language to layouts. And they can, given a layout, they can start guiding us in how we should place objects, what kinds of materials, etc. They aren't perfect. And so it's often the case that you have to do some sort of constrained optimization to make sure that your environments are physically realistic, that there's enough space, for example, for robots to run around and pick up objects, and that they are viable in a physical simulator. But once you do this, you can get these kinds of rich environments. So see, this is much more rich than just saying, I want a kitchen connected to a bedroom. 3 professors' offices connected to a long hallway, and the professor in Office 1 is a fan of Star Wars. And you go to Office 1 and you see that there's some like Star Wars memorabilia there. So what does this give us? When you start scaling up 3D assets, right, you can really start producing generalizable agents. And so the graph there on the left shows one of the tasks that we were interested in, which is identifying objects, navigating around obstacles. So you have to be 3D aware. And then navigating towards this object, taking a photograph of it and saying done. And the previous state of the art in these kinds of tasks is very low. It's about 20, 30%. And we've been working on these problems for many years. But at scale, not only do we break the barrier of 40% on this benchmark, you can see that now we're just compute limited. At 700 million frames of experience using reinforcement learning, robots can now perform more than 80%, and the numbers keep going up. And as I promised, getting into simulation in order to source 3D aware data doesn't keep you in simulation. You can take these agents and put them onto real robots without any real world adaptation, without any real world fine tuning. And you can see a robot being able to effectively navigate in an environment it has never seen before, go to a place, and then even find complex objects. Like it can find a book titled Humans. Okay, so as I promised, 3D objects can also help improve 2D models. Image editing is a task that has a lot of applications. But a lot of the times when you make edits to images, you end up making edits that are not physically realistic. What you really want when you make edits, when you move objects, when you add objects, when you remove objects, is to be 3D aware. And so you want to make sure that you respect occlusions, you respect perspective changes, you respect lighting, you respect novel views. So how do you source this kind of data? Well, the answer, once again, comes to leveraging high quality, large volumes in Observers, and then doing this in simulation. So instead of simply crawling the web and hoping for images with small changes in objects, you can place these objects in a simulator. You can do whatever transformations you want. You can change the lighting, you can change the objects, you can delete things, etc. Take pictures of them onto the 2D image plane, and then use these pictures to train a model. And so here are some examples of objects that are placed on different kinds of surfaces with different kinds of backgrounds, with different kinds of transformations. And then you can use these large data sets to fine-tune diffusion models in order to produce much more physically realistic image editing techniques. So these are results on unseen test sets. And this is in-domain performance. So this is our data set called Object, where you can place these objects on a surface, and you can say, move the bookcase, rotate the skull, insert a baseball cap, etc. It works really well. But in-domain isn't very interesting because you train on it, of course, you're going to do well on it. In simulation, you can also show that you can go out of domain. And so if you go to, for example, the Clever data set, it generalizes well. But that's not interesting enough. What's really interesting is that you can take pictures in the real world, and this object editing works really well on all kinds of transformations. And of course, there's some pretty gifs of, if you continue to do these edits in the real world conditioned on your previous images, then you can start getting into video. Okay, and then finally, of course, there's, the community has worked with Observers on lots of different 3D applications. And so one of the first big applications that came out when we released Observers was 0123, which became very popular for novel view synthesis. And then we showed when we released Excel that when you go from 1 million to 10 million objects, novel view synthesis continues to improve. Now, how does novel view synthesis work? You have an object in Observers, and then you start taking pictures of this object from different angles. And then now you can train a model to input an image, input a transformation, and output a picture. And of course, then you can sort of output all pictures from all different sides, and then you can do 3D reconstruction. This is very powerful and very useful. But in the end, we also want to be able to model the real world, which is not just independent objects. These are objects in context. And so instead of just being able to 3D reconstruct a single car, you want to 3D reconstruct an entire scene. You want to be able to 3D reconstruct all of these vehicles on the road, all the trees around them, the buildings in the background, etc. So ideally, what I would want is to be able to take a scene, and just like I did with, Observers, and just like the authors of 0123 did, I would want to take multiple views of the scene and then learn extremely powerful models for 3D reconstruction. How do I do that? So for many years, people in 3D have been thinking about using video, right? Video is a holy grail of getting lots of information about our real world. And so this is what a typical video on YouTube might look like. This is someone presumably on holiday, carrying a cell phone and walking around showing, capturing pictures of this location. And so you walk around and you see that the camera moves a little bit. And then you end up getting different views of a scene. The problem with these kinds of videos, in order to source data for novel view reconstruction, is that there isn't a lot of overlap in the images. I really want to look at what the first frame looked like, but from the other side of this park. How do I source this data? Now imagine I did I reversed. But now as I walked around, I had the ability to look around. And then I walk around ahead. And then anytime I want, I can look around in all directions. And this is data that you can get from 360 cameras, right? So when you have 360-degree cameras and people carrying them in their hands or people attaching them to their heads, you can get extremely powerful data for novel view synthesis to build 3D models, not about objects, but about the world. And this is our new data set that we're going to release in a couple of weeks called 360 1 million. And so these are 1 million data sets, 1 million videos of 360-degree cameras of people walking around in all kinds of locations, right? And so just from these small thumbnails, which were not cherry-picked, you can see urban areas, you can see rural areas, you can see people going on hikes, you can see people walking on glaciers, you can see people being underwater. All kinds of information about the world can be sourced from this data. So watch out for this on our release and on Twitter. And you should get access to this data very, very soon. So we just wanted to scratch the surface and sort of tease what you can do with this data, right? Just the first tease of what people can do with this data. And so we said, okay, let's use this data to do multi-view synthesis. And so how do we do this? So a usual YouTube video where I have a camera, let's say I have a GoPro on my head, walking straight, is something that you see on the left. And what you see on the right is what you get with 360-degree video, right? And so at any point in this trajectory in the real world, you can look around in all different directions. So the way we sourced good data for novel view synthesis was we said, okay, we're going to grab a frame in this trajectory. Then we're going to look in its neighborhood for frames that have a reasonable amount of overlap. And we do this with Duster. And then, given those 2 points, we then, in a sense, do gradient descent to figure out what angles we should orient these cameras so that you can get interesting data for novel view synthesis. And so here's a sort of a schematic of what we did. Here's an initial frame, and I want to find a nice frame in the next few frames, which are appropriate for my modeling. And so I can take one of these query frames, and then the query frame looks at something completely different. It's a little bit far away in translation world. And then I can start rotating, and I can use Duster to give me some correspondence scores. And then I can start figuring out where can I get my maximal correspondence score. And now you can see these 2 images are real world images that would be perfect for this kind of work. And that's what we did. So we took a little bit of the data from this data set. Oh, sorry, before I go there, this is what you get when you look at the data statistics. There's 1 million plus videos, 80 million plus frames. And as you can see, these videos are from lots of diverse domains. There's videos of people playing with their pets. There's news stuff. There's stand-up comedy. There's music. There's sports. There's all kinds of stuff. It's amazing how many people are interested in putting 360-degree cameras on their heads and walking around. It's fantastic. Okay, so we train a model very much like 0, 1, 2, 3, where we take an input image, and then you can have a rotation and a translation as input parameters. It's a conditional diffusion model, which is trained to predict the generated view. And so now if you have a single starting view, which is the image on the left, you can simply specify how you want to move in space. And then along this trajectory, you can run your diffusion model conditioned on the previous image you generated. And then all of the images on the right, like the second, third, and fourth, are synthesized views. And then you can do 3D reconstruction, and you can start reconstructing your 3D world. So for example, small GIFs of how this looks like. This is our model Odin. And so this is the input image. And then you can start all of the frames after the first frame are all generated using our model. And then you can throw these images into 3D reconstruction, and that's what you get. Here's another example of this. So this is fresh off the press. We have just literally got this data, and these are the first results we're getting, but we're very excited. I think this is going to power the next generation of, scenes or backdrops of 3D reconstruction models. Okay, so there's been a lot of progress in 3D. And particularly in generating 3D assets from text descriptions, right? And if you look at about well, it's 2024, so it's 8 years ago. If you look at models from 8 years ago versus models that are present today, there's a huge amount of progress, right? And it's very clear. You can, cluster these into two separate groups. And there's been, many reasons for this accelerated progress. Some of the reasons are access to, large scale data sets like Observers, but some of these are also building upon progress in 2D generation, right? So you can use stable diffusion models in order to improve your 3D generative models. And then as you look into more recent models, it's getting harder and harder to notice which model is better, which model works well. And there's a real need for good benchmarks and good metrics in order to allow us to continue hill climbing on this. Now, 3D models, especially when you see results in papers, they look really good. But when you start looking into the nitty-gritties of 3D models, all of you, I'm sure, are aware of this. They still suffer from lots of uh, problems, particularly in their details. So, for example, if you look at, this text prompt, an origami crane made from a map. If you saw these images in a 3D paper, you'd say, well, both of these images look great. It looks like kind of a map and looks like an origami crane. And so they both look great, particularly if you use a 2D metric for this. But as you start rotating them, the one on the left kind of looks like a piece of a map, piece of paper with a map drawn on it, and it does look like a crane. The one on the right, actually, when you start looking from all angles, it doesn't really look like a crane, right? And so it's important that we start evaluating these models on a more fine-grained basis. Here's another example, right? A plate of fried chicken and waffles with maple syrup on them. Looks fantastic from this angle. So what you're seeing here on the left is the 3D model rendered in RGB, images rendered in RGB. And on the right are sort of the surface normals. Then there's a couple of problems here. You see there's a little jar of maple syrup. It kind of looks like syrup on the waffle and then suddenly turns into a jar. And then at the same time, if you look at the pieces of chicken right on top, right there, you see that the surface normals are smooth, but the piece of chicken seem to actually be waffles, which means that the textures on the pieces of chicken are sort of, it's like you've painted a waffle on the chicken, but there's no actual 3D structure. And this is not criticizing the models. I think this is already amazing progress. But if we are to make progress beyond this, we have to start getting metrics beyond things like aesthetic scores. So how do we get metrics for this? Well, let's qualify 4 challenges that we are targeting in this work. First is structural inconsistency. And so this is something that, I didn't show a GIF of this because, everyone knows about this. You have people, you have animals, and then when you start rotating them, the tail looks like a face and the face looks like a tail. And so there's structural inconsistencies across views. Then there's text to 3D misalignment. Text is a corgi wearing a hat, there's no hat. Then there are semantic inconsistencies. So when you take images from 2 different sides, 2 different angles, from one angle you have maple syrup, on the other angle, the same point in 3D looks like a jar of maple syrup. And then there's, of course, geometric inconsistencies. So visually, you think that it is structured a certain way, but then when you go into the 3D asset, you realize that the geometry is actually quite different. And so in order to build metrics for these 4 issues that models typically have, we use different foundation models to the rescue. So how do we do this? So here's a text prompt, a Michelangelo-style statue of a dog reading news on a cell phone. And this is a 3D asset that has been, let's say, generated by a model. So the first thing we do is we take a rendered normal from an angle, and then we take an image in RGB from that same angle. And then we use an off-the-shelf foundation model or some other model in order to predict the normal, right? And then we look at the overlap between the predicted structured normal, surface normal, and the true surface normal of the 3D asset. And this allows us to create a metric for geometric consistency. Then you can take 2 different views of this asset, and then you can compute dyno features. And we know that dyno V2 features are really good at part-based localization, right? And so you can take these dyno features, project them back into 3D, and then for every point in 3D on the asset, you can compute the variance of this feature. So let me explain this again. So imagine that there is this dog. From one side, the image looks like a dog, and the other side of the head of the dog, and the other side, the image looks like a tail of the dog. Both of these come from the same 3D location. But the dino features are going to look very, very different on the 2D image plane, which means that when you project this back to 3D, you're going to have very high variance, which means that you're semantically inconsistent. And so this is used to create a semantic consistency metric. Then third, we take a rendered image, and then we create a predicted image using 0, 1, 2, 3 from a different angle. And this gives you structural consistency. And the idea here is that if you saw a 3D asset from one angle, you can predict what this dog should have looked like given the 0, 1, 2, 3 model from a different angle. And so now if you actually rotate the 3D object, if it suddenly surprises you, I thought it was syrup, and I think it should look like syrup here, but instead now you're showing me a jar of syrup, that is going to be structurally inconsistent. So measuring this consistency is also very helpful. And of course, fourth is text to 3D matching. So you can take the caption and you can give it to some sort of a language model, and you can ask questions about this caption, and you can get some answers only from the caption. Then you can do the same with a multimodal model and say, well, based on views of this image, is there a dog? Is there a cell phone? And then you check if these answers match in order to give you text to 3D alignment. And so this is a new benchmark that's also going to come out in the next couple of weeks called Eval3D. And so this is going to allow you to measure different metrics that can tell you about alignment and consistency on all of these angles. And you can see that they start making sense as you look at these assets. So for example, the one on the right doesn't seem to have a very high quality. And of course, it has a very poor aesthetic score, but it has excellent text to 3D alignment. You ask for 4 ripe apples in a basket, I'm going to give you 4 ripe apples in a basket. But the one on the left is much more aesthetically pleasing, but it has very poor text to 3D alignment and also suffers from different consistency issues. So I won't go into the details of how previous models work on, but this is very revealing in terms of what models suffer from what consistency issues and how, and it can give us ideas on how we can continue to improve 3D modeling. Okay, with that, I'd like to summarize. So, as I said, data has been a key driver of progress. Observerse has driven a lot of progress, and we're very excited to release 361 million over the next couple of weeks. Look out for it. We're excited to see what you can build with 361 million. And then finally, we believe that there's a huge need for high quality metrics in order to continue to hill climb as we make progress, and Eval3D is our contribution towards that. Thank you.
And thank you, Annie. I think we have time for a couple of questions.
Yeah, sure.
Hi. Could you please explain more a bit about your definition of structural consistency versus semantic consistency? I think you were using the same example to illustrate close consistency. So I was confused which one do you name structural versus semantic?
I see. Well, they both test similar things, right? There are different ways of testing this. So structural consistency basically says that does the entire 3D asset, right? Is the entire 3D asset consistent from different angles? Which means that if you have a 3D structure of an arm extended here, then when you rotate this asset, do you still have an arm extended or is it down? But this is done on a global level. Whereas semantic consistency deals with, because Dino is so good at parts, it deals a lot more with sort of part-based consistency across views. But they're both very closely related, and we had a debate about what nomenclature to use between these two. But we find that it's important to use both of these metrics in order to quantify the change.
Can you go back to your Apple example? Maybe try to explain why first example has a low structural consistency, although it looks pretty consistent from different views.
I'd have to look into that into a little bit more detail. No, the 4 apples is text to 3D alignment, right? The structural consistency, so the geometric consistency is very high because you can see the surface normals are, they respect the surface normals that you would expect from these RGB images. And the structural consistency, yeah, I don't know. This is probably an issue with, I think in order to get better and better structural and geometric consistencies, I think, as foundation models improve, particularly visual features improve with Dino, I think you can start getting better and better metrics. So yeah, it's a noisy metric because it's been obtained using another off-the-shelf model. But we see that when there are large-scale problems in 3D structures, these metrics do reveal quite a lot. Great question.
Highlight that for graphical consistency, if you're using 013, the MP3 example is typically like it shows lower score because from what you view in MP3 we use a different model rather than 013.
Sorry, I can't hear you. I'm sorry.
You use a different model for MP3 for multi prediction.
Yeah.
So if you have a bunch of models that are using 013, they would have higher structural consistency just because you're measuring structural consistency with 013. So it's kind of, if the score drop is large enough, then it's a good metric. But if it's like on the margins, then it might be.
Yeah, that's a great point. We see this with, we've seen this in vision and language as well. So in vision and language, there was work that, used, some pre-trained models in vision and some pre-trained models in language to come up with metrics. If you use those models as your backbones, you are going to basically get higher scores because you are, if you, in a sense, cheat and you optimize the metric using the model that was used to obtain the metric, you are going to start hill climbing on that. That is an issue with these models. Good point. With these metrics, yes.
Thank you so much for the talk. My question is about the quality of the 3D objects. And I think a lot of work is showing that if you filter off reverse or similar data sets, you can improve the model if you have some type of quality metric.
Yes.
I'm wondering what your thoughts are on the necessity of that for foundational models, and also if you think eval 3D, like any of these types of metrics, to be applied to data sets like Omniverse to filter like maybe the text to 3D alignment or something like that. Like which.
Well, actually, so even though, part of the work at AI2 is in, producing large volumes of data for many different applications, I'm slowly changing my mind on this, is that if you simply scale up data without worrying too much about data quality, I think your learning is going to get much more inefficient and the resulting model isn't going to be spectacular. So I completely agree with you that figuring out the right subset of data is extremely critical. And we saw that the data quality in Observers is the data quality in Observers 1.0 is higher than the data quality in Observers XL. And that's just because, as you keep scaling up, you have more and more issues with making sure that, your data quality is high. And so filtering out and building models based on higher quality subsets is critical. And your question is, how do we start filtering out? In vision and language, in multimodal AI, datasets like Lion and datasets like Datacom started filtering out images that don't have close enough text by using clip models, right? And so it is natural to say, well, why don't we use text to 3D consistency to start filtering out assets that don't have good text descriptions? I think that is a viable method. Ideally, I would like to figure out ways to find good subsets of data without relying on closed source models to do that, because otherwise you would never know how those closed source models were built because it's a cycle. But I think to get the community started, I think that's a good option.
All right, thank you. Thank you, Annie. We have to move on to the
Yeah, I'm glad to introduce our next speaker, Rush Liu. And I think Rush is a PhD student at Columbia University, and he has done a lot of exciting work in connecting foundation models with 3D. For example, he's the lead author of the work 0123, which has also been mentioned a few times in Annie's talk. And today, the title of Rush's talk is 3D Foundation Models for Physical Intelligence. And let's welcome Rush. And yeah, please go ahead.
All right, thank you very much. Thank you very much for the kind introduction and the invitation of the organizers. So today I want to talk about a topic I'm very excited about. It's 3D foundation models for physical intelligence. So the 3D foundation model has been one of the biggest topics in the past year in computer vision. And we see exciting papers and progress coming out on a weekly or even daily basis. However, to me, 3D foundation, the word means that it's a foundation of 3D or spatial applications in the virtual world are today's landscape in research in this space. So I want to talk a little bit about the space that's kind of being ignored by the community, which is the physical world. How do we apply 3D foundation models in the physical world? So in today's talk, I want to basically break this down into 3 parts. I want to talk about 3D foundation model for physical interaction, physical design, and physical reconstruction. So let's start with the 3D foundation model. So if we look at the history of progress of 2D generative models, we can see that the data set has been the unseen hero behind all the progress, even though we have better and better generative architectures. But these are built upon foundation, like the progress of data sets. These data sets become higher quality, more diversity, and just larger in quantity. So on the 3D side, as Annie just mentioned, we introduced Objaverse XL last year. And it was a pretty big success. A lot of work was built upon it. It was a great collaboration between multiple institutions. So to put things in perspective, this is everything else. I don't know if Annie has shown this chart before, but this is the scale of 3D data sets. Objaverse XL is significantly larger than any other 3D data sets or everything else combined actually for Objaverse. And we expect to see more exciting works coming out in the future that base their efforts on top of Objaverse. However, to me, there's always a question, is data set scaling enough for 3D generation or 3D foundation models? So if we put things in perspective, when we compare 2D and 3D data, right? So 3D data, Objaverse XL was the biggest data set release. It has 10 million assets, but it's still not comparable, right? Still orders of magnitude smaller than the biggest 2D data sets, which is lying on 5 billion. So I think we need a bridge to channel the knowledge from 2D images to 3D, which I believe is what 0123 represents. So 0123, as many of you know, is a novel view synthesis method that generates a novel view conditioned on an input view of an object as well as a specified camera transformation matrix. It is similar to Stable Diffusion. We actually fine-tune from Stable Diffusion, which is a conditional generative model. And we just fine-tune it on a lot of 3D renderings from Objaverse and Objaverse XL. And it's able to show very impressive generalization abilities, such that it works on impressionist paintings, works on oil paintings, works on cartoons, line drawings, and even sketches. All of these are traditionally very hard for classical 3D reconstruction or novel view synthesis method to operate on. So we've talked a little bit about channeling knowledge from 2D to 3D, which is kind of what 0123 is to me. What about robotics? You know, robotics is a field where data is even more limited. It's even more expensive to collect robotic data than 3D models. So that brings me to the second part of my talk. How do we use 3D foundation models or generative models in general to help physical interactions? So in robotics, there's a dilemma of robot and visual data. So on one side, we have robot data, which is kind of limited because they are very expensive to collect, but they're very useful for robots. The skills learned from the robot demonstration data can be directly deployed on robots, and they function pretty well. However, on the other side, we have the ocean of internet visual data, which could contain a dog running, a person folding clothes, person cleaning dishes, which are all very useful for teaching robots about physical interaction, but they're not well aligned with robots. So they're very diverse, but there's a big embodiment gap because we cannot extract explicit robot actions from these data. And a lot of companies like Google and Meta train foundation models from internet visual data. So the question is, how do we bridge the gap? How do we use the super diverse, large quantity internet visual data to help robot learn better to operate in the wild environments? So for that, we introduced DrRobot, which stands for differentiable rendering of robots. So given a pose, differentiable rendering DrRobot can generate a geometry or appearance of a robot under that pose, which is represented by a 3D Gaussian splattings. And from sampling a camera perspective, you can render an image from this model, and the gradients on the pixels of this image can be backpropagated into the control space of the robot. And this could be used for optimization purposes. So essentially, DrRobot allows visual appearance of robots to be differentiable with respect to its control parameters. Okay, so given a robot pose, DrRobot can generate a 3D body of a robot, render an image, and this image can be passed into visual foundation models such as CLIP or text-to-video models. And the control signal from these models can be backpropagated directly into the control space of the robot. So I want to draw the connection with 3D generation here, which some of us are more familiar with. The classic work, Dream Fusion, was the optimization of a nerve using text-to-image model, which is a visual foundation model, which is kind of equivalent to what DrRobot is. DrRobot is essentially a 3D representation for robot that is differentiable. And you can interface that with various sort of visual foundation models. So to me, it's basically 3D Jamba for robot. Before I go into applications of DrRobot, I want to talk a little bit about how we achieve the differentiability of the rendering function. So from a robot pose P, we could first pass into forward kinematics, which is a differentiable operation to get the skeleton of the robot. And then we could use an implicit linear blend skinning function, which is commonly used in graphics, to project the 3D Gaussians from a canonical robot pose into a posed Gaussian spreading. But this will kind of mess up the appearance of the Gaussians if you just directly project them. So we use an appearance deformation function to adjust the spherical harmonics, scaling, opacity, rotation, these coefficients of the 3 Gaussians to improve the visual quality of the final robot. And this whole pipeline is trained end-to-end by optimizing the L2 loss between the rendering and the ground truth image. So after we train this model, we could use it for a lot of different applications. For example, here, we use DrRobot to estimate the robot pose and reconstruct the robot action sequence from just a single image or a video by just doing analysis by synthesis, optimizing for the difference between the rendering and the observation. And here shows the results of reconstruction. So the video on the left is the only input to our model. We don't have access to the controller. And we're able to basically re-render the robot in very, very similar pose that outperforms all the previous state-of-the-art models on this problem. We could also use it for planning of the robot actions or control. So here shows an example of we using DrRobot for visual model predictive control with a CLIP model. We could basically input the rendering of a robot model into a CLIP and to optimize in the pose space of the robot for the CLIP similarity between the rendering and the text prompt. And here shows an example. We're optimizing for a shadow hand pose towards the prompt, which is a victory sign. And through the end of the optimization cycle of about 200 iterations, we obtain a shadow hand doing victory sign. Note that if you use traditional gradient-free optimization algorithms such as reinforcement learning, it will take a lot longer time. It will be a lot less efficient. So that's the benefits of having gradients. We could also use Dr. Robot to connect with a text-to-video model for robot control. So here, we fine-tune stable video diffusion on the ASU tabletop dataset from OpenX embodiment. We can prompt the model with a language prompt, pick up the BlueCAN or pick up the RepLog. And our fine-tuned video model would basically generate a plan of a video doing that. And then we could use Dr. Robot to reconstruct those poses because the generated robot does not have a robot pose. Dr. Robot can help you with that. We could also do motion retargeting with Dr. Robot. By here, we use a point tracker, which is code tracker from Meta. We could transfer motion from my hand here, doing a thumbs up sign, by optimizing for the transfer distance between the point tracks in the robot hand and my hand, to transfer the motion from a human hand to a robot hand through pure optimization. Right. This is all of these applications are possible because we have gradients provided by Dr. Robot. So I talked a little bit about optimization, differentiable rendering as a as a bridge between visual data and robot control. What about policy learning? Right. For that, before going into detail, I want to introduce a little bit of context in robotics. A visual motor policy means given an observation of a tabletop scene, a visual motor policy basically needs to output a sequence of motor actions that can be executed on the robot to complete a task. For example, in this video, the robot is scooping the MM beans from one bowl to another empty bowl on the desk. And behavior cloning is the second concept, which has been one of the biggest trends in robotics in recent years. There's a lot of breakthrough in behavior cloning. What it is essentially, to me, supervised learning of human behavior. So for behavior cloning, we basically collect a lot of observation and their corresponding expert demonstrations for this task, for various tasks potentially. And you essentially train a supervised learning model, which is the visual motor policy, to imitate human behavior in these demonstration data. So we want to introduce an alternative way to do visual motor policy. The novel way to do it is use video generation as an intermediate action representation. So given an observation of the same image of the tabletop scene we just showed, we could prompt a video generative model conditioned on a tool. The video generative models could generate a sequence of trajectories describing the plan of a human holding that tool to solve that task. And with 3D tracking, we could track the 6-stop location of the tool from the generated video. And we could execute that on a robot by just following the 3D trajectories. So essentially, at a high level, we break down visual motor policy into dream and imitate, or dreamitate as we call it. So in dream, we generate a human holding a tool doing the task. And in imitate, we have a robot following the trajectories shown by the human in the generated video to solve the task. However, there's one problem left because we are using video model here. Even though they're amazing, they're OpenAI Sora and Luma Dream Machine, but they're not well aligned with robot. If you directly prompt the image, it's not going to work. There's some issue, there's some alignment issue to align video model with robots. So we built a system to basically perform alignment. Here we have our physical setup where we have a 2 top-mounted stereo camera to collect a human holding a tool, perform a demonstration task from 2 different perspectives at the same time. And after we have a couple hundreds of these demonstration video, we could fine-tune the video model to generate a plan, essentially, of doing that task from 2 different perspectives. After we fine-tune this video diffusion model, we could replace the human with a robot using the same camera setup and just prompt a video generative model to generate a plan of a human holding the tool, solving the task. And we can basically track the tools in this generated video. And we have a robot to follow that trajectory to complete the task. So we evaluate this framework on 4 different tasks. And the first task we evaluate on is rotation. So here's a sample generation of our video generative models for rotating an object on the table for 60 degrees. And know that all of the objects being rotated are unseen in the demonstration data set. So it's completely generalized. So here it shows the Dreamity controls the actual robot rotating the objects on the table. And note that some of the objects has very challenging geometry, and it's not that easy to rotate them in a very robust way. And the second task, we focus more on the tracking, 3D tracking accuracy of the tool, the scooping task. If they're jittering in the 3D generation, the 3D tracking, or the video generated video have a lower quality, or the spoon deformed, that could cause noise, and that will cause failure of this example. And as you can see that our robot is able to scoop granular media from one bowl to the empty bowl on the table. And it's important to mention that all these granular media were not seen during the training time. We use other granular media for training and use new granular media for testing. And all the target bowls, as well as distracting objects on the table, were also not seen in the training data. And we also perform a sweeping task where we sweep one particle to the target locations. And our robot is able to do that task pretty well as well. In the end, we also do a push shape task, which generalizes from the famous push T task in the diffusion policy paper. Here's a basically sample generation of our video model, solving the push shape task to a target location within a certain number of steps. And here shows the actual execution of the robot pushing a shape to their target locations. I know that these are all arbitrary shape that's unseen by the robot during the training time at the demonstration data sets. So this is pure generalization. And as you can see, diffusion policy, which does not have priors from video models, it fails to generalize to these novel geometry. Even though they could solve the pushy task very well, they could not solve the push shape task. And we show some analysis of our generalization performance of Dreamity. Here we perform ablation studies where we only train the visual motor policy with 2/3 or 1/3 of the demonstration data. And as you can see that our policy is able to save at a pretty high success rate, even with only 1/3 of the trained data set. And the diffusion policy quickly converged to near zero. So that brings me to the second part of the talk. How do we use 3D foundation models for physical design? So I want to use a task, designing paper tools, as a motivating example. So the task is essentially given a robot taking paper as material to design tools. Oh, why paper, you may wonder? Well, paper is a very attractive medium for design. They make recyclable tools, and they make very useful tools in our society, such as paper bags, paper straws, paper filters. So it is very good for our society to make more tools out of paper. And I want to motivate this design problem, with a very interesting, fun design problem of learning to design a paper airplane that fly the furthest distance. So if we reflect on how us human would solve this task, we will first think of a design of a paper airplane. We will fold it physically with our hands. We will throw it out with our hand, and we will see how far it flies. And we do this iteratively as a kid to learn what kinds of design flies further, right? So the question is, can we replicate that with robots? So to do that, we could parameterize the paper airplane design. We could have robots and a couple of tools to fold them, and we could have a robot arm to throw it out. And we could have a cameras to measure how far they fly. So this is the system we built in our lab. At the beginning, it loads a paper into a folding deck, and two arms will sequentially fold the right and left wing of the paper airplane. And it will grab a holder to stick to the paper to create a grasping point, and it will throw it out. And two top-mounted RGBD cameras will measure how far it flies as a reward signal. So we've automated the manufacturing process of paper airplane with robots. How do we learn the design, right? It's a learning to design problem, not an automation problem. So we adopted an optimization framework based on Stargate-based model. So Stargate-based model is parameterized by a neural network, and its job is to learn what kind of paper airplane design flies further. So through trials and errors, basically in the real world, by folding various kinds of paper airplane in an epsilon greedy manner, it learns a pretty good model of what kinds of paper and fly further, and we could perform inverse design with the gradients. Basically optimizing for the design space to optimize for its flying distance. And here shows the visualization of our robots learning to fold paper airplanes across 100 trials. And as you can see that as it accumulates more and more experience folding paper airplanes, it designs paper airplanes that flies further and further. And at iteration 91, it obtained its best design, which flies over 20 feet or 6 meters in our lab. So we compare our method against several baselines, including SNES, which is a evolutionary algorithm, which is a very classic gradient-free non-convex optimization method. We also compare against a human participant, which is the unfortunate second author of our paper. He tried really hard, but still failed to beat our method by a little bit. I want to move on to the second task that we apply this design framework on, which is designing a practical tool of kirigami gripper. So kirigami gripper is inspired by Japanese art of kirigami, which is cutting paper. So basically, it's cutting paper into gripper that grasp objects. And these are very useful for grasping delicate objects, such as fruit or food. So prior work on a kirigami gripper design relies heavily on physical analysis by studying the mechanical deformation process of the paper during its actuation process. This is very time-consuming and expensive. So we applied our automated design framework that we apply to paper airplane design to the kirigami design without changing pretty much everything, including the hyperparameters. So we basically automate this process with design, build, actuate, and perceive. And to do that, we build a physical system, have basically automate the manufacturing process of the kirigami gripper by using two arms as well as a Cricut maker machine. So I didn't know this exists before this research. I was trying to use a laser cutter to cut paper. But I discovered that Cricut maker machine is a much safer option if you want to interact the machine with the robot arms. So you don't knock off the laser cut and it shoots into your eyes. So Cricut Maker 3 basically efficiently cut paper into certain shapes very fast. And we also use two load cells to measure the horizontal gripping force of the gripper as a reward signal. So apply the same optimization learning framework. As you can see that across 100 trials, our method is able to find a very good paper gripper design that exerts much higher forces than other methods. So at the end of the optimization cycle, we obtain a gripper design that's able to exert 0.93 Newton of force, which is equivalent to the weight of 4.5 strawberries. And here's a video of our design gripper grasping a strawberry. And here's examples of our design gripper grasping various objects we can find in our lab, including big objects and small objects, as you can see. And please find more details in paperbot.scs.com, which is our website. And as a disclaimer, we recycle all the paper used in the experiments. So this is an automated design framework for tools like paper airplane. We could actually use this in real-world tool design by incorporating geometric priors from 3D generative models. So tools are basically 3D geometries. And to connect the virtual and the physical world, we basically need a 3D printer. And with this manufacturing pipeline, we can basically search in the latent space of a generative model to find a tool that is useful for us. And this could actually use the imagination abilities of the 3D foundation models. But there's a problem, which is 3D printing is kind of slow. It takes like 15 minutes to half an hour to print something reasonable. So we might need a farm of 3D printer for this to accelerate the design process, which makes it a little bit expensive. So that's why I haven't convinced my advisor to pay for it yet. So if there are industry funders in the audience, please contact me during the conference. I personally believe that this design framework could lead to marvelous tools that beyond human imagination, given enough resources. So finally, I want to talk about 3D generation for physical reconstruction. Specifically, we studied the task of 3D reconstruction of an occluded human behind this car. So we know that there's a boy that's running out of the car behind this vehicle, and we cannot see it completely. So none of the computer vision algorithms of human detection works. But it's an important problem, to detect this kind of scenarios and detect where the body, where the boy is and what is his body pose to avoid car accidents, right? So there would be one possibility if the car in the front turned into a mirror. So we can see the reflection of the boy in the car in the front. Then we can see the boy, and we could use that information to reason the 3D location of the boy and even body pose. So it turns out that this is exactly the case in thermal cameras, which operates in the infrared light spectrum. So here's a side-by-side comparison of the same car, same view, between a normal camera and a thermal camera. And I was basically walking in front of the car behind the camera. So you can see that there's no reflection in the normal camera, but there's a very clear reflection in the thermal camera. So where does this reflection come from, and how can we use it to reconstruct 3D human? So this is related to black body radiation in physics, which basically says that every object beyond absolute 0 Kelvin degrees emits thermal radiations. And as object gets hotter, they emit radiations with shorter wavelength, which is why when you heat up an iron, it emits visible light, and as it cools down, it doesn't emit visible light anymore. So with a constant body temperature of 37 degrees Celsius, human emits very long wavelength infrared light with a wavelength of about 9.5 microns, which is more than 10 times longer than the longest wavelength visible light, which is why we don't see human glowing in our everyday environment with our visible eyes. But with a thermal camera like this, which is very small, but still kind of expensive, you can see human glowing in everyday environment. And here's my roommate dancing in front of the camera. So you can see when you turn off the light in a normal camera, you don't see him at all because a human body is reflector of environment light in our everyday environment. But in thermal camera, they're light source, right? Humans are infrared light bulbs, essentially. So you can see them even when you turn off the light. And cats are also infrared light bulbs. And this is my cat. And many objects, because the wavelength of the light is longer, they tend to specular reflect instead of diffuse in many surfaces. So that makes a lot of objects more reflective, much more reflective actually in the infrared light. So here's a glass which is fully transparent in the normal camera, but it's reflective in the thermal camera. And here's a side-by-side comparison with the whiteboard. There's no reflection in the normal camera, but there's a very clear reflection of my body in the thermal camera. So with this observation, we propose a method based on analysis by synthesis to solve this reconstruction problem. To do that, we basically use 3D foundation models, generative models, such as object generative models and human generative models. So sampling from a latent space of these generative models, we could initialize some object geometry and their location and orientation of both the objects and human. So it would be wrong, but it will be initialization. And from this initial gas, we could write down the differentiable rendering function of the reflection of human thermal radiation reflected off of an object that goes into a thermal camera. So we could, oh, hello?
Oh, yeah, it doesn't work for some. Sorry.
Okay, can I use the mic?
Yeah, maybe I guess maybe you should.
Okay. Okay, great. Yeah, so after we differentially render this image, we can optimize it towards the actual observation of the thermal camera. And at the end of the optimization cycle, we basically obtain a 3D reconstruction of both the object as well as the human body and their orientation and location. So to go in a little bit more details about how we differentiate, how do we do differential rendering of reflections, right? So differential rendering, if you don't have any light balances, is rasterization. You could solve that with rasterization. But if you have reflection, then the light path become intractable, and you have to use differentiable ray tracing. So basically adapt the soft rasterizer framework for differentiable ray tracing. So for the light starting from a triangle from the human body model, which is SMPL, reflected off of the surface represented by a DeepSCF model. And with DeepSCF, in a surface vicinity, you can sample points and you can take derivative to get the surface normal of the SCF function. And we also have the thermal camera in the scene, right? So differentiable ray tracing starts the ray from the thermal camera sensor, reflected off of the object surfaces with sphere tracing, and arrive the human body. So this process is fully differentiable because we have every components of this are differentiable. So with this function, we could basically perform optimization and try to reconstruct both human and object in the scene. And here show some results. This is the input single view image of various scenes, basically various objects such as cars and bowls and mugs that reflect human thermal radiations in the environment. And in the view, you don't see any human. And here is the thermal image of the same view of those objects, and you see myself in the view. And we are able to, with these information, reconstruct both the car geometry as well as the human geometry that is consistent with the ground truth scene captured from another camera's perspective. It's not perfect. You can see that there's some detailed body pose still missing because we're operating at a single view of a reflection of a human in an object. It's kind of small also. If you have some curvature, it makes the human pretty small. So there's a lot of noise in this process. And sometimes you may need to initialize multiple random seeds to pick the best one to get good results. But it is something. You could get the rough body pose of the human correctly and the object geometry as well. So that summarizes my talk today. I talked a little bit about our work in 3D generation or 3D foundation models, and several work that's inspired by 3D foundation models on physical interaction, physical design, and physical reconstruction. So for that, I want to thank all my collaborators, my advisors, and my collaborating institutions. And here are the references to all the papers. And I'm happy to take questions. Thank you very much.
Thank you, Rushi. We are a little over time, but maybe let's take one question from the audience.
Yes. What simulation?
Yeah, well, for example, you can use the robots to create like the paper, create some the cranes or something. Using some differentiable methods. Yeah.
So is the question, can we use differentiable simulation to design paper airplane? Oh.
It's a background. So yeah. How about the friends? That does for something. For example, you put the materials or for your friends or something. Sometimes there are some damages. You need to use something to repair it. But when we repair it, it's very hard to control the for example, for humans or the robots, it's hard to control it to control it to a very smooth surface or something. So in this case, so do you think, yeah, it's possible, for example, we use the multi-view images because it provides some geometry information inside it, and then we can use this as a single vision with the gradient vectorization or some kind of method to then also sometimes we have the simulator, we can control the robot and we can get controlling all the signals. Yeah,
I see. So I guess the question, I guess a little bit complicated question is, can we use multi-view supervision and 3D knowledge to help preparing a tool such as paper airplane? I haven't thought about that. I think it's possible. Like our design framework doesn't really reason the 3D yet. The focus is more on real-world tool design. So I think there are many dimensions this could be extended towards. But I think you mentioned simulation. This might be not super related, but I think as simulation, we actually picked the paper airplane design task specifically because this is pretty much an impossible task to simulate. So the paper is thin shell object, which is notoriously hard to simulate, and they're also deformable. And when you fly them out, they interact with fluids. So there's fluid dynamics. So they're basically interaction between fluid and deformable objects, deformable thin shell objects, which will be nightmare for simulation if you want to build a simulation. So we actually wanted to build a simulation baseline for this task, but we kind of gave up after a while. So I think that's a good example of why we need real-world tool design. And I think in real world, a lot of these priors, such as 3D, could be helpful, but we haven't done it yet, so we will leave it to future work. I think you also mentioned differentiable physics. I think there are a lot of progress in differentiable simulation nowadays, and we introduced a framework to do differentiable robot rendering, which is on the appearance side, but it doesn't consider physics in these robots. So I think incorporating these frameworks together, combining them, you could potentially reason the physics, basically the interaction itself, as well as the appearance with visual foundation models. I think all of these are great solutions for future manipulation tasks. Yeah, thank you for the question.
All right, thank you. Let's thank the speaker again. And we'll take a short break and come back at 10:15 in 5 minutes. Thank you. Let's talk.
Thank you. Thank you.
We were talking about.
All right, work.
No, I didn't.
All right. Thank you everyone for coming, and we're about to start to continue our next talk. And it's my pleasure to introduce our next speakers, Dr. Peter Wanka and Dr. Biao Zhang. And Peter is a full professor in computer science at King Abdullah University of Science and Technology. And he's also the interim director of the Visual Computer Center. Previously, he was also a postdoc researcher at Georgia Institute of Technology and also a faculty at Arizona State University. I think Peter is really a distinguished researcher working in the field for more than 20 years and has done a lot of work in procedural modeling, urban reconstruction, and data estimation, and a lot of other fields. And Dr. Biao Zhang is a postdoc researcher working with Peter in his lab. And Biao also has done, I think, a lot of pioneering work in generalizable 3D representations and 3D generative models. And today, they will be giving this talk towards training large 3D generative models. Yeah, let's welcome Peter and Biao, and please go ahead. Thank you.
All right, thanks a lot for the introduction. So we're going to make a lot of broader comments, just looking maybe at what we've heard the last few days. And we'll also talk about some specific work, but we'll try to answer some of the questions that this workshop posed. First off, it is true, I'm one of the oldest here, I guess. And one thing to notice up front, this is an incredibly exciting area. And for having been in research so long, it's really, you guys are extremely lucky that there's like so much excitement and so much progress in a topic. I mean, this is really, really rare in research that you can see this insane progress from 2D GANs, and then you have large language models, 3D generation. These things have probably been considered unthinkable, video generation, all of that. So now we'll look at what we've heard the last few years, or seen the last few years, and we will structure the space into 4 categories of 3D generative models. And the first generative model style, I would call it EG3D style modeling, and we call it generation with differentiable rendering. And so what is really great here is that there is no need for a 3D training data, and you only need some multi-view supervision. But there's a fundamental weakness, and I will show that or bring that up also in context of other works. If, let's still assume you have the perfect images captured around an object, how great will the 3D reconstruction really look like? And the answer is, if you know NeRF and Gaussian splatting, the reconstruction will look really great. But how great is the underlying quality of the geometry? And here, my conjecture is, this is not really that great. And NeRF and 3D Gaussian splatting lets the network cheat a bit to put information near the surface to look like the object, which it does a great job of, but it doesn't really tell you where exactly the surface is. So we will call this here noisy geometry, which is more this part on the right, if you then look at the geometry of what is generated. Now, this is a really promising area, but this hasn't great success. There's relatively great success, of course, but we don't see the winning models in this category now. Maybe it comes back, but this is not where the main investment is at the moment. Then category 2, generation with score distillation sampling, extremely influential paper to Infusion, and building on that, no need for 3D training data. but the weaknesses is slow. Maybe there's the Janus problem we've heard about so much. And again, there's noisy geometry. Again, if you want to do betting, this is not where the main excitement is at the moment, what you heard the last few weeks. Third category, generation with multi-view diffusion. We will take a 2D model, and we will either generate multi-view images or videos, and then we can run a 3D reconstruction on the multi-view images or the video. So this seems to be what everybody is betting on. So you see the top models, again, maybe I'm oversimplifying, but the top models from Google, Facebook, Snap, Luma, maybe, I don't know. They are in this area. And so citing, I don't know if he copied it, but citing my one of my collaborators, Sergey from Snap, he posed the question, does the lead to the valley of 2D? And it seems, if you want to go with bets, that everybody's betting on this. We need to do multi-view, or we need to do video, and then we go back to 3D. So there is amazing work, such as CAD 3D, again, insane high quality. And also, if you've seen the talk yesterday, Meta's 3D Gen, I don't know if it's out yet, amazing, or some talk early in the morning, Odin. These people are betting multi-view video. So strength, Janus free, fast inference, but you do need this required multi-view video data set, but there will be multi-view inconsistencies. And you need to have some skill to do 3D reconstruction from inconsistent images. And there is the additional issue as well. What is there with the material information? So if you see Meta 3D Gen, I think maybe the first really great progress in this direction. I would still pose the question, I mean, how great are the materials really in the end? Now, the other question, though, is, and you've seen the same slide many, many times, right? There's 5 billion images from Leon and only 10 million observers 3D, so we kind of forced to train on images and videos. But do we actually, can we really benefit from it? Because it is true that there's so many images and videos, but don't we really need annotated images that have the exact correct viewpoint, or do we need like videos annotated with where exactly the camera is, and how great are these models really in being multi-view consistent? And I would say it's the leader in the race right now, probably by quite a bit, but there are these inherent issues that is not so clear how it's going to go. So maybe the one guy from Luma, I don't know if I'm allowed to quote this. My impression was that he would say, yes, the path from to 3D goes through 2D, but we are not there yet. So they seem to strategically shift to doing videos first before they'll kind of see when the time is to go back to high quality 3D. Now the last one is generating with native 3D geometry. Let's just take observers Excel, train on that, fast inference. You have geometry, texture, materials disentangled, no pre-trained models needed. Theoretically, it has the best geometry quality. I mean, you can argue that there's this trade-off. Maybe it doesn't have enough data, so geometry quality is not that great, but let's say equal amount of data, we would expect this to have the best geometry quality. But we do need very large data sets. And in some sense, there was this quest for an efficient representation. All right. So again, because that's what we happen to have done, we will advertise this as it does still make sense, even though you'll see a lot of people betting on the previous category. It still makes sense to go down this category because eventually, if you want to use assets for games or 3D, it is not clear that you will win with this multi-view. So we believe the high geometry quality will still be in this category. Now, finding an efficient representation, there's many classical 3D representations, and you know, such as voxel point clouds, meshes, signed distance fields, and then these combinations that are very popular in deep learning, there's dense grids together with some other field on top, or sparse grids, or factorized grids. So in general, to find an efficient representation, you want to have quality. It needs to be able to represent each object well with details. So for example, the chair on the right, you want to see you want to have the structure preserved. It should be compact, also an argument made in language models. The more compact, the better. And there's some flexibility required. So in one of the most favorite works out of our lab is something that Biao was spearheading, is the idea how to find an efficient representation. And if you look at a lot of the representations, it's kind of this coefficient times basis function. So if you look, for example, at kernel regression, you have coefficient times basis functions, but the basis function is somewhat spatial. So the Gaussian X something is the basis function, and Fi is kind of the feature. Or you have maybe for Fourier series, again, you have a coefficient and the fixed basis function that doesn't have it is a predefined spatial location. Now, my philosophy in someone, again, I don't know if I'm allowed to say that, but my philosophy is one, the network hates points. So whenever you use points with a network, you have a drastic decrease in quality. And the network doesn't like if you help it with spatial data. So the representation that we propose gives the network the option to, you know, put spatial data into the feature vectors if it wants to, but it's not forced to, and we're not helping it in any way how to do it. So what that ends up with, we just have feature vectors, and we keep this attention of a query point, and, you know, again, this is we kind of use the transformer architecture, and K of Fi, the feature, mimics this kind of spatial basis function if the network wants to use it this way, and then times V of Fi, which is kind of the coefficient. So we give the network the option to do it spatially if it wants to, but it doesn't have to. All right. Yeah.
Okay. Hi. So I will continue this representation. Okay. So for our proposed representation, we call this vector set, and we also propose a network which takes a surface as input and output a field. So we can use any isosurface extraction algorithm, such as Martin cubes, to get polygonal meshes. So this network is a pure transformer-based network. So in recent years, people found that transformers have very good scaling ability compared to convolutional networks. So which means that there's a great potential to scale up the network to large datasets. So, and as we discussed before, the important thing in the property of the efficient representation is the geometry quality. And we proved that we can use this vector representation to preserve very detailed structures, which is shown in the right of these slides. Okay, so training a diffusion model with our vector set representation is straightforward. We can use a very simple transformer as the denoising network in diffusion, and we can easily make it unconditional or conditional. And so this supports many kinds of condition modality. Okay, and this paper DIT is kind of popular recently because of the OpenAI Sora, because it has been used, and it has also been used in several large diffusion models recently. And since the release dates of the two papers are very close, so when we put our paper on the cap, we do not know the paper DIT. And so we actually use a very simple transformer as a denoising network. But now we can directly combine the DIT network with our vector set representation in different when we're training the diffusion models. Okay. And in these slides, we introduce some papers which use this vector set representation in generative models. Most of the papers are finished by other researchers, so we will introduce them one by one. Okay, and so this paper is accepted to New Reach 2023, and the authors basically use this vector representation as a main backbone. And so the authors also introduce a click embedding for semantics, and this model is trained on NopJavers, so which is a huge dataset compared to SheepNet. And we can use this model for text to 3D generation and image to 3D generation. And this motion to vector paper is accepted to CPR this year. And the authors basically applied this vector representation to 4D data. So these 4D dynamics are parameterized by latent vector sets. We can use this vector set to include both the shape and the deformation patterns. And this also proves that this vector set representation is also very useful for other high-dimensional datasets. Okay, this the 3D paper is accepted to CPR this year, which is also an oral paper, and congratulations to the authors. This image is a teaser figure from this paper. In the left, they show the generative results from our vector paper, and in the right, they show the results obtained using GPID 3D. From the quality, we can see that there is a large improvement. So they basically combine this geometry and physical priors when we are doing generation. And the idea is also very simple. They used a quality checker that outputs a score of the latent code to obtain the improved results. They need the pre-trained model from our vector paper. Thus, they do not need highway training to have this performance gain, which is very interesting. Gem3D, this paper is accepted to SIGGRAPH 2024 this year. The authors combine the vector representation with skeleton-based representation. And as a result, the paper is especially suitable for 3D objects with very thin structures, like this chair shown in this figure. Okay, Clay, the paper is accepted to SIGGRAPH Journal Track this year. They basically used our vector network for 3D representation. Since this paper is not released yet, so if the audience is interested in this work, maybe you can check Rodin, which is a product-ready 3D generative model. And Rodin is based on this Clay paper. Functional diffusion. Okay, so this functional diffusion paper is from us, accepted to CPR this year. So in prior works, we often need to compress a SanDisk function or occupancy function to a latent space. Then we train a generative model in the latent space. Since these two stages are trained separately, so this is not end-to-end training and could cause problems in 3D domain sometimes. So we often need a lot of effort to design this autoencoder to find a useful latent space for generative models. And functions are generally infinitely dimensional vectors, which are not compatible with the current diffusion architecture. So in this paper, we asked one question: can we somehow combine the two stages into one? So we can make the diffusion training end-to-end. And as a result, we can generate infinity dimensional functions directly without using this two-stage training. We do not need to do representation learning and then train the general model in the latent space. Okay, so here we show the generating process in the left figure, and we only need a few time steps to get these 3D objects. Since our goal is to generate continuous functions, we can query the generated function with any coordinates in the space. So in the right, we show how the arbitrary queries look like. So and also, since SDF SanDisk function is a function which satisfies a partial differential equation, which is shown above. And so we are actually generating solutions to partial differential equations. And this makes things even more interesting because it means that we can do general function generation And this might be very useful in the field of AI for science. Okay, so we introduce all these extensions, and if the audience is interested in any of these papers, maybe you can check their project pages. So as a summary, there are many ways to generate 3D objects, and there are strengths and weaknesses. So Peter just talked about these, the properties of these general models. Among all these approaches, we believe the native 3D geometry, which is the last category of the four ways. The native 3D geometry generation is the key in 3D general models if you want to get high quality 3D objects. And we keep exploring in this field. Okay, and here are some of our works on 3D representations and generative models. And we also have a paper to present in this CPR this year, which is on June 19th, tomorrow morning. And we can have a discussion about 3D generative models. And thank you.
Thank you, Peter and Bill. And I think we have time for questions. Okay, maybe I'll ask Glenn first. So it's very cool to have the representation like Chip2Vec sets. And I just wonder if you guys think about extending to scene representations and like just beyond objects.
Sorry, what do you mean?
Extend to scenes.
Extend to represent scenes.
Yes, we think about this, but so for the current moment, we do not have lots of data set for 3D scenes, so this is kind of difficult, and it's kind of difficult to test if the representation can be used for scene level data sets. But from our experience, we should see this is definitely possible. We just need to increase the number of the vectors in the latent set.
Okay.
Awesome. First, have you thought about like sort of the space between Gen 3 and 4 where you use multi-views, but also use more direct generation to get unseen parts? Because I feel like there's so much signal out there for what we could visually see from video and image generation models, but like there's always like internal structures and other types of components that we'll never get or be very difficult to get with the sort of multi-view setup or arrangement generation.
I would possibly say that's a good gap. We didn't do it yet, but I know some people that thought about it. But I think there is no like very good model. That's a great topic, actually.
Thank you for the great talk. I have a question regarding so I really like the way you categorize like 4 generation of 3D generative AI. And what do you think, like most of generative AI so far is applied only to object-centric data. And what do you think about going beyond that? Because it's very convenient to have multi-view for object-centric use cases, but what if you want to do more?
Yeah, I mean, I think you've seen the video models, video to 3D scenes in the morning, and I think most likely to me this will produce the first results. I don't know if this will be the best in the end, but probably this will be the first significant results in that area.
You learn it jointly, or do you first learn the representation and perform? So what would you do?
When you're saying the learning them jointly, you mean so
I first learned the autoencoder.
Oh yes, so this is a two-stage training. It's kind of similar to the paper Stable Diffusion. So we need to train the autoencoder first, and we freeze this autoencoder And so we basically have a latent space of the 3D models, and then we train the different models in the latent space.
Too poor. Well, we're too poor. But I would think, again, if you see what most people are betting on, it seems that more people are betting on the latent diffusion model where they train the autoencoder first, like in the video models, and then in contrast to the upsampling type of approaches. I mean, again, I would think that's the trend at the moment.
I think my question is that, yeah, super thanks for the nice talk, and I really like I'm very impressed for the exploration on the continuum side. And my question is that I found that the method is actually quite generalizable. I mean, I did not say that it explicitly use the trial of the 3D. I mean, that have you considered that trying to extend this kind of method to other type of data? For example, for video, you can just consider it's kind of also 3D data, that the dimensions is not XYZ, but XYT. So I just wonder whether this method are also applicable to the other types of data. So if not, maybe I want to understand what's the difference between the data characteristics.
Okay, so our initial goal was to compress the latent space to have a very small dimensionality, so it can be used for we can train the different model very easily. And if the latent space is very large, like a very dense volume, so this can be very difficult. Regarding your questions, you mentioned this video data set. I think this is definitely possible. But for the current moment, we do not have that kind of resources to do video different model. We maybe for the future when we have really lots of GPUs, and that's it.
So, but maybe one small correction. So we do also bet on the other category. So and I have been collaborating on an effort to do for the like dynamic 3D objects from videos, basically, multi-view videos.
Thank you. I guess we need to move on to the next. Yeah, let's thank the speakers again. That's very nice.
Okay, yeah. So our next speaker is Minghua Liu from University of California, San Diego. Minghua is a PhD student in UCSD working with Professor Hao Su. And I think Minghua also done a lot of great work in the space of 3D generating models and 3D foundation models. For example, the work 12345 and others trying to extend the data set of Observerse to do many amazing foundation things. And today, the talk Minghua is giving is understanding and generating 3D objects in the open world. And yeah, like thank Minghua for joining us, and please go ahead.
Yeah, sure.
Welcome.
And thanks, Zhejiang, for the introduction. So hello, everyone. I'm Minghua Liu, and I'm currently a final year PhD student at UC San Diego. So today I'm gonna present understanding and generating 3D objects in an open world. So when I started my PhD, 3D deep learning was still in its very early stages. So researchers have designed various deep learning approaches or techniques to consume and generate different 3D representations and enable various 3D vision tasks in a supervised learning fashion. However, at that time, public 3D datasets are often very limited in size. As a result, many of previous research has focused on a very limited range of object categories, with trails being the most commonly used and showcase categories. Sometimes my friends will just come and jokingly ask, Minghua, are you doing trail research again? So however, things have changed over the past 2 years. On the one hand, large-scale 3D datasets have emerged, covering much more diverse range of object categories. On the other hand, we have observed the remarkable success of various pre-trained large language models, VLMs, and 2D diffusion models. So these models have been pre-trained on large-scale text and 2D image data and can provide valuable props for our 3D learning tasks. So therefore, we now have much more new opportunities to empower our previous trail research with the open world capabilities. And we can now in this room to envision the future of 3D foundation models. So what should a 3D foundation model achieve? I think there are two important capabilities. The first one is that we want an intelligent agent to understand the 3D objects around us, including their semantics, structure, mobility, and functionality. Second, the ability to generate 3D objects is also very important, as it allows us to build a digital twin of our 3D world. So this capability enables many downstream applications, such as training agents in a simulated environment. So in my today's talk, I'd like to introduce some of my recent efforts in improving the open world capabilities for both the 3D generation and the 3D understanding tasks. So let's get started with the 3D generation part. So over the past 2 years, 3D AIGC is really a hot topic, with many exciting works emerging and that covers a wide range of approaches and paradigms. And about 1 year ago, 3D native generating models and per-shape optimization with SDS-like losses were the two most popular paradigms. However, each of them may have their own limitations. For example, the 3D native generating models trained with 3D data only may deliver high-quality data in a very quickly way. However, they often have very poor generalizability and can only handle a very limited object categories. Also, it's very tricky for this kind of 3D native generating models to handle the mesh textures directly, since we do not have many high-quality 3D data with fine-grained, high-quality mesh textures. On the other hand, many works leverage the 2D diffusion models and the SDS-like losses to perform per-shape optimization. So these methods have demonstrated strong open-world capabilities, but are typically very slow and face challenges in generating consistent 3D results. So faced with the limitations of the existing paradigms, it is very natural to ask, can we leverage their strengths while overcoming their limitations at the same time? So which means, on the one hand, we aim to utilize the rich priors embedded in 2D diffusion models to enhance our imagination capabilities. On the other hand, can we also utilize sophisticated 3D reconstruction and generation techniques to achieve fast generation speeds and consistent 3D results? So in our work 12345, we propose combining multiple prediction using 2D diffusion model and feed-forward based 3D reconstruction. So specifically, we leverage 0, 1, 2, 3 to predict multi-view images, and then lift them to 3D through a 3D generalizable nerve mode. For the first time, we achieve open world single image to 3D object generation in just 45 seconds. Compared to SDS loss and SDS-based methods, we also observe much better 3D consistency. However, for 1205 and this kind of new paradigm, one of the main bottlenecks limiting the quality is the inconsistent multi-view predictions. So which means the multi-view images predicted by the 2D diffusion models may not be always perfect. There could be some small inconsistencies and some pose errors across different views. However, these small errors can be very problematic when we come to the reconstruction phase. So to address this issue, on the one hand, we may need more consistent multi-view predictions. On the other hand, we may also want a more robust 3D lifting model that can tolerate the small inconsistencies or pose errors among the different predicted views. So therefore, in 1205++, we propose a more robust single image to 3D pipeline by introducing a consistent multi-view generation and multi-view conditioned 3D diffusion. So specifically, instead of predicting each view separately, we fine-tune 2D diffusion models to simultaneously predict consistent multi-view images. So this is achieved by turning a set of 6 view images into a single composite one. So we then fine-tune Stable Diffusion to generate this composite image conditioned on the input reference image. So in this way, the 2D diffusion model can attend to each view during the generation process, producing more consistent results across different views. In addition, we introduced novel global conditioning and local conditioning techniques to enable the Stable Diffusion to better extract the information from the input reference view image. We also introduced a multi-view conditioned 3D native diffusion model to convert the predicted multi-view images into 3D. Unlike previous generalizable nerve methods employed by 1205, the 3D diffusion model can learn more priors and tolerate the imperfect multi-view images, making the whole pipeline more robust to the inconsistency of the predicted multi-view images. Throughout the 3D diffusion processes, the predicted multi-view images can serve as the essential guiding conditions, elevating the imagination difficulty for 3D reconstruction. So here are some results from 1205++. So the video here showcases the input images, the generated texture mesh, and their normal maps. Our method can take a single RGB image as input and generate a high-quality textured mesh in about 1 minute, achieving high fidelity to the input image. So here are more results. Actually, in the past few months, we have seen many recent works following on these 2 important directions. The first one is leveraging the 2D diffusion model to predict consistent multi-view images. And the second is training a feed-forward model to convert the sparse view images into a 3D model. So among them, the line of work known as the large reconstruction model, or LRM, has attracted a lot of attention recently. By representing the 3D shapes as triplanes, they train a large retransformer model manning with rendering loss. Although they successfully leverage the scaling loss, the training cost is typically very high, and extracting high-quality meshes from the nerve fragmentation is quite non-trivial. So do we really need over 100 high-end GPUs to train a large reconstruction model? So in our recent work, Meshformer, which focuses on learning a feed-forward-based sparse view reconstruction model, we leveraged explicit 3D priors instead of just training a black box model with rendering loss. So we found that by incorporating various types of 3D native priors into the model design, including network architecture, input guidance, supervision signal, and post-processing. So our pipeline can significantly improve on both the mesh quality and the training efficiency. So before we discuss the method details, let's take a look at some of the visual results. So Meshformer takes sparse view images as input and can deliver high quality meshes in a single feed-forward pass, which takes just a few seconds. So here we showcase the generated textured mesh and the corresponding mesh normals. As shown in the figure, Meshformer can preserve a sharp geometric details and avoid artifacts that are frequently seen when learning a nerve orientation. So our Meshformer work has not been archived yet, but it will be available soon. So here are more results. So how do we achieve that? So instead of representing 3D data as 2D plans, we propose representing 3D features in explicit 3D voxels and introduce a novel architecture that combines large-scale transformer with 3D sparse convolutions. Compared to TrackLens and pure transformer models with very little 3D native design, Meshformer leverages the explicit 3D structure of voxel features and the precise projective correspondence between each 3D voxel and the corresponding 2D multi-view features. Unlike previous work that rely on nerve-based representation in their pipeline, so we utilize the mesh representation throughout the process and train Meshformer in a unified single-stage manner by combining surface rendering with additional explicit 3D SDF supervision. Furthermore, in addition to multi-view post-RGB images, we propose using corresponding normal maps as input, which can be captured through sensors or directly estimated by using 2D vision models. So these multi-view normal images provide important clues for 3D reconstruction. We also propose to learn a normal texture in addition to the RGB texture, which can then be used to enhance the generated geometry quality through a traditional post-processing algorithm. So by incorporating these explicit 3D priors, we can train our Meshformer much more conveniently and efficiently. So specifically, Meshformer can deliver high-quality meshes and can be trained in a unified single-stage training fashion. So in addition, the model can be trained much more efficiently compared to concurrent large reconstruction model type of methods. So with just 8 H100 GPUs and 2 days of training, we can achieve on-par performance or even better performance than the concurrent methods that require more than 100 GPUs. So that's a brief introduction to 1205++ and Meshformer. So as you can see, 3D AIGC is a really highly competitive and fast-growing field. So where we have seen a significant progress in the past 2 years, unfortunately, according to the feedback from the 3D artists, they are still not satisfied with the 3D models generated by most existing AI models. So there's still much work to be done before 3D AIGC methods can be widely deployed in various real-world applications. So what's the next step? So where the approaches and or the paradigms for 3D AIGC have not yet converged, leveraging 2D diffusion models for imagination and combining various 3D techniques for faster lifting may still be a very promising direction from my perspective. So in addition to further improve the visual quality, I think there are multiple things we can consider now, such as sharper geometry, high quality PBR materials, part generation, automatic rigging, and interactive editing. So all of these are very critical components for various applications and need more attention and exploration. So that's pretty much about the 3D generation. As I mentioned, in addition to 3D generation, another important capabilities we may want a 3D foundation model to achieve is 3D understanding. So here I would like to briefly introduce some of our recent attempts in open world 3D object understanding. So the first project is called OpenShape. So in this project, we aim to extend the success of the 2D click model to the 3D domain and learn a powerful joint representation of 2D images, text, and 3D point clouds. So this will enable open world 3D shape understanding and facilitate various cross-modal applications. So as illustrated in the left figure, so our goal is to train a 3D native encoder by distilling knowledge from the pre-trained 2D click models. So the 3D native encoder takes a 3D point cloud as input and extracts 3D shape features. So these features are expected to align with the 2D pre-trained click embedding spaces for both language and images by utilizing the cross-modal contrast learning. Yeah. So in this project, we aim to develop scalable 3D representations to enable open world 3D shape understanding. So we have spent considerable effort scaling up the representation alignment and addressing the corresponding challenges. For example, we increased the scale of the 3D data training data by integrating multiple public 3D data sets. In addition, we have observed that the text quality plays a very critical role in the alignment of the feature space between 2D and 3D. So however, many of 3D shapes come with very noisy text descriptions uploaded by web users, which fail to provide accurate and useful description for the 3D models. As a result, we propose several strategies to automatically filter and enhance the text descriptions for 3D shapes. And beyond text filtering and enrichment, we also find that scaling up the 3D backbone is very crucial. And previously, most current 3D backbones are designed for small datasets such as ShapeNet. Moreover, since the training dataset is highly unbalanced, we also propose using hard negative mining to improve the training data distribution. So by incorporating all these techniques, we have finally been able to learn some powerful and scalable 3D representations. For instance, in the left figure, we showcase the results of Beal-Short 3D shape classification. So while previous methods could only support the classification of dozens of categories, our method can achieve remarkable results in Beal-Short classification across more than 1,000 categories, significantly outperforming previous methods. Our OpenShape representations also encode a broad range of semantic and visual concepts. So in the right figure, we demonstrate some results of shape interpolation. So here we input two 3D shapes and use their shape embedding to retrieve the top 3 shapes from a large 3D database. So whose embeddings are simultaneously closest to the both input shapes. So we can see many interesting results. For example, given a rocking chair and a horse, so we can retrieve shapes like a horse-shaped rocking chair or a cowboy figure sitting on a chair. For a cart and a horse, so we can retrieve a horse on a cart or a horse with wheels. Similarly, we can observe some combinations of nano-shaped shapes or egg-shaped chairs. So these results highlight the rich concepts and priors encoded in the OpenShape embeddings. The OpenShape embedding also enables multimodal 3D shape retrieval in an open world context. So this slide presents the results of text-based 3D shape retrieval. So in each row, we display the input text on the left and the two retrieved 3D shapes corresponding to each input text on the right. The OpenShift embeddings enable the retrieval of fine-grained subcategories such as shark, swordfish, dolphin, and goldfish. It also enables the control of various attributes such as color, shape, and style. In addition, it supports 3D shape retrieval based on image and point cloud inputs. So as shown in the figure, OpenShape is capable of retrieving 3D shapes that are visually or semantically very similar to the input image. So here is the first column is the input image, and the right two column indicates the retrieved results. Furthermore, since OpenShape's 3D shape representations are aligned with Clip's image and text embedding spaces, they can also be used as input for various off-the-shelf Clip-based 2D models. For instance, we can input our 3D shape embedding into an off-the-shelf image captioning model to create a point cloud captioning model without any extra training or finding. So on the right, we showcase by inputting the 3D OpenShape embedding into a 2D diffusion model such as a Stable Diffusion, which originally used the Clip embedding as a condition. So we can now obtain a point cloud conditioned image generation model. For example, the model can transform a 3D point cloud into a 2D image. For zebra point cloud, it can also we can also add optional text descriptions to generate zebras in specific backgrounds. So while OpenShape focuses on learning a powerful global embedding for 3D shapes, it cannot precisely capture the fine-grained part structure. However, 3D part segmentation is also very crucial in many applications of vision and robotics. Since fine-grained 3D part datasets are typically very difficult to annotate, and the existing datasets are typically very small in scale, so traditional supervised learning methods are restricted to a very limited number of object categories. For example, the Parkland dataset only includes 24 object categories, which is significantly fewer than what an intelligent agent would encounter in the real world. In the path-leaf world, we propose a novel method for open-world path segmentation of 3D point clouds in a low-shot manner by leveraging a pre-trained 2D image language model, GLEEP. As shown in the figure, our method takes a 3D point cloud and a text prompt of part names as input. So it can generate both semantic and instant segmentations for 3D parts in a zero-shot or few-shot fashion. So here, each color indicates a different part categories. As shown in the figure, for some common categories such as chairs, we can see that the zero-shot version can already achieve pretty good results. However, for the less common categories, such as the screws of scissors or spout of cattle, we still need a few short fine-tuning. So we only need 8 examples for each category to perform the few short fine-tuning, and the fine-tuned results can be pretty good. So quantitative results shows that path-leaf enables excellent zero-shot 3D path segmentation, and the few-shot version can even achieve highly on-par performance compared to the fully supervised traditional methods. Furthermore, it can be directly applied in real-world applications without encountering a significant domain gap. So here in this figure, we feed the iPhone scan point cloud into the path-leaf model, and it can generate pretty decent results, even though we have not incorporated any specific sim-to-real design or training. So this is all about path-leaf. So in summary, today, I introduced some of our recent efforts in enabling open-world 3D object understanding and generation by leveraging the recent large-scale 3D data sets and rich priors. requires embedded in various 2D models. 3D vision tasks will soon not be restricted to sheer research, but possess strong generalizability and being capable of to handle arbitrary object categories that a robot or an intelligent agent would encounter in the real-world applications. However, the fundamental role of a 3D foundation model, especially given the existence of powerful LLM, VLM, or video diffusion models, how can we make the 3D foundation models to be unique and irreplaceable are still open questions for me and require more time to converge. So I guess that's all for my today's presentation. Thank you for all your attention.
Thank you, Minghua. Very nice talk, and I think we have time for one question.
Thanks for the great talk. So maybe a question relates to the previous talk from Peter and Bill. It seems that for the 1 to 3, 45 types of workers already stepped into somewhere between the Gen 3 and Gen 4 category for 3D generation. That like if you train a 3D diffusion model using data. For the Matchformer, it seems you like step back a little bit into reconstruction model. So consideration sites.
Yeah, that's a great question. So actually, according to our experience, we find that the scale of existing data sets may not support the training of very powerful 3D diffusion models. So that's the main reason that we go back to just to focus on a more robust reconstruction model. But however, I guess if we have more sophisticated techniques, such as more powerful 3D orientations, the pipeline of the 3D diffusion models can still be very promising. But now, yeah, we feel that it's still very difficult to train a very powerful diffusion model by using only 3D data.
All right, let's thank Minghua again.
Also, not mirror, stop mirroring. Yes. Share screen. Yes. Yeah, should be good.
Yeah, I think I will. Hi everyone. It's my great honor to introduce Professor Andrew Wadati from University of Cambridge. Oxford, sorry.
Very important.
Very
big mistake.
Sorry. my mistake, yeah. So Professor Andrew has done a lot of great work in 3D generation and reconstruction. Without further ado, I'll give the stage to Professor Andrew. Yeah. Sorry about that.
No worries, no worries. Everybody confuses the two, except us. All right, great, excellent. So yeah, I would like to talk to you about going towards a 3D foundation. So this is not ambitious at all. First of all, what does it mean 3D foundation? So if you think about it, our discipline was essentially started with the idea of 3D computer vision, really. So this is an image I took from a vision by Marr, so one of our pioneers, his book from 1982. And you know, I guess on page 2 or 3, this is what you see. So you see an image which is trying to convince you that 3D is key to vision. The reality is 3D, so it makes sense that you should account for that factor when you want to understand an image content, the image content, and maybe you want to compute some invariants to do that, etc., etc. Right. So it seems like 3D modeling, really 3D vision, would have been fundamental to everything we do in computer vision. All right. So that's the premise. 82. How did that go? Well, the reality check is that maybe it didn't really go as we planned, right? So I started doing vision in around 2004, I guess, more or less. And that's where Back of Visual World exploded. So that's when 3D vision gave up, essentially, to some extent, at least in terms of image understanding. And we decided that, yeah, the extent that we're going to do geometry is we're going to take an image, break it down to 2D patches, compute some descriptors, and slap an SVM on top. Yeah, fast forward to 2021, Visual Transformers doing the same, just a bigger SVM, transformer network, still patches, still same story, okay? So it seems like 3D vision really didn't play such a big role, at least for what concerns image understanding. But my question in this talk is 3D vision going to change that? So is machine learning and 3D vision coming together more? Well, partially the answer is clearly yes. So we know that machine learning is helping 3D vision more and more. So we have things like neural readiness fields, which are a representation of reality, which is based on elements of machine learning, say as simple as MLPs. We have tools that can do 3D generations. We have seen just a great talk about just that a minute ago. So going from some text to imagining a 3D world, at least a 3D object. That's great. You cannot do that with machine learning, obviously, not just geometry. Or you can you can solve plenty of other tasks. So you can take a video of an animal and come up with a 3D model explanation of it. Again, something you cannot do just with geometry. You need machine learning for that. But my question is not just this. I mean, it's obvious that machine learning can help 3D vision, but the question is 3D vision going to be part of the new foundations of computer vision, if that makes sense? Okay, is 3D vision going to play a major role or not? So I think we need to, first of all, seek for an opportunity where 3D might really be important. And there are a few. One that I really like is egocentric data. So you look at this data. This is from Epic Kitchen, which is a data set for action recognition. So very often this is just tackled as a video labeling task in 2D. But if you look at it, it's very confusing. So of course, this is a bit accelerated, so it's even more confusing. But what strikes is that, yeah, there's information, stuff is happening there, but the first thing you notice is that the camera is, moving back and forth. And that is really confusing for us, and it's confusing also for an algorithm, because most of the variability that you see in the pixels is due to something which is not that informative, which is just camera motion, right? That could be useful to do 3D vision, by the way, but per se is just a nuisance if you want to understand what's going on there. So in order to study this problem, we have recently introduced this Epic Field dataset, which is just an extension of Epic Field, where we did something extremely simple. We went there and we just ran Colmap on all of it, basically. So that's the difficult part, I guess, scaling up Colmap enough to make this extraction of camera motion automatic. We succeeded somehow, and now we have an extension of Epic Kitchen. We have this collection of videos of people cooking in kitchens for minutes at a time, maybe even an hour. But now we have cameras together with it. So you think, okay, big deal. Well, actually, it isn't to some extent, because extracting cameras is one of the most annoying things you need to do before you can even start to do 3D vision. And in a sense, that's one good contribution of the NERF paper, right? It's where you get this data set where cameras are already extracted, and all you're left with is something where machine learning can be applied to very, very easily. So by doing that, we can simplify the life of people that want to start to approach image understanding tasks, video understanding tasks using 3D vision. Once you have this camera, you can do many interesting things with them. For example, you can have you can reconstruct your kitchen, and then you can contextualize the action in this bigger space. So you don't have this tunnel vision, which is given by your eyes. You can remove your camera motion. You can expand the sort of understanding of the environment like that. And you have something that can estimate maybe your hands in 3D, then you can project that back into the kitchen. And again, that is part of contextualizing what's happening. You can go from this sort of egocentric perspective in an exocentric one, which makes certain tasks more easy. Now, that's great, but all we're doing so far is just 3D reconstruction. And one way to do that is to use something like NERF, for example. That would be the modern way of doing it. Maybe now even more modern Gaussian splatting, doesn't really matter. It's just a 3D reconstruction through optimization. So you have this model M that you want to get. You have a bunch of images, maybe images of your kitchen, maybe an apartment, something else. And what you do is you have a rendering function that takes this model M, renders that back differentiably onto the image. You can compare that image I hat to the image I that you actually measure from the real world. We also assume you have the cameras, which we do in Epic Field. And you set this up as a loss that you want to optimize over with respect to your model M until you get the model M star, which is your reconstruction, right? This is just analysis by synthesis, just the way to do 3D reconstruction now, I guess, right? And that's great. But okay, what else can we do with this? So with this, we get maybe 3 points in colors, maybe volumes. Can we do something more than that? Well, one thing you can do is you can take your images and you can extract them from each one of them some two-dimensional information. So this is just a sort of rough depiction of what this might look like. So you get an image I, you apply a network. It could be an image segmentation network. It could be a network that extracts some 2D features. Now we get that as output. You can put that, you can take those features F back and add them as feature channels to your image I. So now you get images which are RGB plus features, right? And those features can be anything. And now you can train your model to reconstruct not just the RGB components, but also the feature components, all right? In the same ways as we've done before, same story. And if you do that, well, some good things happen. So here we have done this in neural feature fusion fields a few years ago using Dino features. So Dino features are self-supervised 2D features that capture semantic in your scene, but in a way which doesn't require labels, right? So what you see here to the left are the RGB frames from Epic Kitchens. In the middle, you see the Dino features extracted and visualized using PCA. And the idea here is that the same colors should correspond to things which mean the same. The pixels belong to the same object. Again, this is done unsupervised in a supervised fashion, but the features are sensitive to semantics. You will notice, though, that this is not perfect. So first of all, they're a little bit low resolution, and also they're not exactly point invariant. They should be, because the semantic does not depend on the points, but they are not. Now, if you fuse these features in 2D, just extending NeRF, then you get a cleaner signal, which is higher resolution, which is good. But most importantly, and that's really the argument I want to make here, if you want to solve a 2D task, like, for example, segmenting objects, the semantic segmentation here, or maybe detecting objects and tracking them, but it turns out that if you use features that are being fused in 3D, you perform quite a bit better than just using 2D features alone, all right? By fusing information in 3D, we are helping 2D vision to perform better. So this is actually doing better than just using a 2D network, okay? And this is obtained by using 3D vision, so that's good. At least good if you like 3D vision. And here's an example of what you can do with this. Because the features are semantic, you can embed them into your NeRF, and now you get for free, for example, foreground background segmentation, all right? Now you can extend this concept to many other kinds of signals. So for example, if you have an instance segmentation network, you can do the same story. So what you see here in the middle is a network for instance segmentation, and that is being run on each frame on the video independently. And you can see that it's picking up all these different objects, but the colors which corresponds to the labels of the segments, well, they're not constant over time. The reason is that this detection, well, they're independent over time. So there is no reason why the naming that the segmentation method assigns to the different object would be compatible when you go to the next frame. And in fact, they are not, all right? Also, the objects tend to flash in and out because you don't always see in all frames all of them equally well, right? But if you diffuse these segments in 3D, and there's a way of doing that which is efficient, which is done in this paper, which we call contrasted lift. So if you have an interest, please have a look at the paper itself to see how we do that. And essentially, once you have fused these features in 3D, then the labels become consistent over time, and you also remove noise. So it performs better. So again, you can see that if your task is panoptic segmentation, because you are fusing this data in 3D, then your performance goes up, right? Again, another example where 3D vision helps 2D networks to do better, okay? And your imagination is the limit here. So you can fuse any sort of 2D feature. So here we're fusing clip features. This is probably similar to stuff you're seeing from Kanazawa's group, where they embedded clip into NeRF to be able to respond to textual queries more or less in real time when these features are embedded there. What we did was to extend that to be able to understand better compositional text. So here we can say something like red toy chair, and that's what would light up, not the other chair. You can say something like green toy chair. So the green one now is lighted. Or you can say something like, I think the next thing is, chair leg. So now this is brought up, right? And so there's a way of taking clip features that are this sort of different semantic levels of, well, this different resolution level of semantic, not just size, so physical size. And you can get these features that can respond to all these different queries efficiently by a single embedding vector that you associate to the 3D space, all right? If you want to know how we do that, have a look at our nested neural feature fields paper, which is now out in arXiv, all right? But it's not all good. So actually, let me skip over this. So it's not all good. One thing which is a bit of a limitation, I think, of 3D vision today, when you apply that to tasks which are about image understanding, is the fact that motion doesn't work all that well. So this is a great slide from Kanazawa's group again. So you see here on the left, what we call here causal captures. So this would be captures that you can get with a cell phone, and the subject is animated. So you see that there's a cat, maybe this little thing spinning. And those are things which are hard to reconstruct because it's not just the motion of the camera you have to deal with, it's also the motion of what's in the scene. And this just doesn't work all that well, right? What you see, what people like to use are the data set on the right, where there is still motion in the scene, but the camera motion is dominant. And this is a trick in a way, because then when the camera motion is dominant, doing things like triangulation is much easier, and then it's much easier to get 4D reconstructions. But I think this is really where things don't work very, very well in 3D vision just yet. And if you want to have a foundation of vision, okay, which is based on 3D, really, where you want this to work well are videos. Because explaining videos is where really 3D can shine. But then 3D is not enough, you need to do 4D, not 3D, all right? Now to get there, we're gonna need a new family of methods for analyzing motion in videos. So that's one motivation for us in Meta to develop CoTracker, which is a state-of-the-art tracker, at least at time introduction. I still think basically state-of-the-art. And the novelty here is that you can track jointly a very large number of 2D points together and very, very robustly. And the idea is that you want this to be able to work on any video. So download anything from YouTube, this should be able to work well, because then you want to build 3D vision on top of that, okay? So I think these are sort of tools for analyzing 2D motion will feed into much better 3D computer vision system later. So file that as something that is useful if you want to do 3D vision with time. But when it comes to modeling the dynamics or things that change over time, well, you can try to do that on a per video basis, but what you really want to do at the end of the day is to be able to understand a world of objects which have a dynamic. You have humans, you have animals. It's not just one human, it's not just one animal, it's a family of them, and they all move in a sort of characteristic way. So it boils down to try to understand the dynamic of a family of objects, not just a single one, and to be able to understand the space of possible dynamic configurations they can have, right? And if you look at what we have done in the computer vision community in 3D, there's lots of great work like SMPL and SMALL for modeling respectively humans and animals. But these works, the limitation there is that they're not open-ended. So you need to do quite a bit of manual work to be able to set them up for every new object category. And this is very limiting because we want 3D vision again to be sort of a universal foundation of vision. We don't just want to do humans, we don't want to do a few animals, we want to do all of them, right? So that's the challenge. And so for the past several years, we have been working with a group of colleagues from Oxford as well as Stanford on trying to get there, right? So we want to get a model of dynamic objects which are more and more general. And to do that, we want to supervise them automatically. So self-supervised from internet data, because then we can expand their scope much more, right? So the latest of these works, which I'm going to talk about today, is called Learning the 3D Phone on the Web. And there's going to be a poster here at CVPR. So you can go to the main conference and see more of that later. So the way we approach this problem is photogeometric autoencoding, which is a big word that means something very simple. So you get an image, the ones to the left. You have a network that looks at the image and decomposes that in a bunch of factors which make photogeometric sense. So you have something like the shape, 3D volume, or 3D mesh. You have the material, so what that mesh looks like. You have the motion, meaning the deformation of the mesh, the light, and the camera. Once you have those ingredients, then there's something you can handcraft that generates the image back, close that into autoencoding loop for the construction loss. You can train that, done. You wish. I mean, it's not that easy, but the concept at high level is just that. Now, these are how we actually do it in practice. So first of all, we need a way of learning a template for object category, for example, a horse. So we start from the MTED space, which is just a voxel space where we can efficiently define a mesh that we can learn in real, but together with the other parameters of the model efficiently. We initialize that as it looks like a potato with a skeleton inside. The topology is decided by hand, but everything else has to be learned. After training, what we get is a 3D mesh, and the 3D mesh is also augmented with dyno features. So each point of the mesh will have a characteristic vector that describes that point in a semantic sense, okay? Why do we do that? Because these dyno features, they're so unsupervised, very general, but they tend to be sensitive to the semantic what you're looking at. So again, you can see here that different colors, PCA colors appear depending on which part of the animal you're looking at. So the head is always purple, the legs are always green, okay? This is why it makes sense to try to map that to the 3D model, so then it's easier to establish these correspondences when you want to train your model. So this is how it looks like, again, a bit at a high level. So we have an image there. We have this template model we want to learn for that object category, in this case of horses. There is a network that does the de-rendering, so it figures out the texture, the articulation, the deformation, the shading and lighting, and the camera motion, the camera position as well. That gets then your template model gets into your rendering function together with these factors, and you can reconstruct the dyno features, the appearance of the object, and the mask, and you can compare that to what you have measured in the image. Again, this becomes an autoencoder that then you can learn. I hope you can hear me back there. Hello? Dead. I killed it. Great. Yeah, all right. So I'm gonna shout, maybe. But this is again for a single object category, right? So this is not general enough. Okay, it's back. So what we want to do really is to be able to do maybe any animal eventually, but for now, any quadruped at least. So what we did was to take this model and extend it one further to be able to, from a single image at a time, come up also with the model of the base class on the fly, right? So the way we do that is we map this image to a set of keys that look in a dictionary of base shapes that we also learn, all right? So the dictionary is fixed for every any image we want to explain, but the dictionary itself is also learned. And then on the fly, basically what happens here is that there's a lookup operation using basically self-attention in this dictionary that builds up on the fly a model for that base shape that then we can use as an explanation for what's actually going on in the image. And we close that into this autoencoding loop, okay? This wasn't that easy to make work, but if you persevere, you can succeed. And that's the sort of result we can get. So you can see that applied here on a large collection of images that we got from the internet with minimal cleanup and no annotations other than knowing that there is an animal center in the image, okay? And we can train like that hundreds of categories of animal classes. And how do they look like? Quite good. So here you see a bunch of input images to the left. They get, so you can extract a 3D shape. But again, this is not just 3D reconstruction. What we're getting out of that is a dynamic model, right? So a model of the possible dynamic configuration of the object, because there is a skeleton there that we can deform to try to make the object do weird things, all right? So again, it's not just one single reconstruction, it's a reconstruction in a space of dynamic objects, right? And here's another example, more objects. You can see that it works for a variety of different things. There is a toy cow at the top left, still works. There are a bunch of animals which are not shaped like a kangaroo, and it still succeeds. And this is an example of how this looks like if you apply it to the frames of a video individually. It's good, but this is just because there is no temporal smoothness here. It's just that the reconstruction is stable enough that it looks like you get an animation out, but you really don't. So this is reconstructed for each frame independently. Okay, now, next step, the reconstruction. So what I showed today, just now, is how you can reconstruct deformable animals from a single image, right? Okay, that's fine. And our friends in Adobe have done tremendous work here, as well as a lot of other people in the community, of course. One very good example of a model that can do that, maybe not for a articulated object, but at least for a single object, or maybe starting from a single image or a few images, is the large reconstruction models. These are great. These are, I think, a breakthrough in our community, especially if you want to do text to 3D and a bunch of other applications. The disadvantage is that it takes 385 GPU days to train this model, okay? This is large, great. It's also expensive, not so great, okay? And I'm a Meta, but I'm also in Oxford, so I don't like expensive things when I'm in Oxford. So we wanted to develop something that would do single image reconstruction much faster. So this was an idea by students, which I didn't give credit until I actually saw that this would actually work. That was surprising to me too. It's a poster at this conference on Thursday morning, so you want to know more, go there. It's called the Splatter Image, okay? It's not about horror, it's not a horror movie, although that was an inspiration. What it means is that we do Gaussian splatting from a single image. So take an image as input, and then we do a UNet that associates to each pixel the parameters of a corresponding Gaussian, all right? And the advantage here is that this network is really efficient. You can compute that very, very, very quickly, more than real time, all right? And let me explain what it means to compute a Gaussian for each pixel. That's literally what this is doing. So you have a camera, image pixels. For each pixel, you get a bunch of parameters: sigma, mu, capital sigma, RGB plus, and delta. So what are these? So one is the opacity of the Gaussian, the other one is the mean, the centroid, which is expressed as a depth along the ray. Then you have the shape of the Gaussian, capital sigma. You have this RGB, just the color, maybe spherical harmonics. If you want to get that, you can. And then you get delta, which is displacement. So when you get your Gaussian center there, you can displace it off the ray, okay? So you get a little Gaussian that says that pixel, but that doesn't have to live exactly on the ray. And this is actually crucial, right? Of course, you do that for all the pixels, so you get up to 1 Gaussian per pixel. I say up to 1 because if you switch the opacity to 0, then the model can decide to discard that pixel's Gaussian, all right? And here how the reconstruction look like. single image reconstruction on Code3D on the class teddy bear. You can try it on a bunch of other classes and it would work similarly. And you can see that the back is a little bit blurry, but it's amazing we get the back in the first place because this is pixel oriented. So you wouldn't think that there would be enough information to reconstruct the back, right? That's a little surprising. But these are what these Gaussian displacement are doing for us because they allow to use some of the Gaussians on the back to reconstruct, sorry, the background to reconstruct the back. It works beyond just Code3D. Single categories is actually works well enough open-ended. So if you train into an Observerse, then you can run it in Google scanned objects and it works still quite well. And this is how you get this background Gaussians to do the job for you. So you can see here two objects in the car and the chair. And we don't see everything in that image, right? So there are some parts of the chair and the car that are not visible. Nevertheless, you can see that there's sort of this halo effect where we get still Gaussians there, right? They're not switched off. These are what the others are pointing at. Well, these duplicate Gaussians, actually what they're doing is through this 3D displacement, they're going to be placed at the back of your object to explain what you actually don't see, all right? That's the magic of this, that you can use these additional Gaussians to try to reconstruct your object where you don't see it. What's the point of doing all that? Well, in terms of high reconstruction quality is comparable to state of the art. Sometimes a little better, sometimes a little worse. But the point here is that this is super fast at rendering. Okay, that's Gaussian splatting, so 600 FPS, fantastic. It's very fast at reconstruction is 40 FPS, single GPU, all right? And that's very important for academics, is very fast at training. So you can train this in 7 GPU days, not 300, okay? All right, that's the message. And we have now extended that to scene. So it's a single image to scene reconstruction, same story. It's a bit different because we don't have the idle Gaussian begins for the part we don't see. So in fact, we're estimating up to 2 Gaussians per pixel, same story. And if you start training this using a pre-trained depth estimation network, and we have some excellent ones now, then you get for free excellent generalization. So you can train this on real estate 10K and still get new V-synthesis, state-of-the-art new V-synthesis results on KT, which is quite a big jump. Again, that's the magic of combining the very nice 3D computer vision models we have now based on large-scale training with this sort of Gaussian splatting, right? It's fast. You can train it on a few GPUs for a few days, and you're going to get the results. What's not to like about that? Okay, now last couple of minutes, I want to switch gear yet again, and I want to switch back to proper 3D generative AI. What do I mean by that? Well, you've seen that in the previous talk a lot, so I don't need to reiterate that, but so you have a prompt like a Viking axe. Your task now is to turn that into a three-dimensional object, right? Text to 3D, or you can consider image 3D. So you have an image of the axe, and now you want to get the rest of the views, or in fact, you want to get a three-dimensional object that can be used to render all the other views. This is, again, a task which is not deterministic, because what you get as input is an image which does not contain per se enough information to know the shape of that object, and maybe also what's on the back, obviously. So we need to sample a conditional distribution, P of M given I naught, all right? Where M is the 3D model, and I naught is the image we have, or maybe the textual prompt. So the way we're going to do that is the usual recipe. So we're going to start from an image I naught, and we're going to generate a bunch of views of that using a model that's been trained to do that. The advantage of doing this way is that you can pre-train this image generator using billions of images. You can start from Stable Diffusion, or if you met, you start from EMU, all right? But once you have it, you can fine-tune it to generate new views, and that's great because this gives you really the open-ended nature of the model, all right? Once you have the new views, well, you can just fit the 3D model to that, and off you get your 3D object, all right? So this is, again, 2 stages, right? Input, image or text or prompt, then you have this multi-view generator that gives you hallucinated additional views, and then you have the construction step in which you get to the object. And so what I'm going to do in the last 5 minutes, introduce the latest and the greatest that we could actually achieve in the past year, which is called Meta 3D Gen, okay? So Meta 3D Gen, we started from the same question that was asked at the end of the previous talk, which is, what does it take for 3D generation to be used by a professional? And there are a bunch of things you need, the requirements you need to hit. You want high quality shape, high quality texture, then you also want high quality control. You want materials, parts, good UV topology and quality, mesh topology has to be very good, rigging, et cetera, et cetera. Now, we didn't hit all these targets, but I think we made some progress in at least these 4, right? I don't have time to cover all of them, so if you want to know more about that, there are some references I'm going to give you at the end. But the first thing we did was to add material control. So we want to be able to generate not just RGB objects, but objects with a proper BRDF. So that means we want an albedo, color, more correctly, base color. We want to have roughness and metalness. These are the key ingredients that you need to be able to relight the object properly. So that's one thing that you want to achieve, we did that, okay? Second thing that I think is going to be a bit more interesting to this audience is actually how the reconstruction network works. It's not completely original, but there are some key improvements that we have to make this work really well. So it starts from 4 views, like MVDream, I guess. And there is a reconstruction network very similar to Instant3D, actually, that does the 3D reconstruction there, but with some changes. So first of all, which representation are you going to use? NeRF, volumetric rendering, or are you going to use Gaussian splatting? If you're the cool guy in the block, you would probably use Gaussian splatting, but that comes at a cost, right? So neural field or Gaussian splatting, where do you sit? Well, so if you use neural field, you're going to get slower rendering, okay? But also you get gigantic memory footprint when you do backpropagation. And that really kills it when you want to train, especially if you want to use pixel level loss like LPIPs. This says PSNR, that's wrong, I should say LPIPs. And this is very important if you know that your reconstruction is going to be imperfect, because you want to have a little bit of flexibility when it comes to comparing that to your ground truth input image, especially when input image is generated, so it's not perfect, right? But on the flip side, you get good surfaces and better global convergence. Gaussian splatting is faster, has a very small memory footprint by comparison in backplot, but it gets not very good curved surfaces, and it tends to be more prone to local optima when you train it. So what we did was to try to address the memory bottleneck you get in NeRF. So we could actually base our reconstructions still on a neural field, and that's what we did by introducing a few months ago light plane kernels. So light plane kernels, they do in sort of fused manner the calculations you need to do neural rendering. The big advantage of those is that you get same memory efficiency at Gaussian splatting. Actually, we did this before Gaussian splatting, but whatever. Now is as efficient as splatting in terms of memory efficiency, and that is really what can unlock NeRF for this kind of applications, I think, because they can be high resolution in your volume space and also high resolution in the image you generate. It's still slightly slower than Gaussian splatting, but you get the advantages of having more robust convergence. And that's how this looks like with and without the light plane kernels in terms of memory consumption. So it's a few orders of magnitude better than just using NeRF and standard AutoGrad. The other ingredient that was important was to switch from using an opacity field, as you should assign distance function, so you get much better surfaces there. Again, not our inversion. We use, in fact, VolSDF to do this, which is one of the formulations that allow you to switch from opacity to sign distance function SDFs. The advantage here is that we have integrated that in light plane kernels, and so it's also memory efficient. Final technical ingredients, and then I'm going to just finish some results and conclude. The texture that we get are good like this, but not quite as good as we want them. So we have one final network, which is just a texture generator. And the key insight here is that if you try to generate a texture directly from a single image of 4 views and get the textured object, it works, but not as well as using a texture generator model, which is actually conditioned on the shape you want to texture. So what we did here was to design another architecture, another network that takes as input renders of the 3D object in terms of its position map and normal maps. Position map is very useful, by the way, because that's invariant with respect to viewpoint. So implicit encodes for correspondence between the views. And condition on that, then you can get 4 more views of the object from which you can get very, very good textures. So what I mean by that, here's a 3D asset by an artist, actually. And now what we're going to do is put a texture prompt there, which is not this, but the next one. It says something like a majestic monarch butterfly, and you get the texture out. And now you can decide to change your texture prompt and say something like magical butterfly, arcane sigils on its wings, sparkling glitter on its body. And because this is based on EMU, which is a very good, powerful image generator model, which is based on language, a text recognition image generator model, then it understands these prompts quite well and gives you this very nice, high resolution, consistent texture without many defects. All right, put everything together, and this is the sort of results we can get. So this is a Meta 3D Gen again. Let's spin around so you can see how these objects look like when you have done it. So yeah, they look quite nice, I think. My opinion, also backed by some quality stats we have run with professional 3D artists and as annotators, so we know that they like this. And because we have these texture generation components, once you have your 3D object, you can actually go back and change what you're looking at. So this is Christmas style. And now you can spin it around, and then while you're spinning, you can change your texture, just as you've seen for the butterfly. And so the next one will be horror style, and now I get something a little bit different. Okay, same 3D shapes, but because we have this powerful 3D model, texture generator model underneath, we can get these different skins, if you like, very, very quickly also. In fact, I should say one thing. So this takes 1 minute to generate an object with a high quality texture, which is actually from 3 to 10 times faster than competitors, we think, at least in our evaluations. So it's also quite efficient. So we don't really do iterative optimization. This is just feed-forward networks all the way through. Want to know more? Papers are done. We're just waiting for some approvals, internal approvals, but hopefully they will be available later this week on Friday, possibly next week, early next week. So some thanks, Oxford team, quite a few people there. Some of them are possibly in this room. If they're not, they will be told off later, I guess. But jokes aside, so this is a work that, so thanks to them to carry out all the great work you've seen from Oxford. And of course, this is the Meta team. Again, plenty of wonderful people that have helped us getting where we are. And I guess the animation is incorrect here. So just a summary, I show you 4 things mainly. Opportunity. So 3D vision is great for improving your 2D methods, especially when it comes to egocentric data, I think, where you have lots of camera motion, and 3D vision is really a killer to explain that away. Motion, so that's a Achilles heel of 3D vision yet still, but this is where we're making rapid progress, and I think this is where we're going to see breakthroughs in the next few years. Really great. So then we're going to be able to explain what happens in the 3D, those eccentric videos, also in terms of animation. Generative AI is going to be really helpful to provide the priors we need to do this explanation in 3D and 4D eventually. And efficiency. So if you're not in Meta, but you're in Oxford or any other university that doesn't have access to thousands of GPUs, then you really want to care about these methods that can do some of these tasks quite efficiently to level performance, which is maybe not quite state-of-the-art in terms of quality, but gets close enough that you can still do interesting research on top of them. Okay, that's all. And apologies for being 2 minutes over time.
Thanks for the great talk. So any questions?
Okay, 2.
Can you please switch to the resources slide?
Which one? I had, yes?
No, the next. Resources.
Oh,
papers.
Oh, this one. Sorry, yeah. I thought you said results slides. I mean, there will be an archive, and it's just called Meta 3D something, so it's going to be easy to find. Okay. Anything else? Yeah. Yeah.
You know, for traditional reconstruction, you go through batching and example post-estimation, and then like translation technique to the 3D reconstruction. But you know, now with the large reconstruction model, people start modifying parts and decide that kind of post-estimation.
Yep.
So how do you think about this? Like, is it possible for these foundation models to be benefited from some old school techniques?
Yes, I think so. So first of all, you can still do some post-processing with 3D optimization, which would try to fit better your model back to your input images, and that could use differentiable rendering. It's not exactly what they were asking though. It's a good question. So I'm of 2 minds on about that. So I still think 3D vision in the more traditional sense will still be relevant in terms of estimating camera motion, in terms of doing triangulation, etc. But you see there is a trend also here. We have Jerome Duster is a great example of something that really also get rid of a lot of this the old school 3D approaches to computer vision. It goes away with triangulation. It just gives you nice point clouds from which then you can infer camera motion, you can infer even intrinsics, which is great. So it seems to me at the end of the day, we're going towards a place where we don't need to do these things explicitly anymore. Yes. In fact, one thing which is interesting to ask is, are we still going to need primitives like points, triangles, texture, UV maps in the future, or is it going to be just neural rendering all the way through? Is your PlayStation 15 going to be just neural rendering engine without any actual 3D structure, 3D technology as we know it today inside? It's possible. So these things could go away, but not anytime soon, I don't think. Not entirely anyway. But they're going away. They're going away, potentially. Anything else? No? Okay. Thank you.
We will first have Jun Gao to be our first speaker. And Jun is a PhD student at University of Toronto and the Vector Institute. He's also a research scientist at NVIDIA. And he has done a lot of cool works on 3D generation, 3D reconstruction, and geometry processing. And he will also be joining the University of Michigan as the assistant professor in 2025. Okay, now I will give the floor to Jun to start his talk.
Hi everyone. So it's thanks for the introduction and thanks everyone for joining my talk. It's really my honor to be here and present our work on 3D representations for 3D content creation. Wait, okay. Okay. So in the past few years, we have seen amazing progress on using machine learning to create digital content, such as the language, image, or video. And this is a very exciting time of generative AI. However, the world we humans interact with is fundamentally a 3D world. We study and learn in a 3D environment since childhood. We perceive these very beautiful 3D animals or forests. We also communicate with each other in a 3D environment, such as in this classroom. We further perform some actions like driving a car in a 3D environment as well. So the key common factors behind all of these different scenarios is that the content that we humans interact with is always a 3D content in a 3D world. So therefore, to broaden the impact of generative AI to our life, I envision in the future, the generative AI system will help us to create realistic 3D virtual worlds and enable the immersive interactions between the human and the simulated virtual environment. For example, in this movie, the main character could seamlessly interact with this virtual city. This is going to be a very exciting future. And that being said, the future is not here yet. Generating 3D content with AI faces fundamental challenges that are very different from generating image or language. First, the size of the data set that we have in 3D is much smaller compared with image data set. Even until very recently, the size of the largest 3D data set that we have is still around 2 orders of magnitude smaller compared with image data sets. At the same time, while we have much less data, the complexity that we need to deal with in 3D is much higher than a 2D image. And this additional complexity is not just we have additional dimension in 3D, it is also the complexity in terms of 3D geometry, materials, and the final lighting effects. We need to generate all of these different kind of informations for realism and for immersive experience for the users. So before we go to the technical part, let's also take a step back and zoom out a little bit. So actually, the problem of creating 3D content itself is not a new problem. It has been studied for decades from the computer graphics back to 1960s. So the computer graphics community has studied many techniques from modeling the 3D geometry to animating the created 3D content, from modeling the appearance to finally rendering and showing a photorealistic image to the user. So this is very cool because we do have some tools that can create realistic 3D virtual worlds. And these tools provide a lot of domain knowledge on how we should model the 3D content, such as the appearance, geometry, etc. However, the key challenge here is many of these tools are often designed for experts. And therefore, it is very hard to scale up and allow much more people to create 3D content utilizing the graphics tools. So to push toward the future and tackle the challenges that we have for 3D content creation, my area of research is basically how we are able to develop generative AI system for 3D content by incorporating the domain knowledge from the computer graphics. And this is a very multidisciplinary area in between vision, graphics, and machine learning. More specifically, we have been working on 2 axes along this line over the past few years. First, to tackle the challenge of the 3D complexity, we study how we could leverage the 3D modeling techniques from the computer graphics and incorporate it into the 3D generative AI system. In this approach, we are able to regularize the generation behavior and reduce the 3D complexity. This could further improve the efficiency, fidelity, and the usability when creating the 3D content. Second, to tackle the challenge of the 3D data scarcity, we study how we could leverage the foundation models and extract the 3D structures from these foundation models by incorporating the inverse graphics. And in this approach, we are able to improve the realism and the diversity when creating the 3D content. By combining the approach we have for 3D modeling and also the algorithms we have for leveraging the foundation models, we are able to turbocharge the applications in the whole spectrum of 3D content creation, such as how we can generate 3D content from single view image, how to do multi-view 3D reconstruction, how to build a 3D generative model, and finally, how we are able to do text to 3D generation. And in this talk, I will mainly highlight our 3D representations because our algorithms for leveraging foundation models are building on top of our 3D modeling approach. Okay, so this is basically the motivations of why we are working on these different directions. So now let's dive in. So let's first look at the 3D modeling part. And in the past several years, we have seen amazing progress on neuron field-based approach, such as using a neural network to model a signed distance field. Such a neuron field-based approach has inspired a lot of work from 3D computer vision, such as NeRF for 3D reconstruction and many others. This approach is very suitable for machine learning because it has continuous definition in the 3D space. And such continuous definition makes the optimization of neuron field very easy. It can also represent very complex 3D geometry, such as the complex shape that we can see from the NeRF. However, such a continuous modeling approach is also very redundant. For example, suppose we want to model this bunny, then we need to not only model what's inside of this object, but also what's outside all of these empty regions of this object. And because of these redundancies, rendering a neuron field is actually not very cheap. More importantly, for many applications, like if I want to render this object with lighting, or if I want to touch this object with a hand, what matters most is actually the location of the 3D surface. However, since that 3D surface is only implicitly encoded in the parameters of the neural network, such explicit reasoning on the 3D geometry is much harder. So, however, from the other side of the computer graphics, actually, we do have one representation that specifically focuses on the 3D surface. And this representation is 3D mesh. Mesh is super compact in modeling the 3D geometry because it is specifically localized where the surface is. And because of such compactness, rendering a 3D mesh is very fast. However, generating the mesh with the AI system is not trivial, especially when we want to change the topology of a 3D mesh, because this will involve learning the discrete connectivities between the mesh vertices. So to bring the mesh into the generative AI framework and incorporate the key rationale that we have is that we should focus on the actual 3D surface. We developed a differentiable isosurfacing approach for 3D modeling. And this is a joint work with my fantastic collaborator like Frank Shen on the top right corner. So specifically, in the forward pass during training, we hope to differentiably extract a 3D mesh from a neuron field. And this 3D mesh is the isosurface of the neuron field. Through this approach, we are then able to define a lot of objectives that are directly evaluated on the 3D mesh. Such objectives could range from a rendering loss by comparing with visual observations to more complex geometric energy functions that are defined on the surface. It could even be a loss function from a physical simulator. In this approach, or in the backward pass, since the operation is differentiable, we can then backpropagate the gradient from all of these different objectives into the neuron field to update our neural network such that we are able to generate the content that we really want by minimizing these different objectives. And the benefit of this one is very obvious. First, we could regularize the neuron field on the left side to specifically focus on the 3D surface. It can also unlock new capabilities by allowing us to define new objectives that can only be well defined on the 3D surface. We could also gain the efficiency by leveraging the hardware accelerated rendering or solvers that have already been developed for 3D mesh. Okay, so this is the motivation why we want to do this differential isosurfacing. Let me do a very quick introduction about how we achieve this differential isosurfacing. So formally speaking, what we want to do is something like this. Given a neuron field function, like an implicit function f on the left side, and the input to this function is the XYZ location, and the output, for example, it can be a signed distance function, a signed distance field. And then this function is parameterized by theta. We hope to extract a 3D mesh on the right side. And this mesh is represented by mesh vertices and the face that connect these different vertices. The differentiability that we want to achieve is to compute the gradient from the mesh vertices into the parameter theta, such that we are able to update our neural network and train the neural fields. Without diving too much into the technical part, the key observation we have is the original marching tetrahedral algorithm is differentiable if we can combine it with a grid. So specifically, we can first define a discrete tetrahedral grid in the 3D space and evaluate every corners of this grid cells using this function f. So in this figure, red means inside of the object and has a negative sign in the network prediction. Green means outside of the object and has a positive sign in the network prediction. With all of this prediction, we will then focus on the grid cells, which have different signs on its corners. For example, the one I'm showing here. In this figure, VA and VB denote the location of the grid corners. FVA and FVB is a network prediction at corresponding locations. With all of these predictions, one assumption we have is that given the network prediction at every corner of one grid cell, the whole field within this cell will be linearly interpolated, such as what I'm showing here. With this assumption, we can then very easy to extract the vertices on the isosurface through this equation, the middle yellow point here. The key intuition why this operation is differentiable is because if we look at this equation, the location of this VAB is actually a function of network prediction FVA and FVB. And therefore, the gradient from this VAB can be very easily backpropagated into the function f through the chain rule. Okay, and the same operation can also be applied into the other edge of this grid cell, like VA and VC here. And we can extract another vertex on the isosurface, like VAC here. Connecting these two vertices will give us an edge on the isosurface. And such operation can be applied to all of the grid cells and extract all of the points on the isosurface. Connecting all of these different points will give us an isosurface on the 3D mesh. Okay, so this is basically how we achieve this differentiable isosurfacing. But as I was mentioning in the beginning, the key thing that we want to do is to apply this differentiable isosurfacing into many applications, such as by defining different objectives on the 3D surface. Now let's first look at the vision-based objectives. So in this case, we want to do multi-view 3D reconstruction, which means given a set of images that kind of captures one 3D scene, and then with the camera parameters for each image, we hope to reconstruct the 3D information from this scene, such as 3D geometry or the appearance. We can achieve this goal by simply first using our method to modeling the online 3D geometry and differentially render this 3D geometry into the 2D images. The loss function is then computed by comparing the rendered image and the ground truth visual observations. The key benefit here is that the gradient from this loss function can then be backpropagated directly into the 3D geometry through differentiable rendering and differentiable isosurfacing. And as we can see in this animation, after training, we are able to reconstruct the 3D structures that aligns well with the visual observation. The key benefits of in this video, we can also compare our method with other baselines, such as use a Newton field to model the online 3D geometry. The key benefit of our method is to reconstruct much better 3D geometry. And the reason for that is because differentiable isosurfacing allows us to specifically focus on the 3D surface and optimize for that 3D surface. Another benefit is since the output of our model is a 3D mesh, then we could easily interact with the reconstructed 3D content. Such interaction could be something like we do material editing to change the materials of this object, to do something like physical simulation with this reconstructed object, or doing something like the relightings of the reconstructed objects. So this is like having visual-based objectives. We could also optimize with a soft body simulator and reconstruct a deformer object by minimizing a physical objective. So in this case, we hope to optimize not just the 3D geometry, but also the physical parameters that control the simulations of this object. We can achieve this goal by first using our representation to model the online 3D geometry and fit it into a differentiable soft body simulator, such that the simulated simulated object sequence will align well with the video observations. As we can see after the optimization, we can reconstruct a deformer object that aligns well with the video observations. Okay, like the next one is that we can also using our representations and build a 3D generating model. And this is a very old paper, like back to 2 years ago. And we can also like train a GAN-based 3D generating model using our representations. And these are some generating results from our methods. And of course, this is not the state of the art for now. Okay, so, and furthermore, our representation can also turbocharge the text-to 3D generations with the Scott distillation samplings from the prior works. So let's first also briefly recap what is the Scott distillations for text-to 3D generation. So we can have a Newton field to model the online 3D geometry, and then differentially render this Newton field into 2D images. And we can then further fit these 2D images into a diffusion model And this diffusion model will then give us a gradient direction to update this image such that the image will look more realistic. And this gradient direction can be backpropagated into the neuron field for optimization. And the challenge for this kind of framework, the first challenge of this kind of framework, the biggest challenge is the cost, is the computational cost. Because in this case, suppose I want to do one pass, like one iteration, then the whole computational cost will be the number of images we rendered times number of pixels to render one image, and further times number of points that we will sample for each ray to render one pixel. And typically, to render a neuron field, we will sample hundreds of points along the ray, which means the last item in this equation will be almost 100. And secondly, because of the such high computational cost to render one image, we could only render the image at a very low resolution. And such low resolution rendering, we are missing a lot of details on both the geometry and the appearance. So, however, one thing we do know is that rendering a 3D mesh can be very efficient and fast. For example, suppose we have the mesh in the loop. To render the mesh into an image, what we need to do is just shoot a ray from the camera, and this ray will intersect one point with the 3D mesh. Collecting the colors of this point will immediately give us the colors of the corresponding pixel. And therefore, suppose we have the mesh in the loop, then the whole computational cost of this pipeline will be number of images times number of pixels times 1. And this equation is almost 2 orders of magnitude smaller compared to the equation we have seen previously. Furthermore, because of rendering 3D mesh is very cheap, we can render the images at a much higher resolution. And such high resolution rendering can capture a lot of details on both the geometry and appearance. Such kind of advantages of both efficiency and the quality enhancement can be very easily achieved by incorporating our differential isosurfaces into the loop. In this case, the gradient prediction from the diffusion model can be backpropagated into the underlying neuron field through differentiable rendering and our differentiable isosurfacing. Here are some of the generated results from our model. Our model is able to generate both like high quality geometry and also high quality textures. And the reason for this behind this is are two things. So first, as I was mentioning, the differential isosurfacing allows us to specifically focus on the 3D surface and optimize for that 3D surface. And the second, since in this case, we can render the image at a much higher resolution, and then such high resolution rendering will then give us a lot of supervision signals on how this high frequency details will look like. Okay, so beyond the applications that we have demonstrated, we are also very excited to see broader adaptations of our method in other applications, such as the articulated object generation, like single image to 3D reconstruction or human generation, etc. We have also open sourced the code from our method in NVIDIA coding libraries. And at the same time, there's also very wonderful CUDA implementations from UCSD. Okay, so until now, we have talked a lot about the advantages of the 3D mesh, and we can incorporate this 3D mesh into generative AI systems through differential rendering. But however, the question that I have always been thinking is that, is it always we need one particular representation for every 3D content? Like, are there any kind of like universal representation that we should really work on? Either it's 3D mesh, NeRF, or like 3D Gaussian for now. But actually, when we look at the content in our real world, the answer is no. Like, for example, in this case, I have a cat. When looking at my cat, it seems like it's super hard to use mesh to represent fur of my cat. And such thing is also very common in our real world. For example, this is a picture I took under the Space Needle like last Sunday. And then it may be very, like, it might make more sense to using a mesh to represent the structures of this Space Needle. But however, when we look at the sky, it seems like it's super hard to use a mesh to represent the structures of the cloud. So this means like we probably need to think deeper of what kind of representation we should for different object or for different like 3D content. So to analyze this deeper, let's look at this kind of examples. So this is like a human models. It contains many different structures like the hairs, eyes, or other face. And to our interest, like there are two different types of regions that deserves our focus. The first type of region is the hair of this human. like for example, and the reason for that is because such region is very fuzzy, and it contains a lot of semi-transparent patterns that are very hard to be modeled with a 3D mesh. For example, suppose I want to render these regions using a 3D mesh, then that means I can only render one point. But it may be not true because like this region is very fuzzy and contains so many semi-transparent stuff there. So this means that it might make more sense to represent these regions using a volume-based approach, such as a Newton field. However, on the other side, if we look at the face of this human head, it makes more sense to using a mesh to represent this content because this is a very hard surface. We do not need to spend a lot. We do not need to sacrifice a lot of computations, such as to model the outside of this face or the inside of this face. So in this case, even under this kind of one object, we might need different representation for one object, and we can also extrapolate it out. We might need different representation for different things, for examples. And this also motivates for our new representation. We call it adaptive shell. We hope to model such spatial varying complexities and distribute the computation or the expressiveness of our model according to the local geometric complexities. And this is also a joint work with Zian, Frank, and Merlin from NVIDIA. So, and this also got the best paper award at SIGGRAPH Asia last year. So specifically, what we want to achieve is that we want to first automatically derive the probability of a surface region, whether this surface region is a hard surface or a fuzzy region. With this probability, we then derive two shells to bounding the 3D content within this shell. For example, in this video, we have two shells. One is a blue one, which is the outer shell, and the other is a yellow one, which is the inner shell. What we want to regularize is the whole 3D content will be spatially bounded within these two shells. That means, suppose we have the face region, then the bandwidth between these two shells is very small, which means it's very closer to a surface-based modeling. But on the other side, suppose we are looking at the hair regions of this human head. The width between these two shells is very wide, which means it's much more closer to the volume-based rendering, or like a volume-based representation for 3D content. And through this kind of two shells, and through this kind of spatial varying width of these two shells, we can achieve a very smooth transition between a surface-based approach versus a volume-based approach. Okay. So, and then let's look at the rendering process of this, we call it narrowband rendering. Let's look at the rendering process. It's actually very efficient. For example, suppose these are two shells. The outer one is the outer shell, and the inner one is the inner shell, and we assume the 3D content is bounded within this shell. If we shoot the ray, and this ray doesn't hit any shells, then that means this ray will hit the boundaries. Then we never need to render any points along this ray. And if this point if this ray hits 2 points, but the intervals between these 2 points is very small, and this means this region is very close to a surface-based modeling, then that means we probably only need 1 point along this ray, which is the same as a mesh-based rendering. However, on the other side, if this ray also hits 2 points, but the interval between these 2 points is very huge, then that means this is the volume regions. Then we probably need to sample a lot of points along this ray according to the width of this intervals. And the benefit of this representation is every kind of different scenarios can be done in one pass, and we can do it in one framework for both surface-based rendering and also volume-based rendering. Okay, so in this video, we compare our method with like instant NGP, and then in this thing, with single object, we can achieve like 5 times speed up, and also like say similar qualities compared to the instant NGP. We can also extend our works into the NeRFs like 360 Cs, and it also gains the speed up compared to the instant NGP. Okay, it's finished. It's almost 10 times speed up. 10 times speed up. Okay, so and also because of this we can also like extend our representations with a physical-based animation. So in this case, we first reconstruct this 3D cat and then like physically animate this 3D cat in this video. Oh wait, why it's not looping? So and this is also very, very cute. I like it. So okay, so this is like what we have been talking about the 3D representation for 3D content creation. But there's still like a huge work to a huge gap between what we want to achieve in the end, like to create a realistic 3D virtual world and enable the immersive interaction between the human and the simulated virtual environment. To achieve this goal, there are two things I feel like we still need more exploration. The first is that how we are able to generate artist-level 3D content such that the quality is closer to what we can see in our real world. And second is that how we are able to build a 4D content creation such that we are able to interact with this dynamic 4D content. For example, for the first part, when we look at the content in our real world, we could really zoom in and discover super fine-grained details on the geometry and appearance. For example, the eyebrows of this human. To generate such fine-grained details, we need to study both the 3D modeling approach that are able to model such fine-grained details, as well as the supervision that can give us signals to optimize for our representation to generate such fine-grained details. Along these directions, although we have been talking a lot about we don't have enough 3D data, but one thing I also want to mention, although we talk a lot about this kind of we don't have enough data, there are many 3D information within existing 3D data set that we are ignoring, such as the mesh tessellations, or the UV mapping, or something like the part annotations from the current 3D data sets. Many current 3D generative AI systems neglect such information, but such information is particularly important when we want to explore the generative asset into the graphic engines for animation or simulation. And so in the future, I'm also looking forward to extend how we are able to generate artist-level 3D content. And with all of this, I'd like to thank all of my collaborators, from the University of Toronto and also NVIDIA, and thank you all for listening. I'm happy to take any questions.
We have time for a few questions.
So on the slide relating to physical objectives, there was a pretzel. Yeah, so the question is, the pretzel was animated, but the solid texture on it was not. So do you think that the inner and outer layer of the 3D technique can solve that kind of texture issue, similar with the hair?
Oh, you mean these regions? Yeah. That's a very good point. So the only thing that we animate, this is only surface-based approach. There's no inner stuff. Like we have some internal structures because this is a tetrahedral mesh, but it's not the same as what we are doing in the adaptive shell. Yes, but it's good to explore. Yes.
Do you have any thoughts on using flex cubes for editing geometries? Like the classic guidance, X and image or something else, and the classic guidance directly to this representation to edit the geometry as you optimize.
Yeah, I think that could be. I think there may be two different approaches that we can do such a kind of adding approach. One is what we can do is for example, after we extract the mesh, then we can directly add in the extracted mesh. This is one way. The other way is because we're still relying on the online neuron field to represent the online structure. So we can also do the editing on the neuron field, and then run the flex cube to get the 3D mesh. Yes.
Any more questions? Maybe I can ask a question.
Sure.
Have you thought about how to extend this kind of representations for large scale scenes, or 4D generation or 4D reconstruction?
Yeah, that's a good question. One limitation we do have is it's very hard to extend the mesh for the large scale scene reconstruction because there are so many phases. And one potential application that we have been thinking of is, I think, Sanya has already talked about, so I can talk about it. It's we'll release a FVDB representation, which is basically a sparse voxel grid for the large scale scenes. And it might be worth exploring how we can combine this mesh-based approach with this kind of sparse voxel grid. And talking about the 4D reconstruction, I think that's a very good direction. And one thing I really like is 3D Gaussian, because it's very easy to model the dynamic of the 3D Gaussians. And yeah, I think there's an opportunity to combine the 3D Gaussian with these different representations.
I have one last question. So is Magic 3 state of the art for text?
What's the question?
Is Magic 3 the state of the art for text models?
That's a good question. Well, I wouldn't claim this. I don't want to make this very bold claim. It was the state of the art. I would say this one.
Okay. I guess let's thank Jun again for his one talk.
Yeah. It works when it shows the Zoom stuff on the window.
Yeah.
Not sure how to hide it. Okay. There's still a little.
It should go away in a second. Oh, is it not going away?
Okay, perfect. Sorry.
Hi everyone. I'm glad to introduce Professor Angela Dai. Angela is a professor at the Technical University of Munich, and she leads the AI lab there. And she has done a lot of work on scene level extraction, general extractions, and scene and understanding. And now I give time to Professor Dai to start her talk.
Thanks for the kind introduction. So I'm happy to talk here a lot about 3D, I think, which is very interesting because, of course, what everybody has been hearing about and seeing are remarkable advances in text, image, and video-based models, right? So here we've started to see advances that really seem to break through in terms of realism, of understanding these 1D, 2D, 2.5D kind of data modalities. And a lot of it has, of course, been driven by text and image data, of which there are a lot. So we are thinking of these models as being trained on pretty much everything on the internet, which is certainly at the billions scale, if not at the a few orders of magnitude, possibly more internally. And so, of course, when we think about 3D, there are a bunch of questions that people have been asking. So one of them, of course, is actually, can we do everything on video instead? Because actually, video data, we have a lot of it available. Publicly, less than probably some companies have access to, but certainly video is available at scale. Inherently, video also encapsulates some kind of notion of 3D representations. Although at the moment, I think with current technologies, it is difficult to extract that 3D scene representation out of videos, right? So structure from motion doesn't work reliably enough on in the wild kind of videos like YouTube. And that makes it challenging to get out that actual explicit 3D representation rather than something that might be learned implicitly in the video domain. On the other hand, so obviously I'm more of a fan of 3D because we have the ability to perform direct spatial understanding on a 3D representation. It's very efficient for spatial kind of queries if you want to do interactions, move the stuff around. For interactive applications, I think we need to have this kind of spatial foundation. So I'm just going to say, because I think you've already heard throughout the 1.5 days of CVPR that you've probably already been here about video foundation models. So this is a little bit tongue-in-cheek because I actually think video foundation models are super impressive, but I also think they're kind of overrated at this point. And I'm very happy to be proven wrong in a year or so, but I guess there are a couple of big questions here, which is, what is actually the downstream application? Or are we really aiming to just generate, GIFs for social media? What's the actual application for video generation? From a graphics standpoint, for content creation, I think this is not enough. The scene representation is not editable. So if you think about replacing Hollywood and so on, that kind of content creation pipeline actually looks wildly different from what we can do with video generative models here. From a more theoretical perspective, it's simply a bit unsatisfactory that we do actually have to throw billions scale level of data at a model for it to learn something about the world. It's not very data efficient. And from a perspective of learning, you have to then learn things like view consistency, temporal consistency. This kind of stuff was originally kind of challenging from video generation models that leveraged heavily this image generation pipeline because they had a tough time learning through sort of temporal consistency in the video generation model. Whereas actually, if you want to learn on an inherently 3D representation, you could get a lot of this stuff for free to generate the 3D representation and then produce the video by rendering that representation. So that should be, in a sense, a more efficient learning pipeline. Of course, I'm just going to throw this out there and then not necessarily provide the full solution, because I hope that everybody here will start looking more into how we can actually, build stronger, more powerful 3D models. But there's, of course, then there's a question of what do we do with 3D data? I mean, if you look about just some of the more popular text and image and video data sets that are publicly available, these are multiple orders of magnitude, in the millions plus kind of scale. Actually, with Objaverse, we do have quite a large set of 3D objects, which is pretty nice. But there's like a continual drop in terms of orders of magnitude, right? When the more complex and sort of more spatially informative the data is, the less that we have of it. And if you go to 3D scenes, we're sitting somewhere around thousands, which is not the greatest in terms of, solutions where we can then throw massive quantities of data and hope that we can actually learn the best from it. And of course, in terms of data collection, we have this traditional trade-off between quantity and quality. If you want to collect relatively low-end kind of quality of data, we can potentially do that now. Lots of iPhones have depth sensors. And that's something where, maybe you can motivate a sufficiently large number of people to collect that kind of data. You would end up somewhere a few orders of magnitude larger than what we see currently available. On the other hand, I think what's happened to really drive forward a lot of this progress is high quality data, right? So strong curation of text is important for things like ChatGPT. And we want to be able to see actually, how can we learn from high quality samples? So, I mean, that's probably a question that a lot of people are debating right now. Do you want to gamble for quantity, or do you want to gamble for quality? Because usually you can pick one and sacrifice the other. At the moment, what we're trying to do is produce more on the high quality data set. And inevitably, that's going to be a lot smaller in terms of quantity, right? So this is already something that we've started working on several years ago in terms of reconstructing indoor scene kind of environments. And this is on the more commodity sensor kind of side, where you can, this looks really nicely dramatic now. Okay, never mind. I don't get the cinematography quality anymore. So here you can go around with a commodity sensor. Of course, back in those days, you weren't able to go around and collect data with an iPhone, but you could go around with iPad and a structure sensor and actually collect a bunch of data of 3D scenes. But of course, this doesn't really look that real, because you see there is a lot of over smoothing, a lot of noise in terms of the reconstruction. And the conclusion of working on this data set for several years now is I think we're really missing these high fidelity samples. So data-driven learning is actually a lot easier if you can learn on higher quality kind of data. And so this is the aim of ScanNet++, right? Which is to say, okay, let's try to get out as high fidelity data as we can that scales to some degree, right? So we want to be able to collect something in the thousands kind of order of magnitude, but still have a much higher fidelity representation of the environment. And that you can already see in terms of being able to resolve objects. Actually, the annotation on the original ScanNet data set was challenging, because it was actually very hard for a person to recognize what objects were in the environment, because they were kind of blurry, blobby messes, regardless of whether you saw it in the geometric domain or whether you saw it in the color and appearance domain. So here you actually have a much easier time recognizing the objects as well as reconstructing them. And with a high-end kind of appearance. So here you see the quality of the iPad color camera that we used for the ScanNet data set, and now we have a much better model of appearance based on DSLR captures. So that's going to be an approximation of some of the highest end ground truth that you can capture in terms of appearance that we can still scale to a large number of scenes. So what we have here is a high-end laser scan in terms of representing the geometry. That's about 1 millimeter level resolution approximately of the scene reconstruction. We have a high-end color capture in terms of DSLR image capture. that was also very helpfully informed by Ben Mildenhall as to how to potentially capture the most reliable DSLR that can be used for good appearance modeling and novel view synthesis. And I think what's also important is the tie to commodity type sensor data. So it's, of course, it's not really feasible to expect that eventually we will scale at this kind of high-end sensors. The best chance for scale is something like cell phone cameras, because of course everybody these days even already has a cell phone camera that can capture mostly RGB, but also can capture RGBD kind of streams. So in practice, these are the sensors that we're using. We have a Faro laser scanner. This is a big clunky kind of scanner, but it gets us really nice geometry at very high resolution in terms of the geometric capture of scenes. The Sony Alpha 7 is a very reliable kind of capture in terms of DSLR, and we use a fisheye lens so that we can actually capture much more information about the scene in terms of color appearance. And the iPhone is an iPhone 13 Pro, where it's basically the default settings in terms of RGB video capture. So in particular, I think, given the exponential rising interest in terms of like radiance field, understanding 3D scenes from radiance field representations, and this optimization for them based on novel view synthesis, we did also intentionally try to push forward the boundaries of, what are actually novel views that should be able to be generated by these scene optimization. And so here you see the train trajectory in blue for a couple of these scenes, and the test cameras are taken outside of the train trajectory. So here we are asking people to actually generate views that are more novel. They don't appear necessarily along the lines of a trajectory. It's less of an interpolation task and more of an extrapolation task, although still certainly in the same scene and largely seeing the same kind of content. So you would hope that eventually we can be able to much more reliably generate these kinds of images. So I think that this has a lot of potential, hopefully, for appearance, for generalized kind of 3D scene representations, both in the geometric standpoint, where we have a lot of high fidelity detail in terms of the appearance capture, as well as for things like general semantic understanding, which is a lot, I think we have a lot more diversity in terms of objects, but it's almost potentially an easier task because they're much more separable when you see them at this kind of high fidelity resolution in terms of the geometry of these kinds of environments. I think in terms of the annotation task, you can suddenly start to annotate, the individual plates or the individual books on a bookshelf. And that's, I think, valuable information in terms of grounding all of this low-level information into something that's much more human interpretable, since human perception and human interactions often operate at the level of some kind of notion of semantics. Probably not specifically this task of, let's say, semantic segmentation and one hot kind of version of class labels necessarily, but certainly understanding what kind of objects are in the environment, what we can potentially do with the objects in the environment. So this is a data set that we've already released that has, in October, about 380 SANs. And you can see there's a large number of DSLR frames, iPhone RGBD frames, and we have a lot of different kinds of class categories that have been annotated by people and across a large number of different instances. In fact, I think this 380 is a little bit small on the side of generalization. So we've been, since that time, actively collecting more and more scenes with this idea of keeping in mind a sufficient diversity to hopefully generalize to some degree when training just on the indoor scene kind of setting. So actually, we internally have what you see these values here, about 830 scenes, probably a few more since I made these slides a few days ago, and a lot more capture in terms of the appearance and the class semantics. So you can look forward to seeing that in a few months once we reach the 1,000 scan mark. And we'll be releasing the new version of that with I think enough data to start to be able to mildly generalize when training just in domain on that particular kind of data and looking at other kinds of indoor scenes. So I think there's also a lot of interesting things that people can do on this particular data set. We have already put out benchmarks for novel view synthesis and semantic understanding. So for novel view synthesis, we do have two data modalities, right? The high-end DSLR capture and the more commodity kind of setting in terms of iPhone data. So my hope would be that eventually we can take the input iPhone data and produce scene representations as if they were reconstructed with the high-end DSLR setting, which is certainly going to be much higher fidelity than if you optimize directly with these kinds of methods on the iPhone data without any of that extra knowledge. In terms of semantic understanding, we've got some of the classical tasks in terms of 3D semantic segmentation, just labeling the objects in the environment, and we have currently around 80 classes because there's a very, very long tail in terms of the semantic annotations that we do have. So the 80 classes are benchmarking those at least that have been seen a few times in the trained scenes, as well as, for instance, segmentation, since obviously understanding the notion of objectness is actually critical to a lot of different kinds of applications here. So in terms of the novel view synthesis, the DSLR capture is meant to provide really like a pseudo ground truth. So certainly you can look to optimizing this for specifically the test images that are separated out. And you can get already quite a nice novel view synthesis by just running a state-of-the-art method. This is Nerfacto, but actually 3D Gaussian splatting does perform a bit better on the scenes. And it already looks quite nice in terms of the appearance model from this kind of novel view synthesis. So here we're really trying to provide something that approximates some notion of realistic ground truth of a scene that does contain an inherent 3D representation that's tied to a high fidelity geometric capture and also the lower fidelity commodity inputs. So that's hopefully allowing for enough of a bridge to start to understand captures that more represent in the wild kind of settings. So here we already have the benchmark actually set up and released, and you can go and check it out. On the novel view synthesis side, we've already got a couple of different kinds of methods that are out there. You see that PSNR is not that high at the moment in terms of the ability of these methods. And that's also, we're hoping to test the boundaries a little bit by asking views to be synthesized in these more novel camera positions that aren't actually pulled out of the sort of original capture trajectory. So this is trying to push the boundaries a little bit in terms of this kind of understanding. I'm hoping to also see some more generalized methods. That's not something that we have on the benchmark so far, but certainly on a scene-specific setting, this is also hopefully allowing for people to have a more unified setting in order to test their methods in terms of novel view synthesis. So here you also see the semantic side in terms of semantic and instance segmentation. We've also got a couple of various different kinds of methods that are competing at this level. I think there's also still a fair bit of room for improvement. And what's nice is that we're also asking you now to actually identify these kinds of small objects, like you see the books on the bookshelves in terms of object instances, because we can finally start to annotate them actually to a degree for benchmarking purposes. So I think this is one element in terms of providing some high fidelity samples. I wouldn't, of course, expect that that the models are trained purely only on natively 3D representations, but I think there's quite a ways that we can go to leverage that kind of information. And in particular, the other kind of 3D data that we do have available at sort of reasonably large scale is that of object meshes. And by that, I mean very specifically in terms of meshes that are constructed more like how humans actually create these kinds of meshes, right? Because this is what fits in, you know, modern content creation, modern rendering kind of pipelines. This is also what Yawer has done here on his MeshGPT project, that very elegantly actually learns this model from large-ish sort of 3D mesh data. So I think, you know, it's actually pretty important for many applications to directly generate the 3D mesh representation. So of course, the amazing thing about neural fields, radiance fields, is that they're highly optimizable. The gradient flow is extremely good across the entire sort of volumetric representation. And that means a lot of good things for learning and optimization, but then generating a mesh out usually means that we run marching cubes and get out this kind of marching cube style mesh where you don't quite resolve sharp edges, and you have to run some kind of mesh decimation approach in order to get to something that's of a much lower polygon count. Whereas if you look at a similar kind of object, a lot of objects are varying in terms of their complexity. The top of a table can be quite simple compared to the rest of the object, and maybe we don't want to be able to spend the same amount of triangles that makes it difficult to model a flat surface here. So then, of course, the question is how can you actually represent a 3D mesh here? And this was really inspired by the success of sequence modeling and transformers for language, because GPT models have shown you can actually teach a model to speak all kinds of different languages, even coding. So, you know, why don't we just consider the triangle mesh as entirely a sequence of triangles? And that puts it into this sequence modeling formulation. And we can then directly model that sequence of triangles with a transformer. So of course, first to get that sequence of triangles, we construct this vocabulary of the mesh triangles. And so here the triangles are encoded as a graph over the faces. There's this quantization that occurs that's important to make sure that triangles actually snap to each other. And they should then be decoded to their actual reconstructed mesh faces. So once you have that vocabulary, you can then go ahead and train a transformer across this kind of mesh face vocabulary. And this is basically just a GPT style model. So it's quite nice in terms of its ability to, you know, scale with the amount of data that we have. And it's just a start sequence, a bunch of sequence of triangles, the end sequence. And then we predict what the next triangle should be in terms of the code book. And so the sequence here, because we don't actually know what's the sort of intuitive sequence that a person would model a series of triangles. And to be honest, artists don't actually model meshes truly as a sequence of triangles. The sequence that we employ is just going in ZYX order in terms of sort of applying this arbitrary sequence. And that's also inspired by Polygen, which showed that this kind of sort of sequential ordering of mesh triangles can actually do something. So you get a mesh generation process that looks like this in terms of generating triangle by triangle and building that up in terms of the next triangle prediction for this mesh. And that can be trained. Here we train on ShapeNet on a couple of different kind of class categories. And you get a lot of nice sort of very compact, sharp mesh representations based off of this kind of training. And in comparison with these other works that tackle things from a more implicit field or mesh generation or let's say other mesh parameterization kind of methods, we can get quite a nice representation of the clean, compact nature of these kinds of meshes here. And here you can see another example where you have quite some detail in terms of the bottom of the tables that are generated and a much more clean, flat surface on top of that particular table. So the cool thing about this is that it's being trained on ShapeNet. So in the end, that's something like 5,000 chairs on a per category kind of basis. It's not super large, but we do actually have the ability to generate novel shapes here. And So here you see a couple of just generated objects and their nearest neighbors from the train set in terms of the geometric distances here. And what you see is that it learns to sort of recombine different elements in order to produce these kinds of shapes. So we learn something more than understanding just the structure of the training data, but really how to start to recombine local different geometric structures in the objects that are being seen here in terms of the actual mesh structures. So I think this is also something that is really promising because it's a very difficult representation to learn from an indirect perspective. So here we really need to know what are nice kind of mesh structures by looking at native 3D data in order to produce that kind of data characteristics for these particular 3D shapes. Whereas when you want to learn this from, image or video data only, you have only the notion of whether it looks good when it's rendered and not necessarily whether the mesh topology is actually useful in terms of the actual geometric structures here. So that's why I think we need at least some strong signal in terms of what 3D data actually looks like when it's high fidelity, because that signal is also what we need in order to potentially bridge it to other kinds of data sources that are much larger but don't actually have that explicit spatial signal in terms of 3D. So finally, maybe just a few comments on bridging this kind of 3D, 4D kind of perception where we have fairly limited amounts of data, and how we can potentially also pull in signal from big, image and text kind of models. One very simple thing that we've done is to ground the feature learning here to text features, because in 3D, when you deal with a very small set of classes and a very long tail in terms of the data imbalance, if you look at text encodings, they don't really have an issue of not being able to easily understand, a tissue box, because that appears far more often in text training data. So that means that you can end up with much nicer sort of feature structure in the feature space when you do this. In fact, there are now many more sophisticated and better approaches to tying this kind of information into 3D learning. But I think the thing that is really interesting is, can we actually learn about things where we're really missing data? And that's like things like interactions. So we talk about this 4D modality. Suddenly you're not in the thousands domain. You're really in like the 10, 20, maybe 100 kind of setting. And this is something that we've explored in terms of generating these interactions based on a text description in a 3D scene without any training at all on 3D interactions. And that's purely based off of the sort of imaginative capability of these, text to image generative models. So if we just ask a model like Stable Diffusion inPainting to produce images of interactions, then they can actually produce some reasonable kind of imagination here. And so then based on that 3D scene, we can start to fill in that prior in order to inform what that 3D should look like. So here, this is really just, how do we bridge this together in terms of consistency? So we can render a bunch of images. We can ask a model to then, paint in a person performing that particular interaction. And we have to be a little bit careful about how we do that, because the person shouldn't actually overwrite the actual background context. But this you can do by looking at the attention of the person token in the text. And then you have a bunch of interaction hypotheses that we can interpret as pose hypotheses. So these are 2D poses that are then being optimized for view consistent 3D representation. Obviously, not all of them are going to be view consistent here, but this is something that we can optimize away. So we can optimize for the ones that produce the best consensus in terms of the weight here that tells us what is a potentially consistent 3D interaction. And I think this is super powerful in terms of understanding now situations where we have no inherent native 3D training data, but we can use that extra generality from these kinds of models. So I think I'm getting a little bit low on time, so I'll skip past here and just say, that kind of generality and bridging together of high fidelity 3D samples and this powerful general information is really promising in terms of future directions. So I'm happy to take some questions if there's time as well.
You have one question? So, earlier you mentioned basically, like for section and also like maybe like like various camera positions for like a 360. So I think with this experiment, we would show say the profile or video model.
Right, so you're saying, okay, what about multi-view diffusion models? Because they can produce things that look multi-view consistent. And they do look actually quite nice, a lot of this stuff at the object level. I think inherently this is really challenging if you actually do it on an image by image basis, actually. So what you're looking for is a diffusion model that makes a consistent prediction out of a probabilistic head of different images. Theoretically, you can get something that's close, but not 100% consistent. And I think that's also why most of these models, if they want to produce a 3D representation, they then feed it into a radiance field or Gaussian splatting or something like this, because that's what actually produces finally the 3D consistent representation. So it's not, at this point at least, it's not good enough to only produce the images. Because it's not a representation that can produce arbitrary kind of camera views around. And at least currently, this is also limited mostly to this kind of canonicalized domain with like objects and so on. I think that's going to be more challenging to extend this to be much more general, but I think in the end, you know, if it was good enough, we wouldn't have to throw them into a Gaussian splatting representation to get the 3D representation out at the end. So I still think that we want to be able to learn from the explicit 3D representation. But certainly there's a lot of rapid developments in this area. So it's just generally very exciting to see.
Let's thank Professor Andrew from
Okay.
I'm glad to introduce Professor Xiaoguang Han as our next speaker. Xiaoguang is a professor at the Chinese University of Hong Kong, Shenzhen, and where he's leading the GAP lab. His lab has done a lot of cool stuff on 3D modeling. In addition, he's also made a lot of contribution to the community by proposing a lot of data sets, such as ImageNet, HumanNet, and the DeepFashion 3D. And now, next, Xiaoguang will talk about how to prepare data for 3D generative foundation models.
Okay, good afternoon, everyone. So thanks for the kind invitation. And So it's my honor to be here to share our recent works and some of my thoughts. And today I'm going to talk about the 3D generative foundation model from data perspective. So my talk contains a few technical details, but more about experience and more about some thoughts. Okay. So let me start the talk with a story about a story about a 3D chair reconstruction. Okay. Okay. Let's go back to 8 years ago. So what is the hardest topic in 8 years ago? So maybe one of the hardest topics might be single view chair reconstruction. Okay, I call it a chair because it just usually use a lot of chair category as a representative category for single view reconstruction. And the topic aims to reconstruct the 3D object shapes from single view images, such as 3D R2N2 and point set generation from Professor Su Hao, and also AtlasNet. Okay, so all of these works focus on the 3D representations ranged from voxel, point cloud, and mesh. And in 2019, so 3 works proposed to use implicit representation. Okay, so after that, all of the works about just use the SDF as the reconstruction tasks. Okay, and the follow-up works also try to reconstruct the whole thing, such as our group proposed the total 3D understanding, which aims to instance level reconstruction from a single image. So the instance level reconstruction means we need to reconstruct all of the instance meshes from just a single image. And our group also proposed the RFDNet, which has the same goal, but not from image, but from a noisy point cloud. Okay. And so take this as a background. Let's revisit the instance reconstruction of indoor scene problem. So in real scenarios, we know it is not difficult to capture for each instance the point cloud and images. So we can define the problem as, so we take the point cloud and the multi-view images of, for example, one chair and as input. And we need to output the 3D object mesh, the SDF. So the challenges come from the input is usually noisy and incomplete. Okay, even in the Scanline++ so has a high quality input, but the data is still very incomplete. Okay, and of course we can rely on deep learning techniques to train the model to convert this noisy point cloud to a 3D mesh. But the challenge is it is very difficult to have the paired data. Okay, for example, so we have the example like this, the real capture data like this. The chair is the point cloud is very noisy and incomplete. Okay, so maybe we can imagine that. So how to obtain the ground truth clean mesh for this example, for this instance? I think it is very, very challenging. Okay, so some works try to use the retrieval-based method to provide pseudo ground truth like scan to CD from Professor Angela Day. Okay. And but because it is the pseudo ground truth, because it is not aligned with the input. Okay, and to solve this challenge, a lot of works try to just take the meshes, the clean meshes from synthetic data sets like ShapeNet, like Objectverse as the ground truth, and then simulate the real input point cloud. Okay, and of course this method will raise another issue, domain gap. Okay, so in last year, we also have a work about, we applied domain adaptation strategy to solve this question, this problem. And we proposed a new task, which is called domain adaptive shape completion for real scans. And here, this image illustrates the pipeline. So please look at the left part of the picture. And there have 3 rows. The second row shows the input real scans, which is very noisy and incomplete. And if we directly use the simulating point cloud together with the ground truth mesh as a paired data to train the model, then we apply the model onto the real scans. We will get the result like the first row. Okay. And after domain adaptation strategy, we can get the result like the third row. Okay. And so limited to time, I will skip the details. And then let's just see the conclusions. So we really actually take a lot of efforts to design domain adaptation strategies in this problem, and we finally get the good performance gains. But from visually comparison, so the first column shows the real scan, and the second column is the ground truth. And so the fourth column actually shows the result without using any domain adaptation strategy. And after we apply a lot of domain adaptation strategy, we can get the result like the third column. Okay, and for the last fourth column shows last three columns shows some other trivial domain adaptation strategies. And from the visual result, you can see it is still far from the practical usage. So why we need to design some domain adaptation strategy? Because there is a domain gap issue. The why we have domain gap issue because it is very challenging to obtain paired data. But the why we have no paired data because it is very expensive. So let's consider that when we provide sufficient money, what will happen? What will change? So actually, last year we spent around 1 year to ask the artists to manually craft a mesh based on the real point cloud images. And you can see the image, the money works. Okay, we really get the very well-aligned data. Okay, very well-aligned data. And in total, we contribute around 10,000 CAD aligned allocations for line 20 things. Okay, so with this aligned data, everything becomes easier. Okay, so then we also propose the diffusion-based method to convert image plus point cloud to a clean SDF representation. Please see the left part, the left figure. So here are two examples. And the third row, the third column shows the result of the existing method without using our data. Okay, and with the aligned data, we can get the result like that. So the right part shows the two things, and every instance is obtained from our trained model, okay, based on our aligned data. Okay, so then I think that we can obtain the impressive results, and the story ends. And what does this story tell us? So Einstein used to say everything should be made as simple as possible, but not simpler. And from this, actually from this story, I think we can find that. So maybe data, money, is the simplest way to solve challenges, right? But to have money is not simpler. Okay. And I just mentioned a lot of works about indoor scene reconstruction, and our group also conduct a lot of research about other category-specific 3D reconstruction, like the avatar head, the cartoon characters, 3D garment, and 3D hair. Okay, please take a look about category-specific, and then let's move to talk about 3D generative foundation model. So when we are talking about 3D gene foundation model, I think the first thing we need to consider is the tasks. So today we have a lot of tasks which is already have a lot of 3D foundation models, like Shape-E is for text to 3D. LLM from Adobe is for image to 3D. And MCC, the work in last year, is from point cloud to 3D, which means shape completion. Okay, and to build the foundation model, I think one of the factors we need to satisfy is the generalization ability. Okay, so that means we need to change the category-specific paradigm to the open world. Okay, the open world. And so the first thing, we need to prepare a very large-scale data set. Okay, of course, as long now we have object-verse, a very large-scale synthetic data set. But for real data, regarding the cost of the scanning 3D objects, so how to scale up the 3D scanning of objects is very challenging problem. Okay, and our group proposed to use multi-view videos as a representation. So then it can enable the scaling up of the 3D caption. So we contributed an MV ImageNet. Okay, so MV ImageNet contains around 200,000 objects and over 200 categories. Okay, so in the past, we are very happy to see our MV ImageNet supports a lot of foundation models like LLM, DMV 3D, Recon Fusion, CAD 3D. And on the other hand, we are also not that happy because none of them from our group. Okay, so I think the reason is, so we lack GPUs. So without GPUs, the only thing we can do, we can contribute is continue to collect data. Okay, so then we have MVInternet, the second version. Okay, so the second version contains larger scale data. Okay, so and now the first version and the second version together have over 500,000 videos and over 500 categories. It is just a half size compared with the initial ImageNet. Okay, and also in the second version, we actually a model of the videos captured by 360-degree capturing. Okay, and also we have better annotation accuracy like camera pose, dense reconstruction, and mask. So all of them we just use the SOTA techniques. Okay, so it will be released soon. Okay, so just to mention image to 3D foundation model, and then let's move to talk about point to 3D foundation model. Okay, so MCC, multi-view compressive coding for 3D reconstruction in CPL last year is the first trial in this along this direction. Okay, it's just proposed straightforward encoder decoder architecture and just take a single view RGB D image as the input and just output the occupancy probability. And in this year, we have the work following the similar task and aim to generalizable 3D object reconstruction from a single RGBD image. And our key idea is try to combine implicit field learning with point diffusion. So please look at the left part of the figure. So it has two branches. The first branch is the point diffusion. And the point cloud will become more and more accurate. And we just use the generated point cloud as a query to train the implicit field learning. So this can provide adaptive queries, which will benefit the implicit learning. Okay. And so then let's move to talk about text to 3D foundation model. Okay, compared with image to 3D, point to 3D. So I think text to 3D requires extremely larger scale data. Okay, so it is still like a very good model until now. Okay, because the data is far from sufficient. And the only solution I think is try to leverage the text to 2D foundation model for text to 3D, just a similar like similar Trim Fusion. And then the key challenge is how to bridge the gap between 2D and 3D. Okay. So to solve this challenge, we also have a trial that is, so regarding the gap between 2D and 3D, so we try to lift in 2D to 2.5D first. So that means, so can we generate a text, can we build the text to 2.5D foundation model first? So here the 2.5D means normal map, depth map. So that means we need to build the text to normal map and depth map foundation model first. To do that, our pipeline is we first convert all of the images in the Lion dataset to normal map and depth map using prior models. Like we can use Midas to convert image to depth, and we can use the normal BAE to convert image to normal maps. And now it already have some SOTA techniques like depth anything, okay, to convert image to depth, and also the sign GeoWizard to convert image to normal. Okay, and after that we can just train the text to normal and depth based on the original Stable Diffusion model. Okay, just to fine tune it then, and then we can obtain the text to ND model. Here N means normal, D means depth. Okay, now here shows some sampling results from our built text to ND model space, and you can see that we can get the reasonable results. Okay, based on this text to ND model, we met our work Rich Dreamer. Okay, Rich Dreamer. So using our key idea is use the text to ND as a geometric prior for NeRF and DMTAT optimization for text to 3D tasks. Okay, so I will skip all the technical details and just go to the conclusion and the results. And we found that so the ND prior can produce a better imagination ability. Okay, and so here actually shows the two examples. The first example, condition on the text, the two raccoons playing poker, and the next one shows the human and banana sitting at a desk doing homework. And here's the 3D visualization. Okay. And we also found that our ND prior can help to produce rich geometric details. So that's why we call it a rich dreamer. To be honest, another reason we call it a rich dreamer because we really wish this work can make us rich. Okay. But the realism is it doesn't work. It even costs a lot of money from us, from our group. Okay. And here shows more results. And actually, you can take a care about the middle one. The GEMS is riding unicorn. Okay. I think it very well demonstrated the imagination ability of our model. Okay. Okay, now I just introduced a lot of 3D foundation model, generative foundation model, but all of them are about the general objects. And actually, we also have another very special category or very important category, the human. So how to prepare data for human category? So following MVImageNet, we collected MVHumanNet. And MVHumanNet contains around 4,500 human identities. And for each identity, so it has 2 different data outfits. Okay. And we already published a large part of the data set. And here shows an example about the multi-view capture, okay, of the data. And we also provide very rich annotations like we provide the masks and also 2D skeletons and also the optimize simple models. Okay. And we also provide the appearance text description. Okay. Okay, so then let me end the talk by another story. Okay, a story about the 3D head generation. So let's go back to 3 years ago. So what is the hottest topic in 3D generation area? I think one of the topics should be 3D aware head again. Okay, so EG3D is one of the popular works. Okay, EG3D taught us. So 3D GAN space can be built by only using 2D images, right? But we can see that the disadvantage is actually it has no modeling ability of the back view, okay? So we think the full view 3D head data is necessary. So that means we need to capture for each identity, the multi-view capture, okay? Multi-view images or 3D full head, okay? And so after MVImageNet connection, so we start to collect MVHeadNet before MVHumanNet. Okay. So then last year, it has a work panel head. It is a bad news because it verifies just from the paper presentation, it verifies 2D images are also enough to build a 3D full head again. Okay. But we already studied the collection of MVHeadNet. It's very bad news. Okay. And of course, so the panel head requires the back view images, but it does not require the 3D full data, full head data. Okay. And so when we play with the released code, we find hope. Because in their built panel head space, we find a lot of artifacts, especially on the back view. Okay. And so this also makes us believe more on the necessity of MVHeadNet. So we continue to collect the MVHeadNet. And finally, we have sphere head. And we also proposed a normal spherical triplan representation and a view image consistent loss. And then the good news is the problem is solved. The bad news is actually we don't need MVHeadNet. It is not used. And we get the problem solved. Okay, so then here actually shows a comparison on single view GAN inversion between panel head and our sphere head. Okay, and to conclude, we think for some specific category, for example, 3D head, maybe 2D images may be enough to build the 3D foundation models. And another very important insight is data and money does not mean everything. Okay, so remember the first story, it tells us, so the data and money is the simplest way. And actually this work also, this project also tells us, so data money does not mean everything. Okay. And then let me try to answer the question how to prepare data as a conclusion. So I think it depends on if you are rich. So if you have a lot of funding, if you are from company, and I think the thing you can do is try to scan high quality 3D data. Okay, because the community requires high quality data. The larger scale, the better. And also another thing is try to clean 3D synthetic data, like Objaverse. Okay, and I think it is very dirty. Okay, the more the better. So here the better I think is conditioned on open source. Okay, so then if you are a little rich and try to collect data to reach a trade-off between quality and scale. Okay, just mentioned by Professor Angela Day. So MVImageNet is also an example. That is, we doesn't capture the full 3D mesh or something like that, but it can enable the scaling up. Okay, and I think another very important thing is try to design algorithms to extract high quality 3D info from low quality data input. Okay, and then if you have proof, just use our data. Okay, so and I actually another very important thing I think is, so try to use all available data, like 3D scans, multi-view images, videos, 2D images, synthetic data. And I also think this is not a trivial work to use, so the data from multiple resources. Okay, and another very important thing is try to be rich. So actually, our group was in the second category, a little rich. But now, after collecting a lot of data set, now we are poor. Okay, so the next thing we wish to focus is try to use all of the available data and try to be rich. Again, okay. So then that's all. Okay, so actually, my talk contains few technical details. So welcome to our posters for the algorithm details. Thank you.
Time for a few questions.
Sorry? No, we will not release MVHeadNet. It fails.
So thanks for the talk. I have a problem. I have a question about the MVImageNet. So compared with the pure synthetic data set like Objaverse, sometimes found that, for example, the point cloud could be noisy. So sometimes when I take the point cloud as a part of the input, or I do the loss function over the point clouds, I found the network training to be bothered by the noise over the point cloud.
So you mean actually the quality of the point cloud in MVImageNet is noisy, and you mean so how to build the point to shape completion model, right?
I mean, not that way. I mean, how to handle this noisy problem? Because in some like synthetic data set, we don't have this problem.
Yeah, actually, so this is the thing I just mentioned. So MVImageNet actually has a low quality, but it can scale up. So we need to put a lot of efforts to try to design some algorithms or mechanism to use this low quality data. For example, we can just use MVImageNet, just use the image as the output, and you can design some loss functions to use image as a loss function. Okay, and then you can do some 3D reconstruction just like the LLM.
Yeah, I'm sorry for the inconvenience. And all these kind of things, they are currently integrated into a smartphone. It's just this smartphone. It's not counting my talk time, but it can do all these kind of things. So capturing this data, they are very easy. So we have such kind of data, but capturing 3D data is very hard. So currently, I can make an argument is that there is not a device that can directly capture data. Even there are some things that can capture 3D data, they are very hard to use. So what we actually did is that we need to first capture other modalities, and then we convert them into 3D. For example, we can capture videos, and then we convert it into 3D. And we can use synchronized cameras, capture multiple views of the object, we convert it into 3D, or we capture depths to convert 3D, or we use interactions to convert it into 3D. So I want to make two key points for the motivations of my talk. The first one is that 3D is truly lack of data, but we are actually lack of the method to get 3D data. We are not actually lack of 3D data. So the second point is that, so 3D data, because 3D data is hard to capture, so we need to get 3D data from other modalities. So 3D data creation is naturally a multimodal problem because it's inherently just that you want to convert other modality into 3D data. So in general, so we start our research with the reconstruction model for this reason, because we want to give us ability to get more 3D data. That is just, so reconstruction problem is just trying to get 3D from multiple of images. So, and then I will go to the first part of my talk. It's just I will give a methodology overview of the large reconstruction models. So in general, large reconstruction models that we proposed last year is that it trying to solve the task is the single image to 3D task. That we have an input image and we want to get a 3D directly. So you can see that this is just a multimodal problems, that the input is one modality, that is image, and the output is a 3D. So we also propose a multimodal transfer models to solve that we call it a large reconstruction model. So in essential, so large reconstruction model is just a multimodal transfer models. So you can, I think this figures is usually visible in the multimodal literature that you have one encoder for one modality and a decoder for another modality. So we just bring it to the 3D area. So that is, we have the image transformer encoder for encode the image. And after encode the image, we have image features. And we just use cross attention to send it to the 3D transformer decoder. And then we output the 3D output. So for here the 3D output, what we use is triplet nerf. But I think I do not want to block my researcher to introduce nerf anymore. So you can just consider that this is something kind of tokenizable 3D representations, so we can directly output it. And so because this is using transformers, and so we can use we need a lot of data to train. So we also train the larger reconstruction model based on a lot of data. And so we take the observers data that have about 800,000 synthetic data, kind of synthetic data, and also the ImageNet data from Xiaoguang's group. Where is Xiaoguang? That's fine, but it's just the previous talk. So yeah, we use 1 million data because the single image to 3D is actually a semantic problem that I will get back to this terminology later. So that we need a lot of data to cover this kind of knowledge and semantics. But for the result, you can see that the result is very nice, is that it can work for real images, and then it can work also for generated images. So this is kind of generated. We can do the single image to 3D reconstructions. But there is the issue of in the single image to 3D problem is that it always have generally blurry background. For example, for this Christmas tree, you can find that the front view is almost good, but for the back view, it's very blurred. And the reason is very simple, because larger reconstruction model is a determinist model, so it does not cover the uncertainty. So there are generally two ways to solve it. First one is that you can convert it to a generated model, but the generated model is definitely needs more data to go beyond the 1 million number of data to get all the kind of diversities. So our solution to solve it, we just adding more images as input to trying to also provide front view, back view, and different kind of views. So it just covers uncertainty and ambiguity, so we can do the reconstruction as well. So how we do that is also very simple. So for example, this is a framework for the single view large reconstruction model that we have the neural image encoder and the neural 3D decoder, that the neural image encoder just take one image. So if we have multiple views as input, So what we do is that we just use the neural image encoder to encode the different images separately. And after this kind of processing, we just concat all the features together and we send it to the neural 3D decoder and get the 3D output. So with this kind of models, we can do a lot of work. So we initially think that this is kind of a 3D foundation model, but I'm more conservative now. But in general, later I will just want to show how this work can enable different kind of things. So the first thing it can introduce is 3D generation. That if you have the multi-view library concept models, you can generate multi-view first and convert it into 3D. This is presenting the work that called Instance 3D carried out by our intern Jiahao Li. And you can also directly use multi-view library concept model as a denoiser in the diffusion process. And this is one of my favorite results in the paper. This is carried by Yinghao Xu. And next you can, because transformer is very powerful and it can learn more beyond the 3D constructions, that you can directly use it as a post estimations. And it can do the post estimations and the 3D reconstruction at the same time. And we can do some category specific library concept model as well. That is human. And for the last application is that we can use it as a consistent reward. There is one more thing. We can use it as consistent reward that you can provide as a consistent score to guide the multi-view diffusion to do better. Oh, did I set something wrong? But that's fine. To get the multi-view diffusion to generate more consistent things. So in general, multi-view sparse-view large language models can do a lot of things, and we can train it with different kind of things. And in that sense, we can get 3D objects more easily. So what it enables. So in the second part of my talk, I will talk more about the representations. So previously, all the large language models, we all take the NeRF, especially the triplan NeRF as output. The reason that first NeRF is easy to optimization, and secondly that we use triplan, there are two reasons. That is triplan NeRF. So for NeRF is because it's easy to representation. We use triplan because triplan is a canonical space that is a regularized space, and also it can be easily tokenized. So we kind of use triplan as a representation. But this kind of representation is not very useful if you consider the real graphics pipeline, because real graphics pipeline, you want to directly integrate into some applications like gaming, movies, such kind of things. For this kind of graphics pipeline, we want to have directly mesh algorithms piloting output to be more interactive. So we also work on trying to have larger exponential model which can directly output the mesh and the Gaussian splitting. So for these two works, I would not go to too much of the model details, although there are a lot of things to make it work. I will only show the results because I think that we use other representation only because they are easy to integrate into other graphics pipeline. Otherwise, NeRF is still the best if you just want to optimize the model. So in general, I think that the results largely improve from the NeRF model. If you first get a NeRF first and trying to do marching cube to get the mesh, it's never get this kind of results. So, and this also method can work for generated images as well. And this work is done by our intern Xingyue. And Xingyue is from Haosu's lab. And so yeah, this is also have some generalizability that it can work for the generated results, but I think it's not so surprising now. It should work. And for the method, I want to talk a little bit about the method. That is, in general, what makes the mesh RM work is that we have the differentiable marching cube modular, which is written by the first author Xingyue. And it's kind of open source, so everyone can use that. It's very efficient and very useful to use. And so after we have the NeRF, we can, previously we just run the more marching cube to get mesh. So currently we want to make it a process fully differentiable. So we also have a differential marching cube that is get mesh so that we can train the whole pipeline. So this is the idea. So there's a lot of novelties. I do not want to list them, but I just want to highlight the challenges that I will keep repeating in the remaining of this talk, because I think this is very important. That is stability. So in this work, we have a lot of challenges in improving the stability. So you can consider there are multiple styles of stability. The first one, maybe I just mentioned one of it, is that For example, if you have a ground truth object and you have a surface, and if you run the differential matrix process, it would optimize both appearance and the geometry. Then the geometry is easily to pull out of the surface. If it is pulled out of the surface, there is sometimes no gradient to pull it back, so it's very hard. And this is one kind of stability. Another kind of instability is that the gradient of the geometry and the gradient of appearance is not easily. So I think the project as an intern senior and the project lead Zhou take a lot of time to figure it out. And so this is for Masha. I also want to talk about another work that takes the 3D GS as native output. So in general, so this work, we have 4 input images, and we can directly output the 3D gradient, 3D Gaussian splatting. And the interesting of this work is that this is actually one of the internal Adobe work that the first authors are Adobe employees. That is not very often in the Adobe research because I do not know the reason, but it's just not very often. Yeah, so you can see that in general, the 3D Gaussian splatting is one of the good things that is you already have better visual quality. I can show some more examples. So in general, you can see that every detail is there, and there are a lot of cool things. But this is not the reason we use Gaussian splatting, because if you highly optimize nerve, highly optimize mesh, you might can also get such kind of quality. The reason we have actually 2 reasons that we would prefer this model. And I think we will continue our later research based on this kind of GSI model. The first reason is that the modeling is much, much simpler than before. So I can explain what's the model details here that I usually do not want to do that. So in general, so there are 4 input images I just listed 2 here. So you first just do the patch file. It's just non-overlapped convolutions that get them into tokens. And you can put all the tokens together and send it into transformers. And then the transformer would give you the tokens as output. You just directly interpret it as Gaussian points and put them together and send it to the Gaussian splatting rendering, then it's done. So it's kind of a very simple modeling things, and it's kind of written by Kai. And so the novelty of this is definitely we have the modeling parameters novelty, but I also want to emphasize challenges again. It's still about stability. So this is actually the second version of our model. Our first version, we're trying to follow exactly the larger concern model pipeline. That in the larger concern model pipeline, it's just it's not pixel aligned Gaussian splatting, that we have a pool of points that we just want to cross condition on the images and get to this point, but it never works. It does not work. Even we transfer to this kind of framework, it's still very hard to train it. So we do some works to trying to make it stable and trainable. But once it's trainable, I think it's quite stable. So we kind of release all these kind of stable tricks in our paper. So we hope that it can help us the understanding. So I think in our paper, everything about stabilities we definitely put in our paper. But I just don't know how to emphasize it. So if you read our paper, just read more about that paragraph. I think that's the best thing we can do. And another thing about the first benefit is modeling, simple modeling. The second benefit is that actually it has better capacity than the NeRF model. For example, we can easily extend to the same level theory concern. This is done by Sai. So for 2 or 4 input photos, we can get a nice thing reconstructions. And we can also connect it with some generated video models to get the this kind of scene generation task. For example, this is a famous video clip by Sora. So with our GSM, we can construct this kind of things. And besides the scene level capacities, there are some other kind of modeling capacities, but this is just inherit from the 3D Gaussian splatting representation. For example, we have some transparent effects. It's easier to get all some fraction shapes. So this is some 3D generation results actually. So, and yeah, this concludes my second part. So that is about that we can directly output 3D representation. And in the last part, I want to talk about the 3D reconstruction data. Actually, so in the previously, all the 3D reconstruction models is mostly trained with semantic data. That is mostly trained with observers. So ImageNet. So we also train our models follow this pipeline that is trained with observers and ImageNet. But in this part of talk, I want to talk about not talking about that we're collecting another data, because we are kind of not rich in data funding. So you know that in Adobe, there are two pools of funding. The first one is data funding, the second one is computer funding, and they are not shareable. So we are not very rich in data funding. So that kind of thing, we are not rich as Xiaoguang's group. So we cannot do it in that side. So, but in the other side, we want to explore what is the minimal request that can be a reconstructed data. So more specifically, we ask the question, so can we train a larger consumer with such a data? So I wanted to keep this slide for a few minutes, maybe a few seconds to take a detailed look of this data. So this is actually a data that is created by Zexiang in 2018. So this is a 6-year-old data. So in this data, what happens to this data is that we have some random shifts, and we just simply merge them together, random tetrate, and then this is data set. So the characteristics of this data is that first, it's really bad. It's just break every assumptions that you assume to be a good 3D data. First, it's purely random, and the composition and the textures, they are all random. And second is it's non-semantic, means that it's completely out of the real data distribution. And secondly, it's really bad quality. That is nothing about the beauty of it. So it looks very ugly. But in the other side, this data is also, we also have all the good things. It's kind of still the best 3D data if we can use that. First one is unlimited. And second one is there is no bias issue. And second one is there is no copyright or license issue. So I want to see highlight the copyright or license issue again, because there are two issues. The first, so I found that most of 3D data are released under usable license, but they didn't care about copyright. For example, you can find the Mickey Mouse in some public data sets that is incorrect license. So, but this data actually is very dangerous to use. In company, we need to filter them out. And so in that sense, it's just a hypothesis. We actually have a debate on whether it can be trained or not, but we just give it a try. So in that sense, what we did that we first create a large amount of this kind of data. That is 400,000 of this kind of data. We call it zero first. It means that it's opposite to observers, that is purely non-semantic and does not have everything. And I think we got the idea of the zero from the AlphaGo zero paper because it's just a kind of something from scratch. And it's kind of surprising to us that actually this works pretty well, and this is done by our intern Dosai here. He's still here. So in general, we found that the quality actually matches actually if you train the model with the zeros and observers. So there are essentially almost no change between this model. We only tune a little bit hyperparameters. So we found that the results almost match each other. So it's kind of surprising results, and I want to show video visualization to compare with them. So essentially, this is virtually comparison between the LM0 and the GSM. So the LM0 is the GSM version trained with zeros. That is the data that you have seen that is completely non-semantic, purely random data. And in the right is the GSM model trained with observers. So they are the same models, but only the data is different. They use the same amount of training, and so everything is almost comparable. So you can see that the results, I cannot see visible difference between them two. And also the metric sets, there is not too much difference. And I think the best thing that I got a QR code in the top left of the slides, so you can get a check of the results, what it looks like. And we provide some interactive tools, then you can actually see the results. And essentially, I think it just works for different kinds of scenarios. It works for real data, it works for captured data, it works for generated model data. So essentially, we found that zeros might be very useful in the later research, and it can be an alternative of observers to carry out the research in the later. And I just have one more slide for the data creation process. So I will quickly talk about it, but no worries if you miss it, because we have released the code. So it can be found in our GitHub, and you can just use it because we do not want to introduce duplicate efforts. So in general, the random process starts from primitive shifts. We have 5 primitive shifts, and we just random put them together and random texture them. So for the textures we have, here I just show 6, but we actually have more textures than this. But for primitive shifts, we just have these 5 primitive shifts. And after we have this kind of random textures, composite shifts, we have the different kind of augmentations to add different kind of things to solve different kind of scenarios. For example, for heat field, it's for curved shapes. And for the balloon difference, it's trying to solve the concavity. And for the second, for the wireframe augmentation, is trying to solve thin structures. And so, yeah, that's it. And I want to conclude this kind of part. I want to talk about the reasons, a little bit reasons why I think that IM0 can work and as good as zeros. So this is the slides from my another intern Hanwen. So in a sense, I think it's related to the different kind of reconstruct task categories, and actually there are needs about the data. For example, there are in here I put a line. So in the leftmost is this single view reconstruction. In the rightmost this is dense view reconstruction. So for single view, definitely we miss kind of knowledge. We definitely need to go through the semantic data to get the knowledge about what the object is like. And in the offset for the dense view, we already know that we can directly go with optimization-based method. So that means that dense view is completely intrinsic problem that we do not need to do pattern recognition. So I'm not sure everyone knows that. So computer vision pattern recognition is 2 things. So computer vision is what I show here. It's kind of trying to do this kind of intrinsic task. And the pattern recognition is some kind of semantic that we need to learn from data. So that means that it does not need PR. And but sparse view is something in between. We are still not sure and we are still exploring. But from this work, it's kind of similar to that. Sparse view reconstruction is still kind of an intrinsic task. So that means that we can possibly just use this kind of non-semantic task to solve a lot of things. And one more point is that we also realize that synthetic data is used more and more, for example, in depth anything industrial, that is our next speaker. So this kind of data, I think it would become more popular and popular in the 3D research. And this is also one possible solution to solve the 3D data scarcity issues. And one last slide is, let me just take 1 minute to finish this slide. So this is my personal notes when working on the IM0. So I really want to share some experience. So how this works actually is. So the first one is that stability is still very important. We have a few sections talking about stability in our paper. And because this is the reason of that we need to do model and data co-design, and each of our components can introduce instabilities. And you never know what happens if you not finish the whole data creation and the model training loop. So it's very hard to turn it. And second thing is about scalability, that we are still not sure, that we actually does not get positive result when we're trying to scaling up, that we does not get for both model size and data size. But we have some guess that maybe for model size, that maybe dense view reconstruction is actually because it's a non-semantic problem. So it might have some threat limitation because we just need to have enough parameters to reverse the algorithm of the reconstruction, then it would be okay. Reverse the algorithm of the rendering, that is reconstruction, then it is okay. For the data size, maybe it's same as above. So maybe the amount of data is saturated to learn such kind of algorithm. And another key comment is here that this kind of project is actually requires a lot of resources. So I mean that we are not reaching data funding, but we are kind of reaching other sense of things, that is GPU hours, and human, especially interns bandwidth, he take a lot of time on that. So this project actually use, at some point, we noticed that it used 1,800 A100 at the same time, just trying to explore different configurations to make it work. And so in this sense, we decided we will release the data creation code and all details because we do not want the waste of the duplication. So yeah, that's all. That's all my talk. let me stay at this figure because I do not have time to introduce all my collaborators. So
I think we have time for maybe 2 questions.
Yeah, that's a good question. In my point of view, I feel that they are a little bit different because 3D objects, we know that we want what we want to reconstruct. But for 3D scene, the issue is that we do not know what we want to reconstruct. For example, if you give a video, I'm not sure what the ground truth we would like. You just want to reconstruct visible things, or you also want to cover the invisible things. So I think this is the main difference. It's about the problem definition. I think the 3D scene reconstruction is still underspecified, that we need some exploration on what we want. Yeah, thanks.
Your work is a very interesting data set. So I think my question is so do you think similar method for creating zeros will apply to create scheme level data?
I'm not sure, and we are actually working on that. So I think it might not be a secret, but in general, I think we can do a lot of things with this kind of data. So the most curious thing in my mind is that we are still not sure. So besides the scene and object separation, my main curiosity is still about what kind of task can be solved with this kind of non-semantic data. For example, can we train the sorry, maybe let me just speak loud. So for example, can we train the Duster model with this kind of non-semantic data? Can we train depth estimation with this kind of data? Or can we train such kind of normal estimation generation, even this kind of thing? I think this might be a very interesting problem to explore. Yeah.
In the light of time, I think we need to move on to our last talk. Thanks, Hao, for the great talk.
谢哦，好紧张，最后一个 part 没有怎么 practice， 应该能看出来。
然后我现在主要在做视频理解的是一个社会的策略，然后我。
Good. Sorry? Yeah. I'll introduce him now. So, everyone, it's my great pleasure to introduce Jerome Rival, who is currently a research scientist at Naver Labs. Jerome's team has recently done a lot of cool, mind-blowing work in 3D foundation models, including Crocker, Duster, Master. So in my personal opinion, this line of work represents a paradigm shift to our 3D vision research, and almost makes me wonder if our large reconstruction model work becomes a downstream application of their models. So without further ado, let's welcome Jerome to talk about their fantastic work in this space.
Thanks a lot for the introduction. I think we saw lots of amazing work before, and I'm very honored to present today. So today I will talk about the story from Croco to Duster to Master. So in my presentation, I will first describe what is the current situation in 3D vision, specifically geometric 3D vision. And what is the current issue, I think, with the situation. And that analysis will lead us to build Croco, and then Duster, which builds on Croco, and then Master. So what is 3D vision? And here again, disclaimer, I'm specifically talking about geometric 3D vision. So it's essentially a bunch of tasks like monocular depth estimation. You have large scale 3D reconstruction, you have point matching, visual localization, multi-view pose estimation, and many more like SLAM, calibration, multi-view stereo, right? So the thing is that so far, all these methods have been handled quite separately. And actually, don't get me wrong, there is lots of amazing work, like for instance, for monocular depth estimation, there's this amazing CVPR papers like UniDepth, so Depth Anything, which are really great. But it's a bit like not satisfying in the sense that all these tasks are somehow really intrinsically related to each other, because they all deal with, you know, 3D pixels, rays, depth, camera poses. So we feel that somehow all these tasks are somehow connected, right? And it's a bit of a pity to have like different methods that actually consider all these problems very separately and very individually. So I actually advocate for a unified model of 3D vision, right? And there is a good argument for that, the case of NLP. So in the NLP community, actually before ChatGPT, there was the same situation, right? Lots of tasks like translation, sentiment analysis, dialogue systems, question answering, right? And all these tasks were also treated separately. And then came large language models and ChatGPT and so on. And suddenly you have a single model that can do all these tasks really well. And it's not just a model that's able to do each task separately. It's also a model that can do everything in between. And that's like exponentially more than solving each task individually, right? So a foundation model, in my opinion, is some kind of like unified model that can solve all the tasks at the same time. So what is a foundation model for 3D vision? Well, there is no actual consensus, I think, on the question. So today we had lots of speakers talk about foundation models in 3D vision, and the definition of foundation model is a bit elusive, right? I feel like nobody has some kind of very strict definition, and that's normal, right? Because the field is still evolving at a really high speed. And there is here a list of like non-exhaustive list of really interesting work on the question. And I think the very weak definition is that a foundation model is like weakly supervised, like trained on the weakly supervised pretext task, and then it gets useful for many downstream tasks. So the minimum capabilities of what this model should have is, I think, the ability to establish correspondences between images, the ability to infer the 3D geometry from priors or from structure from motion, the ability to infer the relative pose between some images, to decompose motion, lighting, effects, long-term changes, and so on. So this leads me to our first work, CROCO, which is the acronym of self-supervised learning with cross-view completion. There's a first paper at NeurIPS 22, and then a follow-up paper at latest ICCV. There's joint work with Philippe, Romain, Vincent, Luca, Johan, and Gabriela Boris, Leonid. So CROCO, very simply, is inspired by MAE, Masked Autoencoders by Gaming A, a very famous paper at CVPR 22. So that's basically building on top of self-supervised learning with masked modeling, right? And that's really an easy formulation. So the idea of MAE is you take an image, you mask most of the content. So with a transformer, it's very convenient because you can patchify your image, and then you just need to discard most of the tokens. And then you get the remaining tokens, which are visible. You go through an encoder, get some representation. And this representation is trained so that the decoder can actually reconstruct what is in these hidden but masked tokens. So the encoder has to produce some kind of rich representation so that the decoder has an easy job, actually constructing the full image. And that's great because you can then learn useful priors about the world. And it's very useful for various semantic tasks. So now, what is Proko? Well, it's very similar. And let's play a guessing game. So what is behind the mask? Well, if you don't know better, it's just like MAE, right? You're just supposed to do some kind of in-painting based on, let's say, the surrounding in this image. But what if suddenly I give you a reference view, right? So this is a second view of the same place. And immediately you see there's this stone pole or pillar, I don't know how to call it. And inside your brain, now you have, I guess, figure more or less what is behind the mask. So what your brain is doing is that you're comparing the two images, right? You're doing some image matching. Oh, this is the same tree. And then you're also understanding the relative pose between these two views. And also, I think you need some kind of depth estimation to understand, you know, the position of objects and how they would move. And actually, you need also to understand the 3D shape of this pillar because it has to be rotated a bit. So the appearance of this pillar will be a bit different, right? You cannot just copy paste it. You have to move it realistically. And you have some colorimetric adjustment to do because maybe the two pictures are not taken the same day at the same time of the day. So all of this has to be taken into account to actually produce the actual pixels that are behind the mask, right? So that's Proko, right? That's exactly what cross-view completion is. So it's fundamentally a task about 3D vision, right? And the way the architecture works, that's actually very similar to MAE. So basically, MAE would be here at the top branch, and the only difference is that you would have this reference view here, and you use the same encoder to encode this view. There's no masking here, and then the decoder would actually attend to this reference view using cross attention. And everything is trained using RGB reconstruction loss, exactly like in MAE. So the nice thing with this is that we can do some kind of synthetic experiment. So we train this architecture purely with random data. So specifically flying cubes, right? We can generate as many as we want, right? They're just randomly colored cubes in the space. And here is the result of the training. So each pair of images has never been seen before, right? All of them are completely random. You can generate an infinity of them. So here is the reference view. And on the right, there's the query image. And this time, like it's not like random masking. This time we really mask the whole like center parts of the query. And here is the reconstruction. And here is the ground truth. So you can see that actually a transformer, so these are just vanilla transformers, right? It's perfectly able to solve the task. You can see that the reconstruction is actually pretty faithful. So what is it doing? It's actually really understanding, you know, the scene in the sense like where are the cues and what place are they? What is the difference in viewpoint between the two cameras and so on. And here is actually another experiment where this time I am rotating the reference view, right? So the query view, the masked view is still, and this time the reference view is rotating. So pay attention to the blue cube here in the middle, right? In the reconstruction, actually, yep. In the reconstruction, this blue cube is here, and it's going to disappear suddenly, because I'm going to occlude this cube here behind another cube, and oh, it's gone. And then I move again, and it appears again. And it's really the smoking gun evidence that the network is not cheating. It's really doing what you think it's doing, like It's basically seeing all these cubes. It's doing some like kind of internal reconstruction of this, and then placing them so that they are in the position they should be in the query reference view. And sometimes they are a bit blurry. It's a bit weird, right? That's actually because when they get occluded, the network is only seeing a few pixels of the cube, and then it has not enough information to understand the full position of the cube. And so it's because this is L2 reconstruction loss, it's just outputting some blurry cube, meaning that it's unsure about the actual location of the cube. Well, so that's really nice. That was a proof of concept. And by the way, if you can do the same thing, like whenever you have an idea to first try with some simulated data, I mean, I think that's really convenient. But after this, we actually train this with actual real image pairs. We collect 2 million pairs from the Habitat Simulator and 5 million pairs from like many data sets like Megadeth and so on. And we fine-tuned Croco, the network, for different binocular downstream tasks. Like this is stereo depth estimation. This is optical flow estimation. And it was actually state-of-the-art, and we are still, I believe we are still state-of-the-art on the Spring benchmark for stereo flow, stereo depth estimation by quite a margin. So in summary, this is self-supervised training method that's specifically designed for 3D vision, right? It is inherently multi-view. It's very important because if you think about Dino and like many popular pre-training methods, they are not multi-view, they are like monocular methods. And this is arguably probably learning important bricks of 3D vision. And it's also a very generic architecture that you can easily adapt for many downstream tasks. But is it a foundation model? Well, not really, right? Because nothing is actually unified. You still need to fine-tune your model to every downstream task individually. So coming back to the 3D vision landscape, and one task is standing out. That's the dense 3D reconstruction task. So could this dense reconstruction be a kind of super task for 3D vision? And the answer is kind of yes, because so this figure is a Colmap pipeline. So Colmap is actually doing 3D reconstruction, right? And in Colmap, you find actually all the other tasks of 3D vision that I talked about before. You have the key point matching, you have like triangulation, multi-view stereo, you have like pose estimation, and all these kind of tasks are inside this super task. So Colmap is actually the secret agent behind a lot of progress recently in neural rendering or novel rendering and so on. It's used to have good initialization of the camera parameters and sparse scene points. And Colmap is really good. It's basically a pipeline that's been optimized during several years, but it comes with a lot of restrictions, lots of limitations, and these are actually the official guidelines. You should basically avoid textureless images. You should avoid like specularities, high dynamic range. You should have lots of overlap between your images. You should have lots of different viewpoints, right? So if you fail to have like all of this requirement, then your reconstruction is most likely going to fail. So the current solution is quite problematic. It's brittle. You need enough images, enough overlap, enough textures, enough viewpoints. It's also heavily handcrafted at all levels, right? It's honestly, I think this is a bit of an engineering hell. It's becoming so complex that it's really hard to, you know, like improve a lot on it, in my opinion. And there's also something not really satisfactory, is that it's solving multiple minimal problems sequentially. Because historically, the problem, like the task is just too hard to solve it in a single step. So researchers have been breaking it down into multiple simpler problems, right? So the first problem would be pixel correspondences and so on. And the pipeline is sequential and you don't really have internal collaborations between these solvers, these minimal solvers, even though it's actually making a lot of sense to have collaboration between these solvers, because typically pixel correspondence could benefit from the relative pose estimation and from depth and this kind of thing. And last point, POLMAP is quite slow. Now the big question is how to reconcile, 3D reconstruction and deep learning. We want to put some deep learning into the equation, but it's a mess, right? You have lots of different data types. You have images, you have poses, depth maps, meshes, normals, intrinsics, point clouds, you name it, right? It's like from, let's say, an engineering point of view, you have all this together. Is really hard to combine in a single deep learning framework. There has been some attempt though, for instance, there is Metric 3D, there is UniDepth, there is many more at this CVPR. Most of these approaches are monocular, meaning they take a single image and they convert the image into 3D. And with some success, right? It's still quite handcrafted, in my opinion, but it's still limited to like single views. There's also VGG SFM, which is also CVPR paper this year, which essentially takes POLMAP, makes it differentiable, and that's quite something. Actually, that's quite impressive. The only, I think, big problem is that it's still behind the hood. Is still relying a lot on POLMAP. I think it needs to be initialized, like all steps as far as I understand, needs to be initialized with POLMAP. And it's not really outputting dense outputs. So it's like half the job is done, kind of. And this leads us to DUSTER. So DUSTER is the acronym for Dense Unconstrained Stereo 3D Reconstruction, a joint work with Shujo, Vincent, Johan, and Boris. So we start from Croco. The architecture is really simple. That's the beauty of it. And we make it symmetric. So instead of having like a single decoder on the first branch, now we have a second decoder on the second branch. And instead of outputting RGB, like reconstructed images, we output point maps. So what is a point map? It's basically just an image, but instead of having RGB values, you would have X, Y, Z coordinates of points that correspond to pixels. So for each pixel in the image, you have a 3D point, right? And that's the output. That's very simple. And here is actually what is output for these two input images. It's very important to note that the two point maps are expressed in the same coordinate system, which by definition is set to the camera 1 coordinate system. So camera 2 here is represented, but it's not actually an output of DUSTER. I mean, like, we can recover camera 2 as I will show later, but the output is really just the point maps, right? The dense grid of 3D points. And this is trained with a regression loss, like really in a simple manner. So we assume we have the ground truth point maps, and that's it. We just try to regress, to output what is in the ground truth. So from these point maps, so you have this like unconstrained image collection as input, right? The output is for each image, you have one point map. What can you do with that? Well, you can actually recover the camera calibration. Somehow, the calibration is actually encoded inside the point maps. You can recover this really straightforwardly. You can get depth estimation, dense depth estimation. It's also in the point maps. Like literally, you have nothing to do. It's already there. It's just the Z coordinates in the point maps. And it works. It works for the monocular case with a single image. It also works for multi-view. You have pixel correspondences because these are just basically nearest neighbor in 3D space. And because you have this, dense 2D, 3D mapping, yeah, you can go back and forth between 3D and 2D. We can cover the camera poses for like just a pairwise case, multi-view, or even absolute camera pose visual localization. And of course, then 3D reconstruction. Essentially, the point map is really dense 3D reconstruction of the scene. So just by outputting point maps, we can do all these tasks seamlessly in a very straightforward manner. Right, so how do we train Duster? Well, we just take all the data sets we find where we have dense ground truth, meaning like camera poses and depth maps, more or less. So we use Habitat, Pose3D, ScanNet++, ARKit Static Sync 3D, Megadepth, Blend, MVS, Waymo. And by the way, all these data sets are actually available on the GitHub if you want to retrain Duster for yourself. So yeah, in terms of what some illustration of what you can do. So point matching, I already discussed that. Recovering the intrinsics, we learned some evaluation, like is it how accurate the intrinsics are, and we tried on Habitat, Blended MVS, Pose3D, where you have lots of variance in the intrinsics on these data sets. We find that the estimation by Duster is really faithful, especially in the binocular case. Like you have 2 degree, I think this is the average, average absolute error in field of view estimates, right? It's not the median, it's the average. So I think 2 degrees is pretty good. And yeah, we can perform visual localization. And if you have more than 2 images, then no problem. Actually, we have this global alignment that takes, all the point maps for every pairs that you have, and a very simple optimization problem that's essentially like a well-behaved 3D version of bundle adjustment that takes just a few seconds and basically align all point maps in the same coordinate frame. And then after global alignment, you have this multi-view poses, which we show are state-of-the-art on Pose3D and real estate. And it's actually working even with 3, any number of views, like even 2 views is still as good, right? As I was saying, we can do depth estimation, monocular, and multi-view. And this is really actually, I think, a milestone because it's the first time that the same method can apply to both monocular depth estimation and multi-view depth. And historically, these 2 families are actually treated really differently. Monocular depth estimation is like prior-based approaches that learn, to predict depth just from RGB and from RGB priors. And multi-view depth would be actually completely different, would be matching and triangulation. But we have Duster, we can do both of them exactly in the same framework, right? With the same model, same way, same everything. And it's actually state-of-the-art, right? And it doesn't need the intrinsics. So multi-view depth, normally you need the camera intrinsics. Well, we don't need them, and it's still state-of-the-art. So something else I think is important is it's a bit small. Here we have no Propo version. So basically we pre-train Duster with Propo. We show in the paper, we have some ablations to show that if you don't pre-train with Propo, it's actually much worse. So this Propo pre-training is really important, right? To I guess learn some useful 3D vision priors into the network. These are some 3D construction example. So the same model works indoor, outdoor, on large scale outdoor scenes, close-up objects like object-centric data. And it surprisingly even works on opposite views. This is something we discovered after the training. This was not intentional actually. And somehow it's working. So here you have the 2 input images on the left, and here is the output on the right. You can try it for yourself. It's quite surprising. The most surprising thing being this impossible matching that I think is a bit famous now. So you have these 2 images without any overlap, meaning there's no correspondences. But it's still okay, actually. Somehow the model has no issue doing some reconstruction without any correspondence. And this is, of course, completely impossible with, I think, all existing methods, right? A structure for motion is building on correspondences. And if you don't have correspondences, I'm not sure what you can do. Well, for Duster, it's apparently fine. So in summary, I said before, the current solution for dense tree reconstruction is problematic. It was brittle. Well, Duster is robust, works under any number of images, any overlap, any texture, any viewpoint. SFM is heavily encrypted at all levels. Duster is surprisingly simple with minimal encrypting. It's solving multiple problems all together, right? It's just transformers that are doing things internally. We don't know exactly what. And it's fast. It's actually real time if you get an image pair, it would take about 15 seconds. Right, it has some limitation. This is just an example on the visual localization. So there's different ways of achieving visual localization with Duster. The first way would be, okay, Duster inference and get like nearest neighbor in 3D space to get pixel correspondences, and then use these correspondences for PNP, and then we get the pose, right? The second route is simpler. It's just PNP on the point maps. You also get the pose. And actually, the first route is working much better than the second one. And we observed this consistently on several tasks. So even for 3D construction, if we triangulate the surface rather than just the global alignment, we have much more accurate results. So we wonder, you know, Duster was never trained explicitly for matching. So what if we did? And that's what Master is. So Master is joint work with Vincent and Johan. And it's going to be really quick because Master is basically just Duster that's trained in metric scale. So now the point map, instead of being, you know, scale invariant, meaning like with an unknown scale factor, now is metric. And we have a second head for the transformer decoders that's outputting dense local features, meaning one feature per pixel for the two input images. And by, you know, basically matching local features, we can get accurate pixel correspondences. So why is it accurate? Because this time we don't use a regression loss, we use a classification loss, specifically the info NC loss. By the way, the paper is on arXiv if you're interested, so you can check the details. Right, and then with these precise correspondences, we can estimate the relative pose between two images. That's exactly what the map-free relocalization benchmark is about. So if you don't know this benchmark, you have these pairs of images. So this is image 1, image 2, right? And the goal is to find the relative pose, actually the absolute pose, like metric pose between the two images, right? It looks really hard. Like I'm guessing that even for a human, this is quite hard to understand the difference in viewpoints between these two images, right? It looks like they don't overlap at all. Actually, they do. This is the same pole here, right? And if you input this in Master, this is what you get, actually. So it's actually correct. I'm not saying it's millimeter accurate, but it's actually correct. So the second camera is on the sidewalk on the left, right? So that's how we get actually quite incredible results on the map-free online benchmark. So yeah, I didn't update the table. I'm sorry, there was some new methods, but Master is still first by a large margin, I would say. So we get 36 median translation error, and the next method is like 1 meter and a half. And Duster, by the way, Duster is here. So Duster was actually quite good compared to the rest, with 1 meter translation error. And yeah, we get, I mean, this is really, I think, impressive. Get two degree median rotation error, and like, yeah, 93% in projection, AUC, and so on. So this is, by the way, a benchmark with a private test set. So this is actually really legit. You cannot cheat on the benchmark. Yeah. And beyond the map-free localization, we also perform experiments in visual localization. So we actually get state-of-the-art performance on some data sets like InLoc, which was a really hard data set for like traditional approaches. And finally, free reconstruction. Like I was saying, the Duster is not super precise. Now, Master is really state-of-the-art. We get 0.3 millimeter overall accuracy, and Duster was at 1.7 millimeter in comparison. So matching is actually really important to get accurate camera poses and so on. Recently, there was after we released Duster, we were really glad to see that many people started using it. And in particular, this is very recent work, not from our group. This is from Ziwan Fan, who actually applied Duster to, combine Duster with Gaussian splatting to make instant splats. So basically, after initializing with Duster and putting that in like further finishing the optimization with Gaussian splatting, he gets reconstruction in less than 1 minute. Like specifically, I think you get 40 seconds from scratch, right? That's the most impressive thing. Just have the images, no intrinsics, no pose, nothing. From scratch, you get your 3D Gaussian results in, 40 seconds, right? So here on the left, that's a NeRF-based method that doesn't use the poses. And yeah, you can see how fast it is. And this is, again, another result, 20 seconds from scratch from 3 images. So yeah, I mean, that's very promising. I think there's lots of great things to do with Duster and Master. And I think this is only the beginning. So to conclude, we have then 3 reconstruction in a single step without pose nor intrinsics. I believe this is indeed a paradigm change, right? This is, I think, one of the first, maybe the first time that you don't need intrinsics to get your 3 construction and so on. Duster Master is a universal model of 3 vision tasks. For the first time, again, unifying the monocular and binocular cases. And the point map representation looks obvious retrospectively, but somehow, I don't know why, nobody tried that before. Yeah, so it's simple, neat, and fast. And yeah, thank you. I'm happy to take any question. Okay, yeah, that's actually a question we get really often. I think this is interesting for many researchers. So dynamics in theory, Master, so just first, I want to say that Master in theory can handle dynamic scenes because it's not, so now the 3D points for the 2 images don't need to overlap, right? Let's say you have a vehicle that moves from image 1 to image 2. In the first image, in the first point map, you will get 3D points at like time t0, and in the second image, you would get the point map at time t=1, but you would still get the correspondences between the corresponding parts of the vehicle. So in theory, that's not something we really tried, to be honest. But in theory, you can have scene flow straight from master. Actually, in our training data for master, we have dynamic scenes. We have, I think in the Tartan AR dataset, there are some dynamic scenes and not a lot, but there are some. And it's part of our training data. So how to train that? I guess the easy way is to generate some synthetic data. That's the easy answer. Like if proper pre-training with the dynamic scene would help, yes, for sure. And how to find good training data for dynamic scenes, I don't know. Yeah. Exactly. So you would so for master, not for duster, because for duster you don't have like these local features that gives you correspondences. But for master you have, you know that these two pixels are the same thing, like the same location on the vehicle, let's say, and you can just subtract the points, the 3D points from frame 1 and the 3 points from frame 2, the corresponding one. If the object moved, then the 3 points would be at different locations, right? But that's not something we explored yet. Yep. Yes. So, oh yeah, very good points. Master, the code and model are going to be available mid-July. Yeah. Right. Yeah, so you would need, I guess, to modify the loss. So actually, this is something we tried internally. We have like the loss we use for duster in the paper is really fully supervised, right? Regression. But you can also use, let's say, weakly supervised losses. Let's say if you just have the camera pose, for instance, but not the depth. This works, or if you have sparse correspondences, this also works. You can formulate the loss slightly differently. And if you don't have like any information, I guess you need to go with a self-supervised loss, like I guess with rendering losses, like photometric losses, maybe. We didn't try that. We tried the weakly supervised losses, and it's actually working, but the convergence is much slower. So you would need like 10 times more data to achieve the same quality as with like fully supervised dense regression loss. Yes. No, for the still so much better. It is possible to use very strong like that. So your question is basically like, can you use some, let's say, super strong depth estimation method and combine it to help Duster improve the results? Is that your question? Yeah. 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 Okay. Yeah, I mean, that's something we want to explore. Actually, we didn't try anything, but it's true that in terms of, so Duster is not super precise, like typically with details, with small parts and so on. The network itself is not really big. It's just, I think, VIT large encoder and VIT base encoder. So is it necessary? I mean, yeah. Yeah.
Maybe, it's sort of like a rephrase of your question, because I also share the same question. So, let's say, take a very strong multi-nest estimator, and you use very small amount of multi-view batch data to fine-tune it for.
Okay, this is about training. Okay. Yeah. It's something I want to try, but I didn't try it. I don't think there is an easy answer, easy solution to that. I hope there is, but I don't know. Yeah. The confidence is actually something that's improving. So it's a bit weird that like intuitively you would think that just outputting the point map without confidence is a simpler task that's going to because like the network has a given capacity, right? Has like on fixed network with this fixed number of layers and fixed token size. Is it a bit weird that when you ask it to output more stuff, like specifically point map and confidence, it should decrease, but somehow the quality increases actually if we train it with the confidence. So I guess like internally, computing a confidence, like per pixel confidence, is actually helping the network somehow to perform the task better. That's a bit mysterious, but that's what we observed actually during training. Yeah. Yes.
You know, have you evaluated part with their FPT and people to get like standard
I mean, we evaluated on DTU. Oh, okay. Yeah, we evaluated on DTU on tanks and temple. I'm not sure if we did that. Yeah, it's on our to-do list. The thing is that with Duster, we have potentially a ton of experiments, right? It's not just a single task, it's like 10 different tasks. So it's really hard to do everything. Yeah, we tried our best. Sorry.
Oh, I was just saying that, the workshop, we are running out of time, but feel free to stay and ask your questions.
Okay, thank you. Yeah.
So did you notice that there's very strong identifiers in predicted depths?
Yeah.
So how did you get that specificity?
Well, the data set we use are influence like coming up with dense branch group, I think.
But for like words, etc., they are testreless, right? It's very difficult to get even pseudo.
Yeah, exactly. So that's where the synthetic data is super useful.
Oh, to have it.
Yeah, exactly. Because actually, that's something I wanted to say, is that if you only train from, like, let's say, rendering loss, photometric loss, it's just impossible to get the white right. Because it's a ill-posed problem, right? The Gaussians or whatever can be anything, it's still white. So synthetic data, I think, is something you gotta have in your training. Otherwise,
maybe you can highlight that part, because I feel that this is quite amazing when I tested this colors. Walls and floors are like very flat.
Yeah.
So it's very difficult to
that's
get
all
that.
reports from the ArcGIS scenes and Habitat.
Very impressive.
That's sorry. Yeah.
Do you think that this dust relies on whether it's accused the dust relies on why is the low level appears cues? Not why the high level that is semantic cues. So which two do you think plays a key role in the performance?
That's a good question. To be honest, I don't really know. Duster is like purely data driven. So what we observe is that the more data we have for training, the better results we have.
Okay. So you have this kind of skill.
Yeah, definitely scaling. Like master is much better than Duster because we use twice as more data.
Yeah.
And recently there is this mega scene data set. There is a 360, 1 million, all these data sets which are huge potentially, and I'm pretty sure that if we scale Duster, it's going to be much better than even the top like monocular depth estimators and so on.
Because I think in the logic extract model, what we find that okay, if you have just a sufficient overlap, instead of just with a random texture, random shift, you can train the extraction model.
Yeah.
We seem to suggest that it's a kind of low level task.
I think it's a mix. It's a mix because, for instance, if we try Duster or on objects it has never seen, like human bodies, it's actually not pretty good.
Oh, okay.
So it's definitely learning priors,
okay.
Right? It understands, oh, this is a table, but it must be flat, or this is a wall, it must be flat, right? But if you give some random, like, random shape, it's still doing some okay job. So it's a combination of like priors and geometry for sure. Yeah, exactly. 2D geometry. So it's really similar in some sense in the zero LRM work by Hao presented just before. Just training with fully random data is still get really good results. I think it would be interesting to try the same with Duster. We solve actually a lot of our problem for data collection and data set generation, I think. Yeah, thank you.
I'm just wondering, have you ever tested Duster on the generative images from a different model?
So we didn't. No.
What do you think that, how do you imagine the Duster?
That's a good question. So something that may be a problem is that Duster internally is there is something weird is that sometimes you give two images and you get like no output, like low confidence everywhere. Because internally it's deciding whether these two images are matching or not. And if it thinks that these two images are not matching, it's not going to do anything. It's like it's going to say, I don't know, and zero confidence. But sometimes the two images do match and it's still not, it's thinking it's not, they are not matching because you have some inconsistency between them, right?
That's right.
Let's say if you have one image, you move a bit the table, the second image, then Duster might think, oh, it's not the same thing. So I'm not going to do anything. This might happen if you feed generated like images which are not exactly consistent.
Yeah.
But what we observed with master, so with master we have this map-free data set for training. This map-free data set is really interesting because it's sequences that are being taken like maybe 6 months apart. And so between the two images, you have some substantial changes. The scene like 6 months later is a bit different, right? Have differences. And now we are training master with these images, and now suddenly it's becoming much more tolerant to changes. So now master is actually okay if the scene is a bit different, if the illumination is not the same, the shadow are not the same. Duster is not really, you know, tolerant to this kind of changes. But so it's really data driven. That's my point. If you train it, I think if you train it with this kind of images, then it's going to learn that this is fine and I should do it.
Yeah, so if it is in this case, does that mean that the result you showed that without any overlap, that totally depends on the like semantic understanding during the training?
Yeah, it does. So for instance, it means that this would not work if during training we didn't have this kind of pairs.
I see.
Actually, it was a mistake. We didn't intend to put these pairs in the training, but somehow there was, I mean, millions of pairs. So you will always have some kind of weird situation. We have these weird pairs that don't overlap in the training, and that's how Duster can actually do that at test time, because it has seen the same kind of situation, but basically my bottom line is that you need to at least fine tune it, I think, for this kind of situation. So if you want to apply on generative AI data, I think you just fine tune it a bit, and then it's going to be perfectly happy with it.
Okay, sounds good. Thank you so much.
Thank you.
By the way, my name is Zhi Zhou. I'm from UCLA. I'm currently a PhD student at UCLA, and recently also read a paper for your Duster plus some like semantic foundation model.
Already?
Yeah, and submit to Durex.
Okay.
It's very nice to meet you.
Oh, nice to meet you too.
Have a great rest of the day.
Thank you.
See you.
Hi,
Hi.
Yeah, I'm the first author of LEAP. Yeah.
Oh.
Yeah.
Okay.
Xixing has,
amazing.
Yeah. Xixing told me you have a discussion with.
Yeah. At IKEA, right?
Yeah. Yeah, I like Duster and Coco a lot.
Oh,
so I have a question regarding Coco. So how much like Duster benefits from Coco?
A lot.
A lot.
Yeah, but actually you can still train Duster without Coco. It still works, but there's a big gap in performance. So Coco pre-training I think is really important. Maybe you can reach the same performance with just Duster alone, but you need to train maybe 10 times more, something like that.
So how about Master? Are you still using Coco?
Yeah, exactly. Actually, Master is fine-tuning Duster. So we have Coco, Duster, Master.
So another question is, how do you think of the future of 3D reconstruction? Like Duster is kind of a top-down method.
Yeah. But
Master kind of go back between top-down and bottom.
Yes. I
know. So what do you think?
Yeah, I think the future of so the handling large-scale reconstruction is really challenging from a deep learning point of view, because you have variable like number of inputs. You have actually a huge number of inputs. It's not just 2 images. It's like maybe 10 or 1,000 images, and how to have a single model that's taking all these images, and I don't know, it feels like it's impossible. So I think there is still a long way before you have your like fully differentiable 3D reconstruction pipeline. But I don't know, I think Duster, Master are a first step in this direction. Yeah, that's what I'm reflecting on a lot. But okay, thank you.
I'm wondering if you have mastery on some correspondence tasks, since you have this feature descriptors like sparse correspondence or dense correspondence.
Dense and sparse. You can check the papers on arXiv. And it's so basically it's dense correspondences, but because it's kind of slow to do the full dot product between all features, like all pixels in the first image, all pixels in the second image, and then nearest neighbors, it's a bit slow. So we have a fast like sparse matcher, which is in the master paper. It's it's really fast, and it's actually improving the results compared to the dense matching. Again, checking out.
Yes, thank you. So I'm asking since I have been following work TIBFlow and also.
Oh, really?
I also worked on.
Oh, awesome. Okay.
Since I worked on OrbitFlow before, so
okay.
I worked on the JMFlow.
Because nobody knows Proco usually or TIBFlow.
But I worked on stereo and the flow before.
Yeah, me too. So we came from the same background. Okay, amazing.
So I'm also wondering, so how this. So I love the idea of this unified model, but then also wondering how they will compare with like a specific model, since usually even with a unified model, you will do some task specific fine tuning.
Yeah,
we can even get some performance improvement. So in this case, then we'll even have a same architecture, but we have different ways, different tasks.
Yeah.
So I'm wondering, so how they will compare with task specific models in terms of performance, about performance.
Yeah, I think Master is really good for matching, definitely. We get like whole map level accuracy with Master, but I don't know, we didn't have time to conduct a lot of experiments. I think when the model are released, you can try for yourself. Thank you.
I have a question regarding the data sets. Do you use a lot of various of data sets in the work?
Yeah,
they have
exactly.
different scales. How do you kind of like the different scales? How do you convert them into like one, maybe coordinate?
Yeah, that's a good question. So basically our intuition behind this is that we don't want to have too much redundancy in our training. So let's say even if you have one data set with 1 million images, but it's all images are the same just one scene, you can generate an infinite number of pairs. But in terms of redundancy, it's going to be always more or less the same pairs, right? So what we do is that for each data set, we sample a number of pairs that is proportional to the number of scenes in this data set. So for instance, in Megadepth, we have like 300 scenes, right? So we measure the data quantity of Megadepth as 300, right? And then in, I don't know, in different data sets, you have the different number of scenes. For instance, in, I think in ScanNet++, there's also 300 scenes. But you have some data sets with really a small number of scenes. And then we would sample much less pairs. Because it's just too redundant. You want deep divers as diverse as possible training data.
Okay,
that's the important thing.
I also have a question regarding the like the points. So you know, outdoor data sets, I've seen like they act like these are super large.
Yeah.
But for some indoors, they are like rather smaller.
Yeah.
Do you just use them and then let the model to predict whatever?
Yeah, we have an exponential mapping actually. So I didn't say that. Actually, it's not even in the paper. But when the model is outputting the XYZ coordinates, there is an exponential mapping so that it can, in theory, it can output points which are really far away from the camera kind of easily, like, because regression is always will pose a problem. It's like if you train your network to output points between like values always between 0 and 1, if at test time you have a value of 2, it's not going to output 2, it's going to output 1. Because it has never seen 1 like 2 during training. So yeah, we have this kind of exponential mapping that's, I think, helping a bit, but it's not a big deal. Even if you remove it, it's not changing much.
So when you say exponential mapping, you mean like map the output?
Yeah, so it means like, it's like in the depth framework, instead of outputting the depth, you typically output the log of the depth.
Okay,
right?
Okay.
That's what master or duster is outputting, is actually the log of the coordinates, 3D coordinates.
Okay, so but you didn't like resize the XYZ in any data, so you just use that. Okay.
But the loss is scale invariant with duster. You have actually during the loss, you have a rescaling.
Okay.
So that the ground truth and the prediction are rescaled to have the same scale.
Okay.
It's just dividing by the average scale, actually.
Okay, that makes sense.
Yeah.
Thank you for the great work.
Thank you.
I have one question. So in the slides you presented one table, like in terms of the composition of the data sets.
Yeah.
I see it's a mixture between the simulated data and real world data.
Yeah.
So I'm wondering, like, did you do any testing or experiments like in terms of like whether if you're training on the purely synthetic data, large amount versus just a large scale real world data and versus this combination? Did you do this study?
This slide here?
Yeah.
I think it's not in the paper. We don't have an evaluation of that because we are not really GPU rich, to be honest. Duster is trained on just 8 GPUs for maybe 1 week. We don't have much more GPUs than that. So this kind of experiment, you need a lot of GPUs to try with, right? But internally, initially, we only used Habitats pairs and a really small number. Like here, you see it's like 1 million pairs, but initially we are using just 10,000 pairs, right? And training Duster with just 10,000 pairs from Habitats is actually already working quite fine. So it's helping to have lots of data, but I don't think it's really critical to like having more data is helping to generalize or generalization, and it's also the law of return. You know, the more data you have, it's improving, but marginally.
Yeah, and also, and this is just for training the Duster, right? For pre-training the Croco, you have a larger amount of data.
Yeah, actually, we have. Actually, it's in the Croco paper. It's not exactly the same data, but it's very similar.
I see. So because I'm from NVIDIA, and because I'm also working in the company, so I have some question about the data set. So when you provide the data set, do you need to filter out the unlicensed images for training the Croco, or is that
so depends. So some data set we cannot use them because we are not academic lab. We are like funded by a company, right? Even though we do academic research actually. For Croco, I think we used a lot more pairs which have no labels. Right? Croco is self-supervised. This has the advantage of you can use like YouTube videos, for instance. There is like Creative Commons videos on YouTube. You can use them to make pairs. I don't know if that's what we use actually to train Duster, but I think we used like public license-free data sets mostly.
I see. Because the question, the reason I'm asking is mainly because we also want to use your curated data set.
Yeah. So we released the data sets on GitHub.
So that data set is that a raw data set or the curated ones with the filtering of the pairs?
Yeah, the pairs.
Oh, I see. That's fantastic.
Yeah. So if you want to train Duster right now, you can.
And also, did you do any plot, like the horizontal axis is the number of images for pre-training Croco and the vertical axis is performance?
No. In Croco, you mean?
Yeah, Croco pre-training.
Yeah, Croco we did.
And you find some saturation point where the number of images are really.
Yeah, I don't think it's saturating.
Okay, so
but
there's still some gain.
Yeah, definitely. It's just that it's becoming too big to train.
Right. Yeah. And also another maybe technical detail question. So when you pre-train the Croco, did you balance the samples from each data in each batch, or did you just append the data sets in some ratio?
So actually, if you see the numbers, we have like similar number of pairs for each data set. So it's really randomly sampled. But the full training code is now available if you want to check. But yeah, it's nothing very smart. It's just random sampling, like putting everything together and random sampling. That's it.
Yeah, that's very awesome work. Thank you.
Thank you very much.
Hey, very super excited. I'm actually just finished off the internship with the team that's released Metric.
Okay, amazing. At Niantic.
Yeah, and so recently I just played the Duster and it's working very well. One of the things that I tried is to try to see if they can successfully recover the relative close between a real image and synthetic image. And the good news is it works pretty well.
Oh, okay.
With, for example, Gaussian splats that render high quality image. But the problem is that I want to recover the true scale of the stage. And it is probably not
Wait for master. Master is metric scale. That the true scale is like the metric scale, or what do you mean exactly?
Yes. So for example, in Duster, you tested on the absolute pose regress, absolute pose in 17 and Cambridge.
Yeah.
What you did in your description is you align with the true like cloud or depth.
Yeah.
So that you can recover the true scale.
Absolutely.
But we tested on both 17 and Cambridge without using the alignment.
Okay.
It still works, but we wanted to see if it if there's a way to recover the scale without using those things.
So that's a difficult question, actually. The scale, like recovering the scale, the scale, like,
yes,
3D reconstruction doesn't care about the scale, right?
Yes, I
could have a tiny model and it's still the same rendering.
Yeah.
So to recover the scale, you need some 3D anchor. Like typically we use 2D, like PNP, which is 2D3 coordinates.
Yeah.
You have this pixel, the ground truth 3D points,
yes,
which is what you do with visual visualization.
Right.
And if you don't have that, like, do you have that? No, you don't.
No, we assume that we don't. So there's one idea that we currently come up with is that I can estimate try to estimate the scale predicted by the Duster by using 3 images.
Yeah.
So one image is like the real image. I don't know where the pose is. The second image is probably the render image nearby.
Okay.
So you don't know the scale between these two.
Yeah.
But if I render another image,
I see.
With the main pose, and
actually we have this. I think in the master we have this function that recover the scale.
Okay.
So I think it's going to be released mid-July.
Okay. Yeah, that'd be nice. Yeah, thank you. And another question is that one kid in my lab, so I'm in the Oxford lab. He works on 2D image matching.
Yeah.
So basically, he thinks that Duster may kill the test of 2D matching for like a feature descriptor matching, because I think the main purpose of that task is to recover pose.
Yeah.
And Duster don't need that.
Yeah.
Basically, it could kill his field. I don't know what's your opinion.
Yeah. So actually, I still think that matching is really important. That's why in master we actually do
you add a
matching ahead, right, on the supervision. Yeah. Because without that, you get something that's more or less good, but not exactly accurate.
Right.
And for like 3D reconstruction, accuracy is really the key. It's like if you train your nerve or your motion splitting thing with inaccurate poses, it's going to be really bad, the results, right? You need extremely accurate camera poses and intrinsics. Right. And so I think, I mean, I don't know, Vincent, which is co-author on the paper, disagrees with me, but I think we got to use pixel, like, to have very precise correspondences. Right. Like, even though Duster is outputting some kind of okay-ish relative pose, yes, it's not good enough for many applications.
For example, for a skyscraper toy, which compared with a skyscraper that is real, if they look very similar to each other, Duster maybe will fail to recognize.
This. The interesting thing with master is that master is, exactly the same network as VIT large, VIT base.
Yes.
And we ask the network to do more things because now it has to output point maps and local features.
Right.
But if you think about it, outputting local features is like outputting the relative code, because correspondences and relative codes is like two sides of the same coin.
Right.
And what we find surprisingly or not surprisingly is that master can do both tasks without loss in performance, meaning that it's actually really internally. I think it's actually solving a single task.
Yeah.
It's just that instead of having one output, you have two outputs on the same thing, more or less.
Right.
But that I think that's very interesting because, like, internally we know that Duster is solving multiple problems, and the fact that it's still okay doing more things with the same architecture means that these two things that we are asking it to perform are actually really connected and related, and actually maybe it's not a two tasks but one task.
Right. So just one last question. Sorry.
I have to go. Do you mind if I jump in and then ask? So I run my own computer vision group at Nearmap.
Okay.
We have tens of petabytes of multi-angle aerial imagery.
Okay.
We have all the camera parameters. We design the cameras, including right down to the lens.
Yeah.
We currently do 3D reconstruction the boring way, structured for motion,
using
a very classical pipeline. Two-part question. One is, given we know all the intrinsics of the cameras, do you think we get benefit from master? And the other is, can we get benefit from master? What are your licenses?
So question one, yes, definitely.
Yeah.
With master, we have a new version of global alignment that is actually doing bundle adjustments with pixel reinforcement lenses. So it's way more precise, like extremely good actually. I think it's full map level of accuracy, but much faster. Actually, it runs on my laptop. It's super light. I think it's really scalable. So it's going to be released in mid-July, I guess.
The same non-commercial license.
Yeah.
Is there someone that you can talk to? Like, I assume that people are going to approach and say, hey, can we use this commercially?
Yeah, a lot of people are actually reaching out to us. But the fact that we use all these data sets, which are mostly, commercial data sets, non-commercial data sets. So if we want to make Duster, to sell Duster, or even to make like completely free and open source, we would need to find some free training data. That's a big issue actually.
So when Meta was doing for Dino and things, I think they were separately licensing their code and the model.
Yeah.
So they had, I think for Dino or something, so they would license their code for commercial use, but say the model itself, because the weights came from data sets, had to be non-commercial use. I'd be really keen if I can get contact details for you or someone else to chat to.
Anyway, our plan is to, at some point, to do it.
Okay.
It's actually, we discussed this a lot internally. You cannot imagine how much of a work it is to actually to find a whole bunch of data sets which are the license is good for us, and redo all the pre-processing, generating pairs, and it's actually going back to Tropo. We have to redo Tropo pre-training with new license-free data sets.
And if we were willing to do that with our data and just wanted to use the code,
there is very little chance that the code will be open source. I mean, like license-free.
Not license-free, but if there's a commercial license.
Yeah. So we are working on it. Okay. Yeah.
Is there someone to contact or not?
Vincent or myself.
Yeah, I'd be like, what do you?
You can contact me.
Okay. Email or
email is fine.
Is it?
It's not going to be too soon. I don't know, maybe end of the year or something like that.
I'd be interested in putting my 3D lead in touch with you. Okay. Is your email address?
Yeah, it's on my website. It's easy to find. Or Twitter, you can contact me on Twitter.
Okay. Thank you.
Yeah.
Thanks very much.
Okay, bye.
I just want to send a question. So I play with the Duster and also Mickey.
Yeah.
Also actually just.
Oh yeah, you are the one on Mickey, right?
I'm not seeing the magic anymore. I just finished.
Yeah.
Just but I was just
did you submit the roadmap plus Mickey on Maptree? It's not you. Okay.
I worked on the ACE.
Oh, ACE, that's you. Okay, that's amazing. Yeah. ISO ACE0. I don't know if you.
Yeah, I'm also.
Okay, that's great.
But the truth is that we tested several data sets, compared Duster with Mickey, and the Duster is actually outperforming in
Oh, okay.
But in my point of view, there are a lot of like similarity between the two methods because you're using both using transformer, two view transformer. Yeah. Obviously, there are detailed differences. Yeah. I was just chatting with Mickey author and I asked him what's his opinion. Like, what's the difference? Why Mickey is lower than Blaster?
So Mickey is much more scalable in the sense it's like pairwise approach, right? It's having the outputting key points, I think, without knowing the second view. Duster has this advantage of basically outputting local features or point maps conditioned by the second view, right? So if you have 1,000 images, it would be super costly to run Duster on all possible pairs. Right. But with Mickey, you can just compute your key points on every image individually, and then do some kind of stupid, matching like dot products between all your key points, which is much more scalable. So I think Mickey has this. I mean, it's like a trade-off, right? Mickey is more scalable, but less robust, maybe. Right. Duster is.
Also, I think Mickey doesn't have the cross attention.
Exactly. Yeah, that's because it's another pairwise. Yeah. But if you train Mickey with like pairwise mode, cross attention, it's actually looking a lot like this.
Right. That's my yeah. So I want to test the Duster to run more than 200 images.
Yeah.
Using the flick like the.
Oh yeah. So master can handle that.
Right. Is there any tricks that I could maybe handle it? Or?
No. Because Duster is like dense optimization. Right. It's really hard to fix it. But master is like a sparse optimization, so it's much more efficient.
So when you test it on your 80 gig,
4 gigabyte GPU on my laptop, right? It's working in a few seconds.
So even for like 200 images,
so on my laptop, like 100 images is fine. 200 images, I don't know. Like 100 images, like maybe taking 1 minute. So it's quite fast.
Yeah, I'm really looking forward to it.
Yeah, thank you.
Thank you so much.
Yeah. Hey, how are you, man? Nice to meet you. Yeah, nice to meet you too.
Yeah, we are quarter.
Okay. Nice to meet you. Yeah, so did you attend because I talked about instance management?
Yeah,
right?
Thanks for featuring this paper.
Yeah.
I have one request. So when you record the results for the multiple studio, can you also incorporate our paper? I think we are the one that is follow up the MES tag.
Okay.
Our paper is called Cascade. So this paper. Yeah. So can you also, add this paper in your table for multiple studio results?
Oh yeah. But you mean in the CVPR paper?
I mean master.
Oh, master.
Yeah.
For do we have this table in master?
Well, you have the table, but
okay, yeah, then sure. Absolutely.
Yeah. So my second question, let's say you have the Duster, and we need thinking, let's say, can we extend the Duster into a semantic aware constraint modeling?
I want to try.
Yeah, I have talked with you earlier.
Yeah.
And I need to take some result. I will share.
Oh, really? Yeah, amazing.
So the image, yeah,
wow. Oh, that's amazing.
Yeah, no depths, no depths. And we can lift some features for just really, and we can do the PCA and do this visualizations.
That's amazing.
And open vocabulary communication. Wow. Yeah, so this is one that you can think very straightforward. We don't know. We can recover model to make this more stable. Yeah. What's next? I was thinking, is it possible to make this a more foundation model for action prediction?
Oh, that's interesting. You mean like human action prediction, or
not? Maybe just some model agent.
Okay, like navigation.
Yeah, navigation.
I never thought about that.
Yeah, so my observation or my intuition is that we can represent this to the world. Okay, we know the geometry, but humans just in one shot. And let's say in this case, we can build the 3D map just in one default path. We can do the information reconstruction, and we know the geometry, we know the appearance, and we also know the semantic stuff like this way. Yeah. So can we then do the actual prediction for the trajectory planning?
I would say you can, but then how do you like? I think the Duster architecture is really dense for dense tasks. Like for every pixel you have some like the confidence or the X-ray coordinate of the local feature. But if you want for the motion or the semantic labels or whatever, right? So what we did so far, I think is like a still dense prediction task. Right? Yes, for 3 million. But if you want to predict like actions, is it the dense tasks? I'm not sure the architecture
is this available? Oh, you can access, but we still not make it published. Okay.
Yeah, please let me see.
Yes, so it's called large speech model.
Oh, amazing. Well, congrats. That's amazing.
That's the one that I talked with you about 2 months earlier.
Okay, yeah. I remember. I'm sorry I didn't follow up. So basically the answer to your question is we can talk, but it has to be informal. It cannot be like regular.
Yeah, I also understand that we are all in different companies.
There is some intellectual property issues.
Yeah. So, but what I'm thinking to extend is, of course, we can have more data. Yeah. Right now, we are only use kind of plus data.
Yeah.
We got to.
So, by the way, all the data sets are available.
Yeah, I know that. I don't really let all my colleagues know that.
Okay.
So, I really appreciate for your.
I think just Habitat is missing, but Habitat could come maybe tomorrow or really soon. And Habitat is it's just a dedicated data sets and generate data. So we will make available the scripts to generate all the data.
Yeah, but what I'm thinking is, I do a lot of reconstruction from my to let's say nerve tissue process.
Yeah.
But what I'm thinking of bigger, that's also from your side. As we perceive this work, so we need to do like some agent to do planning.
Oh yeah, I mean that I agree, but what I'm not sure about is how would you use Duster for that? Like it looks simpler in my opinion to have Duster outputs. Maybe semantic labels from depth, 3D, and then having a second network taking, I don't know actually.
So let's do this way. We will have a prediction lab, and we can do sequential remote. So we can make a video from 2 view to any view. That do not consider any incremental error. And this radio build will contain one or spatial information. And we just do a very simple array decoding based on this 2 radio view. And the supervision is just the action prediction.
Okay.
Yeah, so do you think that's feasible?
I think so, but it's hard to say without trying.
Okay. So here,
like, what exactly would you have to? It's like the algorithm is like move forward or turn action space. So actually, in our lab, we have not in my team, but we have different teams working on it. They have this paper. It's called Coco Lab. So Coco is exactly Coco that we use, right? And they do exactly that. You can check this. It's actually not Pokemon. Let me show you.